morning, we are going to open the second day of the final meeting of our project, InnovaConcrete project. The first, according to the program, now the time for our colleagues working the chair of this session the mortars, to the preparation of the mortars and the aging of the mortars. The speaker is Inés García Lodeiro, from the same institution, Instituto Eduardo Torroja, Ciencias de la Construcción. And the second one is regarding to the fabrication of mock-up samples from the case studies. The speaker in this case is Di Andreou from Mirtec, from Greece. And this is the time for the session. Thank you very much, and go ahead, Ita. Thank you.
Good morning. I am going to repeat the same said by María, pero lo voy a repetir en español para que vayan ustedes preparando la traducción. O sea, vayan ustedes preparando los sistemas de traducción antes de que empiecen a hablar los conferenciantes. En estas dos charlas van a consistir en, después de los trabajos hechos desarrollando nuevos productos, estos productos han sido validados en dos sistemas. Uno simplificado. Is not working the translation? Sí. Un sistema simplificado que consistiría en aplicar los productos sobre morteros, un sistema simplificado, y después ya un sistema más similar al que nos encontraríamos en las obras y en los casos de estudio, que sería la validación también de esos mismos productos sobre hormigones. En el primer caso, Inés García Lodeiro va a hablar de la validación que se ha llevado a cabo en el Instituto Torroja sobre la validación en materiales sanos y artificialmente deteriorados para simular en su microestructura los daños producidos por distintos tipos de envejecimiento. Inés.
So thank you so much, Ita, for your nice introduction. So hello, good morning, everybody. So I'm going to give my talk in Spanish, but if you have some troubles with the translation, please let me know and I will try to switch to English. Bueno, hola, buenos días a todos. Como bien ha dicho Ita, yo voy a presentar los resultados de la validación de los productos desarrollados de InnovaConcrete, los cementos de mortero artificialmente acelerados. Bueno, como bien es sabido, el hormigón de cemento Portland puede sufrir diferentes tipos de deterioro. En esta diapositiva pues, os presento algunos tipos de deterioro que pueden tener su origen en causas físicas, como puede ser la erosión, los cambios extremos de temperatura o la abrasión, o causas químicas, como pueden ser la hidrólisis que sufre la pasta cementante por su contacto con el agua, o reacciones químicas entre la pasta cementante y los agentes agresivos, como pueden ser los cloruros. Independientemente del tipo de ataque, las consecuencias para el hormigón van a ser siempre las mismas. Y es un aumento en su porosidad, en su permeabilidad y el consecuente craqueo, la aparición de estas grietas que podemos ver en esta diapositiva. Como bien os contó muy bien ayer María, en este proyecto pues, se han desarrollado diferentes tipos de tratamientos y soluciones para tratar de proteger y de reparar el hormigón del patrimonio cultural. Entre estos tratamientos se pueden destacar los tratamientos de impregnación desarrollados por la Universidad de Cádiz y la Universidad de Creta, o tratamientos superhidrofóbicos también, que van a conseguir repeler el agua de una manera casi al 100%. Otro tipo de tratamientos, como son los desarrollados por la Universidad de Mainz, basados en la biomineralización, el uso también de inhibidores de corrosión desarrollados por el CNR en combinación con los primeros tratamientos de impregnación, o otras soluciones, ¿no? Como son los morteros de reparación. Estos productos de impregnación tienen la bondad de que van a estar especialmente diseñados para proteger el patrimonio en hormigón basado en cemento Portland. Uno de los objetivos del proyecto era la validación de todos estos productos en nuestros casos de estudio que también nos presentaron ayer. Pero previo a la validación en estos casos de estudio, en estos monumentos, es necesario y esencial una validación en el laboratorio, y es de lo que yo os voy a hablar hoy. En este sentido, pues hemos desarrollado diferentes tipos de morteros en base Portland, estándar, unos morteros no estándar, en los cuales se ha aumentado la porosidad con respecto a los primeros, y unos morteros que han sido degradados de manera artificial mediante una serie de ensayos de deterioro acelerado. Con respecto a este tipo de ensayos de deterioro, lo que queríamos era simular en los morteros los procesos de deterioro tradicionales que podemos encontrar en los hormigones de cemento Portland. En este sentido, hemos seguido diferentes aproximaciones, hemos hecho un deterioro de tipo físico, ¿no? Sometiendo estos morteros a diferentes ensayos de hielo, de temperaturas extremas, o hemos simulado el craqueo, ¿no? Por retracción, sometiendo a los morteros a ensayos de humedad secado. También hemos simulado los ataques químicos, ¿no? Mediante ensayos de carbonatación. La carbonatación es una de las causas de deterioro más importantes de los hormigones. La presencia de cloruros, ¿no? Que también va a acelerar estos procesos de corrosión, o los ensayos de descalcificación de la pasta de cemento, e incluso los deterioros de tipo mecánico, ¿no? Donde hemos producido estas grietas, estos cracking a partir de una serie de ensayos de carga y descarga sobre las probetas de mortero. Previa a la validación, es importantísimo una caracterización de estos morteros, tanto de los morteros estándar como de los morteros deteriorados. En este sentido, pues hemos caracterizado todos los morteros desde el punto de vista físico, prestando especial atención, ¿no? A sus comportamientos mecánicos, a su porosidad, también a la cantidad de agua que absorben antes y después de estos ensayos acelerados, y también hemos hecho una caracterización desde el punto de vista mineralógico y microestructural. ¿Por qué hemos hecho todo esto? Porque los procesos de deterioro van a alterar la... y sobre todo qué tipo de test se van a emplear en el laboratorio para ver la efectividad de estos productos en la protección y en la reparación de los morteros envejecidos. Bueno, aquí os podéis ver los diferentes tests que no voy a detallar, pues por falta de tiempo. Y permítanme explicarles de manera muy breve, aunque luego ya en la siguiente sesión nos contarán un poquito con más detalle algunos de los resultados de la validación, ¿no? Aquí os presento los resultados de la validación correspondiente al tratamiento de impregnación desarrollado por la Universidad de Cádiz, ¿no? Se ve perfectamente cómo después del tratamiento, ¿no? se mejora la compacidad del material en casi todos los morteros, aumenta la resistencia mecánica y además, bueno, pues también preserva el color, ¿no? Ya sabéis que los cambios estéticos es un parámetro fundamental a la hora de la conservación del patrimonio cultural. En todos los casos vemos que el incremento de delta E va a ser menor de 5, con lo cual significa que está dentro de unos rangos aceptables. Además, bueno, pues se observa que efectivamente la compatibilidad de estos morteros con los productos diseñados por la Universidad de UCA es del 100%, ya que el principal producto de reacción que se produce es el gel CSH, que como bien sabéis es el principal componente de una pasta de cemento y es el responsable de las resistencias mecánicas y de las propiedades ingenieriles del mortero. Con respecto al tratamiento superhidrofugante desarrollado también por la Universidad de Cádiz, bueno, pues podéis ver cómo realmente a través de medidas del ángulo de contacto se observa que tiene este efecto superhidrofugante. Se consigue reducir hasta la absorción de agua capilar hasta en un 90%, ¿no?, por la creación de esta nanorugosidad, por la deposición de estas nanopartículas de sílice en la superficie del mortero, y también con respecto a los cambios estéticos, pues se ve que son imperceptibles para el ojo humano. Con respecto al otro tratamiento de impregnación desarrollado por la Universidad de Creta, bueno, pues también se obtuvo excelentes resultados. En este caso conseguíamos grados de penetración hasta de 20 milímetros. Se conseguía mejorar mucho la compacidad del material. El análisis de la velocidad del ultrasonido del módulo de Young se vio cómo se mejoraban las propiedades del mortero, y además pues también de nuevo se conservaban estos parámetros estéticos tan importantes de conservar a la hora del patrimonio. Los tratamientos de biomineralización también tuvieron mucho éxito. Como veis en estas preciosas diapositivas, se ve, ¿no?, cómo la grieta se va sellando por la precipitación de este carbonato cálcico, por este efecto de biohealing, ¿no?, que ya os contará más adelante el profesor Müller. Y bueno, con respecto a los otros tratamientos, pues también no os voy a contar mucho porque tenemos luego otra charla específica de esto, pero también fueron bastante efectivos. En conclusión, ¿no?, que los productos de InnovaConcrete han sido validados en los morteros, tanto los morteros estándar como los envejecidos de manera artificial, con excelentes resultados. ¿Cuál es el paso siguiente antes de la validación de los monumentos? Pues la validación en los mockups. Pero de esto no voy a contar nada porque ahora pues vamos a ser nuestra compañera Día de Mirtec que lo va a contar. Muchas gracias.
Bien, Día Andreoli va a contar también la validación de todos los productos, pero en este caso ya en un sistema mucho más parecido al que nos vamos a encontrar en la realidad, porque es sobre hormigones. Pero además es sobre hormigones que están elaborados para obtener las mismas microestructuras y propiedades que los hormigones que se han tomado de los monumentos. Es decir, en lugar de ir directamente al monumento, se hace un hormigón simulado con la misma microestructura y entonces se validan los tratamientos. Día.
The introduction. So my name is Diane Andreoli, I'm working for Mirtec SA, and I will present you some critical aspects regarding the work carried out in the InnovaConcrete project for the fabrication of mock-ups from the case studies. But first of all, why we need the monuments mock-ups? Mock-ups need, first of all, to simulate the monument's concrete in order to study the application of the new developed products in the project and be able to validate the products in different labs. From yesterday's presentations, you saw that all the monuments, each monument has a special type, a special origin, so each monument has a different set of characteristics that need to be considered in order to have the most appropriate mock-up for each one. So the work is starting with entities based on the characterization of the samples we have from the monuments. In InnovaConcrete project, several characterization techniques and samples were used in different labs. So a plethora of results were collected, and we tried to summarize all the results and concentrate, let's say, focusing our aspects in critical parameters in order to be able to fabricate the mock-ups. Some critical characteristics from the monuments are the construction material, if it is a concrete or if it is a mortar, the binder type, if it is cement, lime plus cement, the aggregates type, if it is dolomite, siliceous, granite, etc., the mechanical strength of the samples, the porosity characteristics of the samples, the pore structure and porosity, the durability damages for the monuments, and also, the most important, the type of main deterioration causes. Having this in mind, we are able to decide for the mixed design for the mock-ups. Then, in order to prepare the mock-ups, we need to know the number of samples we need in order to do the validation testing, but also the geometries and dimensions of the samples that we need to prepare. Then the mock-ups need to be aged artificially in order to be able to apply the products and proceed with the validation of the products developed from the labs. This is the value chain of our work. So one by one, all the steps. The first step, as I said before, is to collect the characteristics of the monuments. A plethora of results were collected. I think that the specific deliverable were hundreds of pages with all the characteristics of the monuments. And in order to, let's say, focusing on the most important one for the mock-ups, we simplified all this history in a table for each monument. We took into consideration, as I said, the concrete of mortar, the binder type for each case, the aggregates used, the porosity, the cement content, the mechanical resistance, with all these tests, and also the main cause and comments for each specific monument. Then we came up with the mixed design for each of these monuments. Each monument had a special mixed design. For Centennial, we have MD1, for Elogio MD2, etc. And for some monuments with similar characteristics, we decided also to have some special mixed design. The binder, the porosity, and the aggregates were again selected in this mixed design. One important property which took into consideration was the porosity. The porosity affects also the penetration depth of the InnovaConcrete products, so the mixed design was guided mainly through the porosity property. So the next step was the preparation of the mock-ups. The appropriate specimen dimension for the validation test were decided, and this was mainly based on the requirements from the test method used, the limits that exist due to the aggregates size. There we need to minimize the wall effect of the aggregates and also to minimize the dimension effect from the pulse velocity test. So we end up with three types of geometries for the mock-up samples: prismatic, cylindrical, and some special prismatic samples having also the steel rebars. Then suitable available raw materials were collected. We had to collect it in appropriate quantities in order to proceed with all these preparations, and of course we characterized the materials we used. Two types of cements were used, Chem2, in order to let's say, to control the strength of the mock-ups that we produced, and several aggregates were again collected and used for each specific mixed design. In this table, you can see the number of mock-ups produced for each mixed design in the different geometries, for the prismatic, cylindrical, special geometric, and you can see some pictures from all these mock-ups prepared during our work in InnovaConcrete project. As you can see, close to 800 specimens were produced, and more than 2 tons of materials produced in lab and distributed in various labs in order to validate the results. It is important to mention that we achieved to have mock-ups that exhibited similar characteristics in terms of strength and porosity, as it was our goal for making the simulation of the monuments. The next critical step was to perform the artificial aging of the produced mock-ups. So the chemical degradation was based on chloride penetration and carbonation, and physical degradation was based on freeze and thaw and wet dry process. As you can see, for each mixed design and for each monument, different, let's say, aging was decided. For example, for Elogio, which is located near to the sea, chloride penetration was also selected as an aging process, while for all the others, due to the long lifetime of the monuments, freeze and thaw, but also carbonation was selected. As I said before, a high number of samples produced for the mock-ups. So we had to prepare for InnovaConcrete project several big installations in order to have the chloride penetration testing, the carbonation, and the freeze and thaw. In these pictures you can see some of the chambers. The conditions was based on the results we had with the mortars from the previous work. So we proceed with the same model, but for the mock-ups. At the left you can see the chloride penetration, at the right you can see the chambers and some samples from the carbonation. You can see here some pictures from the carbonation depth for different mixed design samples. And here you can see the freeze and thaw artificial aging. Some industrial size equipment was used in order to have this artificial aging, big furnaces for wet drying process. And the important here with the artificial aging of the mock-ups was that we managed to have an effective, let's say, artificial aging. This was proved also from the capillary rate values. In this table you can see for all mixed designs the capillary rate value for the sound samples and for the samples after the carbonation, freeze and thaw, and the chloride penetration. As you can see from the carbonation we have a reduced value of the capillary rate, which is expected as we have smaller pores, so a smaller water absorption. While after freeze and thaw, because of the cracking induced, we have higher values of the capillary rate. Here you can see the mock-ups that after the aging were delivered to various partners in order to test our InnovaConcrete products. And the last step was the validation. The validation in InnovaConcrete project was decided to base on various standard test methods. Various parameters were tested according to these selected methods, and for these tested parameters the specific dimension the specific samples with the dimensions were used. An indicative case of, from the evaluation that we performed is the chloride penetration, which is a very critical, let's say, parameter for the new materials. For this specific parameter, 400 tests were performed for validating the InnovaConcrete products, and in these figures you can see the chloride content percent versus the depth from the surface, the chloride penetration depth in samples. In the left we have blank samples, that means samples after aging but without any product applied. And in the right we have the chloride content after the application of an InnovaConcrete product. It is clear that after the InnovaConcrete product application, the chloride content is 4 to 5 times less than in the case without this product. And some concluded comments from our work in mock-ups preparation. This was a real challenge work for us. This is mainly due to the lack of concrete mixed design data on the construction time of the monuments. The materials used in several samples, even from the same monument, exhibited some heterogeneity. The characterization of the concrete samples were performed from different labs, and the most challenging issue for mixed designs was to compromise between the properties of the concrete of the monuments and the new prepared concrete. Again, special attention was given to the porosity of the concretes that affect the penetration depth of the samples, and appropriate specimen dimensions were produced for the validation after the appropriate accelerated aging. Sound and artificial aids mock-ups were used from different labs in order to validate the InnovaConcrete products. The validation work was based on several test methods and standards, and it was a very complex and time-consuming work. And the important is that from the plethora of the collected results, the high effectiveness of the products on mock-up samples was observed. It was in agreement with the results from the validation on mortars, and thus all these results from the mortars and mock-ups guided the work for the application and the validation on the real monuments. That is all for me. Thank you.
Thank you, Ria and Ines, for your excellent presentation. And if someone has a question.
Thank you very much for very interesting. So I have a question on evaluation of durability. So you remarked on this, and then in the second presentation you were mentioning how porosity defines the depth of the penetration of the product, and then you went through possible erosion causes of this. But what is the expected evaluation and durability? How long, how resistant will this product be on monuments? So in how many years do we have to reapply? And then I have another question. So is it one layer that you put, or do you need 2 layers? Is it improving the resistance with number of layers? And a bit of a long shot question, how much do you think this product would cost per meter square?
Okay. I'm going to answer because we did some durability tests of the specimens after the application of the treatments. I'm not sure if we are going to show something about this afternoon. So after the application of the different treatments, for example, the impregnation treatment, the superhydrophobic and so on, in both in the standard mortars and in the decay mortars, we submitted these specimens to different types of durability tests. In all the cases, we found that the specimens without these treatments behave much more worse than the specimens with the treatments. So in this sense, we have to say that the durability is quite good. I couldn't provide you a certain numbers of years because it's going to depend on a lot of conditions, not only the original state of the concrete, but also the environment. So probably maybe the people who has designed the product has more information about this. And with respect to the price, I think Maria or Noni or Rafa even can answer you about how much it costs.
I think, to add something, I think that Sika made the calculation regarding the price that each product could have. This is based on the application layers that used. I think that perhaps Antonio from Sika could add something. Maria.
So, hello. The calculation, approximately calculation, was done by Rina in the LCC, and it could be around between 7 and 10 euros by kilo or by liter. Okay, but about your question about durability. This is something we used to work on this, and this is a difficult answer. Why? Because it depends on the different concrete situations. It's not the same. For example, the weather in Kaunas or the weather in Gijón. So what we can do, what we can say is that we have experience, for example, with the Sika when one of our materials, and we have seen in the lab, which is similar results. So that means if we have experience with our product for more than 10, 20 years, this product can be worked like this or more, you know. So we are very helpful about these technologies because it's going to prevent the entrance of the concrete of the different bad product for the concrete. Sorry. So then it's going to increase the durability of the concrete for sure, but it's difficult to say. You know, for example, we work with aging machines with QUV, and people used to tell us how much if we do the 2,000 hours, 6,000 hours in the QUV machine. Say how much time? It's not possible to say, but we can say we have experienced that more than 20 years. So that means it's going to be the same or better, you know? I don't know.
Thank you. Just a question. I want to know if you... Oh.
I think now in the next part of the meeting we are going to explain the products. Maybe we are going to discuss again regarding to these issues. Just I would like to say that in the case of the price, the point of view for people in the InnovaConcrete and people from SICA and the companies in the InnovaConcrete is that the price has to be similar to the products in the market. And the point is, we have, in the case of the impregnation products, just in the case of the products from University of Crete and products from University of Cádiz, they are very similar in composition to the products in the market. It's just a sol gel process, like in the products in the market, I mean from Baker and from other companies, international companies. And the difference is not the components, is not the synthesis route, it's just we change very slight difference in components, in our case, in the case of the catalyzed, and we produce the CSA gel. This is only the difference. That's the reason we have very similar route, chemical route, with very similar price. And this was the starting point of the project. We need similar price because in the market, the people they are not going to pay more money because it's a traditional market. And okay, this is very high, a product with high effectiveness with higher effectiveness than the products in the market, but people they are not going to pay more money, and this was the starting point. Regarding to the durability, we study the durability for different aging tests, durability tests, and so we don't have the results in the monuments because the first application in a complete restoration was in Italy during the project in Abruzzo, but we calculate the service life, and the service life of the product is over 50 years, and this is more than the most products in the market. And regarding to I think another question about layers, about the application, we have two different products, and it's different in one product and another product. In the case of the impregnation treatment, we applied twice two impregnations applications, and this is okay to obtain the success of the product. But we have different products. I think in the next section, you are going, and all people, you are going to know all the products, the difference between products, and we have different products, different solutions with different applications, times, different conditions. So, thank you. And
And sorry, I forgot to tell one of the best experience with this project, and it was impressed to our tire market refurbishment inside SICA, is that the work that David Ines did in the Kaunas Monument, after 18 months, still this effect was working. When our actual materials, it disappeared in a year, in 1 year, it disappeared. So it was impressed to our people there in the market. That's why there is a big interest inside SICA to continue with these technologies. So I think we are so helpful about this, and I think it's going to be a very good solution. Also about the codes, we always recommend 2 codes, but in the test we did, it's a pity we cannot share the test in the video, we had to apply in our system 5 layers, while with this material, in this case from Yucca, we only apply 2 layers. Same results, even better results, only with 2 layers. So we think it's a very interesting proposal. Okay?
The last question.
Just one question. In order to reproduce reliable mock-up samples comparable with different monuments, did you have the possibility to have archive data about the real kind of binder used in these monuments? Because there are different Portland cements, and it's very difficult from the chemical analysis to come back to the original kind of binder. Thank you.
Actually, we have some information for the cement used at that time, but not for all the monuments. But we need to take into account the cements existing now in the market. So we try to use cements, several types of cements, in order to have, let's say, the mechanical strength close to the ones exhibited in the monuments. For sure, the technology of the cement was not the same at that time and today. And this was also a challenge for us to decide which kind of cement for each specific case we'll use and how we will change the water-cement ratio in order to target the porosity and strength characteristics. This was the way we try to solve this problem.
In the case, our case, in the case of the Eduardo Torroja Institute case study, what we did, it was to extract core samples of the concrete and analyze the samples from the chemical point of view in order to identify the type of aggregate, the type of cement, the microstructure, the pore distribution, and so on, in order to try to reproduce exactly, or not exactly, but a very similar concrete that the one that we have already. And not only have considered it also, but also the pathologies. That is why we have selected the accelerated test to be the most similar one that we have already identified in our monument. So this was the different steps.
Well, thank you very much. And the next session. I'm sorry.
Okay, one more question. So, you were talking about, again, back to porosity and penetration of product. But now my question is, do you think this product can be used for brand new concrete elements, for infrastructure, climate-resistant infrastructure, or because it's brand new pieces of infrastructure with hopefully smooth layers, so not much porosity and permeability, then it makes no sense? Or is there a space for usability of this product for this concrete infrastructure elements, like dams or bridges or whatever climate resistant?
For sure, the microstructure is going to have an important impact in the penetration depth and in the degree of uptake. But you can also apply it in brand new concrete, because the concrete has an internal porosity. So it's true that maybe the pore size distribution is not going to be the same, but it's a measure to protect the concrete. So you can apply also, and it's a traditional approach also to protect with super hydrophobic products, or with this kind of impregnation treatments.
Yes, I would like to remark that now Janet, in next section, he's going to present the relationship between the depth penetration and other experimental parameters. And we have different parameters that they are going to modify the penetration, not only porosity. And I think in the next section, I want to remark that the modeling was really important to know how the effect of the parameters of the soil of the products regarding to the penetration. And I think you can modify this composition, you can modify the product according to the characteristics of the substrates, and you can apply perfectly the impregnation treatments or other treatments, InnovaConcrete treatments in sound samples or in sound buildings. Okay. The next section is regarding to the InnovaConcrete materials and techniques produced during this InnovaConcrete project. Now this is the time for our overview about the technologies developed during the project and validation results. We also we are going to speak again about the conclusions and future perspectives, and of course the open discussion with public, with people here in the room. The next presentation is about the multi-modeling. Janet Perko, he's going for the Belgian Nuclear Research Center. He's going to combine in one presentation all the results from the modeling. And I want to remark that it's really important in InnovaConcrete project, the relationship between modelers and people and experimental scientific. Because, for example, in the case of University of Cádiz, we had the products previous to the starting point of InnovaConcrete, but we used the modeling results, the multi-scale modeling results, to optimize our products, especially in the case of the penetration depth. We have some problems because we have several products developed in our lab, and they have problems in concrete, especially in some concrete, because the low porosity of the concrete it was a problem to the penetration, the impregnation treatments, and the penetration is a key parameter to guarantee to have a good durability. And we're working together with Janeth and the group from Janeth, and we promote a different composition in our product, promoting a good penetration of our hydrophobic, super hydrophobic material. And this is the time from Janeth. Thank you.
Good morning. So my talk will be about modeling. Actually, there should be 2 talks, but unfortunately the first speaker and the work package leader could not come because of the circumstances. So I made a hybrid presentation of the both, so you get 1 talk for the price of 2. And I would begin actually where Dia finished, because she made very good presentation about how different the concretes are. So each concrete is different in terms of all parameters, of the chemical parameters, chemical structure, mechanical parameters, pore structure, and one typical parameter that was important here in this project was this pore size distribution. So each concrete would have different curves. You see the curve there on the left side or your right side, where you have number of pores versus the pore size, and these pores go from nanoscale to actually in microstructure to millimeter scale, because we have the microfracture and so on. Each material would have different curve. In this case, this curve shows, okay, we have relatively homogeneous material with 1 pore size, with a large number of 1 pore size. But not only that we have a lot of different materials, these materials also experience change in time. This is because they are in chemical disequilibrium with environment. So whenever you are in disequilibrium, you have the chemical reactions in the concrete, and so you have the ingress of water, of moisture, you have ingress of CO2, you have ingress of other species, and what happens with time is that you change the structure. And in the worst case, if you wait too long, this change in structure shows visibly on the macro scale and as a damage. As you see there on the picture, this could be in form of cracks, it can be in form of delamination, but it also changes the pore size distribution. So this curve becomes different. Typically, let's say with some dissolution processes, you will dissolve the small pores, and so the number of large pores will increase and the number of small pores will decrease. So even the same material, the same concrete, the same initial composition would result then in different pore size distribution after time. Now imagine the user which wants to use this, the product, the impregnation product. He knows that, okay, you want to protect the concrete against the processes from the environment because of this disequilibrium, so you want to retard this. But okay, these products also produce the CSH gel, so one of the phases in the concrete, and in this way they protect the concrete structure. And we know that the deeper it is, the more durable it is. And we also know, so this man here knows that the process of getting it deeper, so the penetration of this product is by suction processes, because we deal typically in concrete in partially saturated media, so we have the process of suction. If we look at the physical processes behind, they typically depend on at least on 5 parameters. So we have density, we have viscosity, we have surface tension, contact angle, and also there is gelation time. The thing is that all these processes, or the properties, the physical properties, they change with time because the product changes with time. We have the reaction from the fluid, and then we continue to some solid, to some gel state. But the user doesn't care about this, of course. What he does care is, okay, how should I mix my product? Because the product is mixed with different components. In which way I should mix the product so that I get the correct properties, so that I get the deeper, the penetration depth, the maximum or optimal penetration depth. Of course, what you do is, what you need to do is, you need to take experiments. And typically so the experiments are for each mixtures. What you see in the bottom spheres are actually experiments at different ratios for 3 components, in this case only, water, you have catalyst, and you have precursor. And typically you have to do experiments in several of these mixtures. You make different mixtures, and you measure then the properties, the physical properties of the impregnation product, and also then you measure the penetration depth. The problem is that here we only show the 3 components, but normally there are more. So, but visually you can only present 3 very nicely. And the problem is that with more components, the more experiments you need. And in concrete world, the more experiments means a lot of additional time. And if we apply, if we look from the point of view of predictability of these experiments, so we can use the same type of models as they are used in machine learning, they show that the variance or prediction capability of these experiments in only that points that I showed, in only that mixture, it's good only in that points, which you see with the blue color, so the small variance. But in between you have a lot of empty space with no information. So what you have is a big variance. So what you want to do is to get additional experiments in the best possible points, so that you get, for all these 5 physical parameters, the best predictability. And we did this, and we tested it, and with only, here in this case, 12 additional experiments, we could make much better predictability of the experiments, let's say, of the data. Now, if we said that we do experiments to know, I wrote here that then we should model to understand. I don't mean that you don't understand if you do experiments, but unless you cannot build a model, you are not sure that you understand. Typical example, the COVID situation. Now we have millions of experiments, and nobody knows when the next one will be. So this is, once we will be able to build a model, we could predict this. So we went and try to build a model that simulates the penetration depth. What we needed as an input were, of course, experiments in some of these experimental points. And those experiments were made by Rafael and from University of Cadiz. In parallel, we also did the modeling part to predict those physical parameters of consolidant. And this has been done, the work from Technalia, from Achu. the problem here is the measurement of the physical parameter. The problematic thing is that, like I said, the properties change in time. So if you can model this, it is much easier to then for the next mixtures to predict what kind of evolution it will be. On the other hand, what we need is the pore size distribution, because the material defines how deep you will penetrate. And also this, so we had the experimental part, and we got the experimental data from Torroja Institute. And on the other hand, we also did our modeling part, starting by microstructure. So this is typically what you see. These cubes are of 100 micrometers. So this is the cement paste, and it's this is the virtual microstructure. They did it in the University of Darmstadt. Did the modeling of mechanical degradation. From all of this, you can assemble the information also of change of pore size distribution. At the end, what you do, you again do the experiments on the penetration depth of this product, and also you compare these experiments with what we get as a result from the model. And if they fit, I mean, if you can, from the random experiments that you do also for validation, if you see that they work, then you know that you didn't miss some important process. That's the point in the whole modeling and understanding of the physical processes. Now, when we have the model, this is the experiments that we had for different physical parameters, we can have the combination of any of mixtures of this water catalyst and precursor, which is shown at the top with these spheres. So each of these spheres represents one mixture of water catalyst and precursor. In each of these spheres, we get the parameters of density, viscosity, surface tension, time, and also the contact angle. So we put this in the model of the penetration depth, and then we calculate the penetration depth. So what is the result of this? What can we do with this? We can optimize the product. First of all, we can have two materials. We can have different materials, as we said, and for example, I showed the left is the material which is intact, which is new material, like you asked before. So this is the fresh concrete with fine pore structure, a lot of fine pores, and you can make the mixture. So all these spheres are again on different mixtures, and the size of the spheres is how deep it will penetrate. So you can choose. You can see which mixture would make this penetration depth maximized. You can have degraded material on the right, and you see that it would be different. This mixture of components that would make a maximization of this penetration depth. But you can have additional thing that you can get from this model. You can put additional limitations to it. In this case, we said, okay, what if somebody requires that we have fast reaction time, or the gelation time will be 12 or 6 hours. So you need to add more precursor, and here you can get which type of mixture would give you the product that gelates in this time, and that would be that would give maximal penetration depth. It's very easy to include other parameters like color, hydrophobicity, so you can choose and you can weight all these parameters, what is important for you, and you can choose which mixture then would be the most optimal. So this is what I had. So at the end, just want to point out where these models can help to improve impregnation products. I think I made this point. So it's first of all that we understand the process, because only then we can optimize, and then we can optimize, and with this we save time also with minimizing the number of experiments, for example, and to make the process of selection much faster, and at the end this saves also money. So that's all for me. Thank you.
Interesting talk, and thank you. And next speaker now is okay. Sorry, Werner. It's your turn.
Eddie, you know, I like very much your approach. I would like to have it by myself in the laboratory. I hope this will happen on Monday when I give the lectures to the students. So I have to cry like I do on Monday also, Monday morning when I give them biochemistry. The question is, you make it in a wonderful way to mimic and to analyze the physical characteristics of, let's say, corrosion. But then we come to the level of chemical changes, changes. Let's say to go to the metal, which is inside of the concrete. This is already, I think, very challenging, because then you have to go to the nanoscale. But if you come to the, so you can measure the different, let's say, iron elements, or whatever, the minerals. But then you come even to the biochemical level, that you are settling on the, for instance, metal material, bacteria, which are iron bacteria, this dissolves also. And then you have to go to the Angstrom level, right?
Yeah, that's correct. And it's very challenging having this multi-scale, especially when you go very, very low into the scales, because then you're really at angstrom level, and taking the conclusions that it's not necessarily the number, it's not necessarily what you usually see, okay, here we have one scale and we get upscaled parameter and so on. There are concepts that you learn, and this is something that is not something that you can really hold in your hand. So it is going there into this scale and trying to understand what the results are, and then trying to get these concepts upscaled. The problem with biological combination, chemical, biological, is that we don't have a lot of databases for this. So for chemistry, we have the chemical databases. These are quite well known also for concrete. But combination with biological, we need to make. Yeah. Yes. Yes. Okay.
And no more questions. Okay, so now is the time for Noni Maravelaki. We are going to change the order because she needs to travel now. She's my colleague, my friend Noni, Professor Maravelaki from University of Crete. She's going to present the result regarding to one of the two impregnation treatments. We produce two different impregnation treatments in InnovaConcrete. The reason is we have different kinds of materials, different kinds of concrete or cementitious materials, and that's the reason we need different solutions. And Noni is going to present the solution of the University of Crete. Okay, thank you, Noni. This is your turn.
Good morning, everyone. Thank you very much, Maria, for this introduction. I'm very glad to be here and to be part of this very great InnovaConcrete consortium. And I'm going to present a consolidant hydrophobic product with affinity to concrete structure. The outline of my presentation is, first I would like to explain the inspiration for the design of this conservation material, which strengthens and protects concrete and other carbonaceous substrates. Then I'm going to present the characterization of this nanocomposite, the performance evaluation, other case studies, and my conclusions. First, let me say some consolidance criteria which are common, but it is always very useful to recall them. A consolidant should strengthen and protect the construction material for the whole lifetime, should have a satisfactory penetration depth, should efficiently chemically bond it to the substrate, should not present cracks during shrinkage and drying, should have a physicochemical and mechanical compatibility between the non-decayed and the consolidated substrate, should avoid the accumulation on the surface and the color alteration, should be eco-friendly and with a low concentration of volatile organic compounds, should be friendly and convenient for the users, and should have an increased lifetime. The Took strategy for the design of these consolidants derives from observations on monuments of very well preserved layers, the so-called patina or salvatura layers, which contain silica, calcium oxalate, and calcium phosphate. These particular layers show properties such as low solubility in acids and bases, cohesion to calcareous substrates, protection from salt action, the stone porosity remain agents, protect from pollutants, and allow the water escape. Therefore, we have tried to incorporate these particular components into a consolidant, and you may see here how the calcium oxalate could be combined very well with the crystals of the calcite, and they form a very compatible material. And at the same time, the calcium oxalate shows a very low solubility, is thermodynamically stable, and is very compatible to the calcite, as I said before. Therefore, we have incorporated into the TEOS matrix, which is the tetraethoxysilan, the nanoparticles of calcium oxalate, along with another component, which is a stable siloxane, the polydimethyl siloxane, and it derived a very monolithic gel with no cracking, with a nano roughness on the surface. When this material applied to the cement, you may see here that the cement surface is the material is compatible with the cement surface as it covers the CSI faces, but not occluding the pores of the cement surface, and at the same time it provides hydro-repellents to the surface. This is the one-pot synthesis of this material, a simple synthesis, and presenting here a brief conclusion of this product properties, we may say that is a non-toxic strengthening and protective agent, which was synthesized in a one-pot procedure via the salt gel method, incorporated nanoparticles of amorphous calcium oxalate monohydrate in TEOS. And these nanocomb particles provide the chemical affinity through an electrostatic interaction mechanism between the nanocomposite and the carbonate fragments, which frequently occur as aggregates in concrete. And at the same time, the main matrix of FXC shows a chemical affinity to the CSH phases of concrete. The optimized product requires a lower amount of isopropanol and an increased amount of water, and the water repellency properties were improved by introducing in the nanostructure of this composite the polydimethyl siloxane, which is a stable siloxane frequently used. Here you may see that through the SEM and the microscopic images, there is an absence of cracking, there is a micro roughness on the surface, and in the characterization of the sample through the TEM, we may see that there are the silica spheres with a uniformity and a shape and a hollow shape. This shape was maintained, and then during the analysis inside of these spheres, we may found the nano calcium oxalate structure, as you may see from the results of the despacing here in the images on the right. The characterization of the infrared analysis shows that an ongoing hydrolysis of TEOS is achieved, given that the peak of the ethanol at 880 centimeter minus 1 was decreased from the salt to the xerogel, and the infrared spectrum of the xerogel shows that an incorporation of polydimethyl siloxane along with the formation of comb was achieved from the characteristics bands of PDMS and nanocalcium oxalate, which are evident. You may see here the characteristic bands of nanocalcium oxalate, and with the blue bands is indicated the characteristics bands of the polydimethyl siloxane. Then the bronze band that is presented here in 1050 is indicative of the antisymmetrical stretching vibrations of the silicon, oxygen, and silicon bonds. Then this product was very well combined with the anti-corrosion inhibitors provided by GNR, and when it was integrated in the LDH with the glutamine, as well as with the P-aminobenzoic and mesoporous nanosilica particles, the gels that were achieved were without cracks, and the final product shows a penetration depth and an anti-corrosive ability in the experiments that were done during these experimentations. The validation of the effects on the cement mortar took into consideration the possibilities of the various kind of application. You may see here that the application with the spray of the surface, of spraying the product on the surface, is an easy application, but we obtain a larger penetration depth, but at the same time we have a large consumption of the quantity of the product, and sometimes this is an uncontrolled application on small surfaces. However, applying the product by brushing there is a control application. We have an optimum consumption of the product, but is a time-consuming method concerning large application areas, and sometimes the product is not absorbed under pressure. In these images, you may see how the product behaves on the surface before and after application in sound and freeze-dose the aged samples. It is very evident here that after treatment we have a ceiling of cracking in both cases, and this slight whitening that was observed on the surface after the first week of application was disappeared, and this observation can be also confirmed by the colorimetric measurements. The application of the product is an important step in the whole process, and of course requires specialized personnel in order to obtain the best results from the product. Another example for this issue is some images that we have obtained here with the first application, the first layer application of the product, in which you may see on the left image that we have some crackings, but when then we applied extra isopropanol, then the cracking was disappeared, and the color difference delta epsilon lies within the acceptable limits. Regarding the validation of the penetration depth of the effect C on the cement mortar samples, we have obtained different results according to the pore size distribution and the porosity of the substrate. When we have large size pores, the penetration depth is up to 20 millimeters, as it was observed by the infrared spectra of the product, and you may see here in the plots, in the infrared plots. But when the samples show low size pores, like the carbonated samples, then we have a penetration depth up to 3 millimeters. The validation of the product and the microstructure on the cement treated samples shows that we have a deposition of the effect C on the faces of CSH, and the product is concentrated at the boundaries of the grains without blocking the pores, and we have observed that the product filled some microcracks of the untreated products, of the untreated samples. Regarding the physical properties, we have seen that an improvement of the water repellency was achieved in all the methods that we have been used for measuring this water repellency, and we have seen a reduction in the water absorption by capillary, in the sponge test measurements, in the cast pipe test, and in the contact angle measurements. In the mechanical properties, particularly in the calculation of the dynamic modulus of elasticities through the UPV measurements, both to cement samples and the mock-up samples, we have seen that an increase was achieved after treatment, but this increase was a slight increase and is totally due to the low penetration depth of this product. Indeed, these structures are very dense structures, and it's difficult to have a great variation in the UPV measurements after the application of the product. In those images, you may appreciate the water repellency ability of the product. Here we have the water repellence in treated samples of concrete and stones, and here in the untreated, in which the absorption of the material is evident. And the same here in a concrete treated, and then in the untreated part in which the water was absorbed. The product was also applied on other cultural heritage monuments. For example, here you may see a Minoan palace of Komos in the south part of Crete, in which there were soil mortars, and these soil mortars were treated with this product. And what we have observed after the treatment is that the biodecay was disappeared. And here you may see in these images how is evident this disappearance of the biological decay after the application of the product. And also the product was applied to the sandstone in which the cohesion of the surface was increased, and there was no color alteration. And it was also applied in the Mycenaean floor and consolidated this floor. During the Innovation Radar Prize in 2020, the product Surfapore FX was among the other finalists and is categorized as second in its section. And my conclusions are that the principal components of patina were embedded into a colloidal solution of low viscosity in order to ensure a penetration depth. These nanocomposite functions bridge between the carbonaceous aggregates of concrete and binder. The residual non-toxic raw compounds from the nanocalcium oxalate synthesis were used as catalyst for the salt gel process. Then the nanocalcium oxalate was incorporated into trials, providing these crack-free materials which performs effectively as a consolidant. The performance of the consolidant is related to the application type. The penetration depth of this product is up to 2 centimeters and has affinity both to carbonates and siliceous substrates, and the hydrophobic properties of all the samples treated with product were improved. These are the publications. We have collaborated with Mirtek, TUC, Nanofos, and Toroja Institute, and we have organized the second meeting in Chania. And thank you very much for your attention for me and my team.
Thank you very much. Thank you very much.
Do you have any question, Werner? Yes? No? Okay. 2 questions, yes. Okay.
It's working. Noni, we as a biochemist would say you have intelligent biomaterial. Question is, you have 2 principles in your material. You have the TIOS, which is going to, let's say, initiate the silicification process. And then you have the oxalate, which is slowing down the maturation process in the carbonate cycle. Question is now, how can you control the pH? Because both of the reactions are pH dependent. And how can you avoid, like in Heraklion, the dissolution of the calcium carbonate?
Yes, the solution of this calcium carbonate was controlled because when we put into the final mixture the calcium hydroxide and the oxalic acid, they were before interacted and produced the nanocalcium oxalate. Therefore, the pH remain the pH that we have in the sol gel process. I mean, very near to 5.56, not dangerous for the calcium carbonate, because we have modified the synthesis and controlled the pH in such a way to not dissolve the calcium carbonate.
Basically, the TOS reaction starts at pH 3. For the TOS reaction, one has to go down to the pH 3. Perhaps in your case, it's very good. It slows down, it's a slow process.
Yes, the TOS reaction sometimes goes to the acids when you use acids, but sometimes you can also use base in order to have the TOS hydrolysis. So in our case, we have controlled that in order to have the appropriate pH, both for the hydrolysis of TOS and at the same part not to damage the substrate of calcium carbonate. And we have controlled that a lot of time by using even powders of calcium carbonate and to see if they react with the product. This is the first step that we have tested. Thank you.
Thank you, Noni, for your answer. Thank you for your question. And now it's for Evelyn. Yes? The microphone, please.
Okay, I have a question because you did lots of different tests on the resistance of products to different form of degradation. So you listed freeze, water, and so on. But I was wondering, did you do the test as well to resistance to heat and sunlight, which I guess in Crete is very intense? And if you did, there was no impact, or you didn't do? Because it's a chemical product, so it can react to heat and sunlight as well.
No, you mean to the heat, to see to the heat.
To the heat, to the temperature.
To the temperature. No, I don't have a particular test for the for the heat, but I have the test of the DTA measurement, which the thermal degradation of the product, which is a method that shows the stability of the product even in high temperatures up to 800. And we have seen that the product starts to lose weight after the 150 degrees. Which is the degradation of the calcium oxalate. This is the first, and then for the organic part. This is only a test that correlates the thermal degradation in the product. Regarding the real application outside, and given that in Crete we have some very high temperatures, I can say that after 2 years of application, I haven't seen any change on the surface on the cases that we have applied the product. But another particular test, for example, with thermal camera and so on, I don't test it.
Actually, we did. This kind of test was combined with the high humidity. So after the application of both impregnation treatments, the one developed by UCA and the one developed by Noni, one of the tests, it was to submit these mortar samples treated with these two products to wet and dry cycles that consist in to immerse the mortar in water, and after for 12 hours, and after that to heat at 120 Celsius degrees. And we repeated this test for more than, I cannot remember, it was for 80 days or something like that. And after that, we test again the properties of the mortar. And again, we observed that the mortars treated with both these products behaves much more better than the one our reference that were not treated at all.
Okay, thank you, Nes, thank you. And thank you, Noni, for your very nice talk. And I would like to remark that one of the objectives of the target of InnovaConcrete was to bring the solutions to the market, from the lab to the market. And this is a success solution because one of the products is now in the market. And this is not the TRL that is 6, I think, in the proposal. We have a very high TRL because we are with a product in the market. And another success of the product was the radar prize, and thank you and congratulations for your work in the project. Thank you, Noni. Thank you very much.
Thank you, Mary.
And now is the time for the products from University of Cádiz. We prepared another impregnation treatment. It's a completely different solution. It's a different solution. We look for the CSA gel creation, and additionally, we add to the same material another component, organic components, and we promote a roughness in the product to produce super hydrophobic materials with repellent properties. In the same way, we prepare this product by the chemical route. And next, another partner of the Gianfranco from Yombag, he's going to present the solution by using the UCA product, but without the organic component. And in this case, the nano-roughness is produced by the plasma treatment. Two different solutions to achieve the same performance, superhydrophobicity and repellence. But now is the time of my colleague, Rafael Zarzuela, and Rafa is going to present impregnation treatment from University of Cádiz and superhydrophobic materials. Thank you, Rafa. And please, people from the traduction, they need that we remove the mask when I'm going to speak. I'm sorry because it's not in my case, but please remove the mask when you speak. Thank you.
For a second, I had to drink because I have the dry throat. Okay. Well, without further ado, I proceed with my presentation about the two families of products we have developed and optimized during the InnovaConcrete project at the University of Cadiz. As Maria has said, we were focusing on the products that can consolidate by generating CSH gel. Before proceeding directly with the products, I want to introduce some concepts in a very brief way, just so to put you in context. The first one I will just say because the previous speakers have already told you about all the problems that concrete make up. The only thing I want to remark here is that we have all these problems, and this is the reason why we need to develop different treatments. In our case, we are talking about surface treatments. Specifically, we develop impregnation treatments. They are meant to prevent these damages or compensate these effects when they are in their early stages. They are not for healing big cracks. Then you'll later hear another speakers talking about the products specifically for that, because we are talking with prevention and early healing of the damages. And what is the base of the products we have developed at the University of Cadiz? We start with the alkoxysilane-based products. These are very popular in cultural heritage, restoration, especially in stone. On concrete, they see some uses, but they are not really that popular. Also, you can also find it. And why they are used? Well, they have some advantages because you apply the product as a salt, which behaves like a liquid with a low viscosity. It can penetrate in the pores, and once in the pores, they polymerize in situ. You can apply in situ, and with environmental moisture, they generate a compact silica structure, which silica is chemically inert and normally have a good interaction with many minerals, especially silicates, feldspars, etc. And it also has a good mechanical properties. But what is the main problem that alkoxysilanes tends to display? The typical zero gel they form is a microporous material And in microporous material, when the solvent or the reaction byproducts evaporate, they generate a huge capillary pressure. This can lead to cracking of the aerogel structure, so that consolidant starts to lose efficiency. Or if the aerogel is flexible, it can collapse the pore structure. And in that case, what you have is that you block the pores and you don't have permeability and you have a plethora of problems in the treated materials. The strategy we developed at the University of Cádiz to compensate that is to add a surfactant to the synthesis that will direct the structure of the final aerogel. In this case, it forms a aerogel formed of regularly sized nanoparticles, and the gel, as a result of this, will have bigger pores and with a uniform pore size. And that way, we can lower that capillary pressure and also lower the internal tensions when the reaction byproducts or solvent are drying. The other concept we introduce, I'll be really brief, is about what is CSA gel. Right? The CSA gel is the main component, is the most abundant phase in the hydrated cement phase, and is responsible of a great part of the engineering properties of cement. And what we are aiming to is to have a product that can react with another hydration phase of cement, in this case mainly portlandite, and in the presence of the water, it can finally form a CSA gel that will have the same composition, so we are increasing the compatibility with cementitious materials. The other concept I want to say something about is what is a super hydrophobic surface, because sometimes there are some confusion. Well, with the super hydrophobic surface, we have combined different effects. On the one hand, with this we can prevent the absorption of water in the material, preventing water damage, but also we have repellence on the water surface. And this can be exploited to obtain surfaces with a good stain resistance. And also, we can get some interesting effects like self-cleaning effect under the rain. The rain is able to remove contaminants, dirt, or different kinds of stains. So, the requirements is just that we need of a super hydrophobic surfaces that we have a high contact angle, higher than 150 degrees, and low hysteresis. That is translated into that the water droplets or the water can easily slide or roll over the surface of the material. And in order to get this effect, we need to combine two factors. The first one is that we need a low surface energy. If we only have that, we get a hydrophobic surface where the water impregnates the roundness valleys, but it's thin. But anyways, it doesn't penetrate. But if we increase the micro or nano roundness, preferably both of them, we create what is called a Cassie-Buster state, where the air gets trapped between the solid and the water. And in this case, we are minimizing the contact area, and in fact, for this reason, we can have the water that easily slides over the surface. And now, having introduced you these concepts, I'll start to talk about the product, first the synthesis, and then some of the highlighted results. For the product, we use as a basis an ultrasound-assisted process, and the main components are the silica source. We use oligomerized theos, tetrahydroxyserine. In this case, it's cheaper, and also it allows us to have a faster reaction. And the reaction products are pretty much the same. And the surfactant we use has a double function. We use a basic catalyst, a long-chain amine, and it's at the same time the surfactant that controls the pore size, and also the one that catalyzes the reaction. Also, we need to add water because it participates in the reaction, and we use ultrasound because in order to have a homogeneous product, we need the energy provided by the ultrasound steering. So now, regarding what does the product do when it's in contact with the concrete? Well, first I'm going to show some results about when the product auto-condensates with ambient moisture. We have that it forms the typical aerogel structure with a nanoparticulate morphology. And if we analyze by nuclear magnetic resonance and other techniques, we see that it has a reticulated structure, which will be something like that. This is the typical silica ceruleal. But when we make the product polymerize, in the presence of portlandite, we have the totally different polymerization route. On the first hand, we see that the portlandite is depleted from the system, so the product is reacting. And also, if we analyze by nuclear magnetic resonance, we see that the structure is of linear chains, and the morphology of the reaction products is the typical shield-like structure of the calcium silica hydrate. In summary, we have this kind of structures, which is different from the reaction when it's not in contact with the portlandite. And also, if you put the product or make it polymerize in contact with the cement paste, we see similar reactions. The product is also able to polymerize, forming linear chains and consume portlandite. But joined to that, we also observe that the silica oligomer is able to break down and incorporate into the linear silica chains already existing in the CSH structure. So now, with respect to the application and evaluation, I'm going to give some results. I could give a million more, but I had to condensate everything here in this presentation. I highlight that the application we can apply by brushing or spraying. Normally for the laboratory, brushing is more practical, but we have performed the two of them and compared, and the results were pretty much the same in all cases. And this is an example of the structure and penetration of the product. We can see here at different depths that the product is able to increase the compaction of the mortar. In this case, image D corresponds to the untreated area, and we can see the effect is evident. And also the structure of the reaction products, you can see that they have the fiber-like and shell-like. All of them are consistent with the CSH gel structures. And also we can see that the product doesn't cause a significant color change, is invisible to the naked eye. And regarding the consolidated effect, we have a more compact structure, but this structure is coherent and is adhered to the substrate, and for that reason, we see that the surface has a higher resistance. I put the sample of the pickers hardness, and the bulk properties, in this case flexural and compressive strength, increase for the mortars. A little bit less for the carbonated because they are more compact and have a lower porosity, but we can still see some effects. And now for the super hydrophobic product, well, in fact, the multifunctional super hydrophobic and consolidant product, what we did is a modification of the synthesis. We, we incorporated two components to hydrophobic. The first one, polydimethyl siloxane, which gives a better effect on the surface, and the second is a monomeric alkylsilane. The reason we use this is related with the optimization using the results from modeling, because our first version have a low penetration, and we observed that with this component, we managed to change the physical properties of the salt in the way that the modeling predictions told us that would be better for the penetration. And in fact, it was true that this really improved this parameter without sacrificing the properties. And also, to create the nanoblandness that we need, we add to the product the silica nanoparticles that will stay on the surface and create those structures. So, here we can see some examples of the hydrophobic, the water repellent, and the self-cleaning effect. In this case, it's a dye in powder format, and we can see that the water has a minimal interaction with the surface. Also, we have the contact angles typically about 150 degrees and lower hysteresis, and the capillary absorption is decreased by, depending on the material, by over 70, 80, or 90%, depending on the case. And in this case, it's a combination of the hydrophobic effect and the decreasing porosity that I had shown you before. Similar results were observed with different methodologies, like the contact response test of the Karsten pipe that is not displayed here, but it's similar. And also, really important, we need the hydrophobic product. We have modified the formulation, but we need to verify that it is also able to form calcium silica hydrate. In our experiments, we showed that, in fact, it forms that morphologies in the presence of portlandite, and also it can create a more compact structure, as we see by the porosity measurements. Here I'm going to give an example of a durability test. In this case, it's a test of resistance to salts. We can see that it is really evident the difference between the untreated samples and the treated samples. You can see the damages, but also the aesthetical alterations in the color change. And in the internal damages, we see that the loss of ultrasound pulse velocity is minimal for the treated specimens. And these results are similar to the results we obtained with a benchmark commercial hydrophobic impregnation we use for the test. And now, to finish with, I'm going to give some brief overview of some of the results we have obtained on the mock-up concrete specimens. Similar conclusions. We can see the repellent effect, you can see in the video. We also get the high contact angle in pretty much all of the mock-up specimens, and the reductions in water absorption are in all cases above 75%. And also we can attest that the mechanical properties are improved by the Smith hammer and ultrasound pulse speed in all the mock-up specimens, with some difference. But we can see that the general trend is over there. And with this, I finish my presentation. If anyone has any questions, you can proceed.
Okay, thank you for the really good presentation. I have one question. Maybe it was not part of the project because you work with concrete. But I was wondering if you, by any chance, also did the check of interaction of product with other materials, like, let's say, bricks, asphalt, or stone, and if it improved impregnation, if you did any tests like this?
Well, with other materials, for example, with stone, we have the experience because the starting point of the synthesis route were consolidants that were designed for stones. We know, for example, for stone, with the silicate minerals, it can form covalent bonds because the silica, oxygen silica, we have verified that it forms. And also, with this synthesis route, we don't know the exact mechanisms, but we can see that when we put in contact with carbonates, there are some kind of interactions. We know that the catalyst, the amine, is involved in some way, but we have studied that. But for example, for asphalt, we haven't studied. I predict that it shouldn't have a big interaction with the binder because it's purely organic, but it's something that it should be tested. But in fact, our experience is mainly with stones.
I would like to remark regarding to the substrate that as we have a long experience with stone, we work with another materials as well. Now, in a new project from our group, funded by Spanish government, we are working with textiles in a similar approach, because now with the pandemic situation, we have a new research line regarding to the biomaterials and to produce coatings and to produce impregnation treatments in textiles, to produce repellents and also to prevent the organism ingress, like microorganisms, like bacteria or other materials. And it is working very well. It's not exactly the same approach, but it's with the same components. And I mean, I think the success of these salts, of this product, is just you can change the composition, or you can change the ratio of components, and you have solutions for different porosities, for different substrates. That's the point. Thank you. And now, Muller, okay.
Raphael, you allow me, because we have to train anyhow for the refereeing process in Brussels, this referees from the EU Commission will ask similar questions. So that's the reason why I'm doing this. Question is, when you apply your TIOS material on the surface of, let's say, of concrete, you have anything together with the TIOS. Do you embed it into PMMA or whatever? In other words, how is the surface where you put the TIOS material on? Is it very plain? Because this will affect the contact angle very much, I believe.
You are asking me about how does affect the surface profile of the properties on the
Yeah.
Well, I can say that, well, for example, for the impregnation treatment for the consolidating effect, it shouldn't be too relevant in the case of the consolidant properties, because the component is penetrating in the structure and the effect is in the down layers. Actually, if the surface is polished, we may have to check that because we can block the surface pores. But this is something that has to do with the surface finishing, and it would need to be analyzed in a case-by-case basis. But now, in the case of the super hydrophobic treatments, it can actually affect because we have the nano roughness caused by promoted by the nanoparticles, but also if the substrate is already rough, we have an additional micro roughness. And normally, rougher surface will improve the super hydrophobic effect or will improve the repellence. There may be some exceptions in in substrate with a macro roughness in the case that the particles are not able to form a more continuous layer. But this is for extreme cases. And if the surface is really flat, the particles are covering the part of creating the nano roughness. But in fact, if you have a micro roughness, normally you achieve the best results.
Thank you. So thank you. Just a short question, whether you have an idea of the duration of the effect, so under open air conditions and normal, and whether it is somehow robust enough to tackle the problem with different, let's say, reinforced concrete usually adopted. So if you have to adjust to the specific concrete, or it's somehow general purpose somehow, to a certain extent.
Yes, I'm going to ask, oh sorry, to the first question regarding to durability and regarding to the real validations. I want to say that we have a long experience, my group, in the laboratory for 20 years ago working in this kind of materials, and for us it's really important, this project, the InnovaConcrete project, because we have the opportunity to work with people working in the real situation. In this case, we work with different companies, with different architects, engineers. Especially, I want to remark the work from Ines in Kaunas and in Warsaw with our products. Yesterday, in my presentation, in my overview about the project, I presented a very, very nice movie, very nice video regarding to the effect of the super hydrophobic materials in Kaunas after 18 months. I think it's a very, very significant question, this question, because you have another solutions like InnovaConcrete solution, like a super hydrophobic product proposed from UCA, from University of Cadiz, in the market. I am sure you know, because you have the typical nanoparticles, and you apply nanoparticles with hydrophobic effects, and they are producing the same roughness than our products in the surface of the concrete, of the stone, and you have very the similar approach, the similar effect. But in InnovaConcrete product, this product has a very significant difference with another product because we include nanoparticles and in a soil, in a starching soil. And that's this very, very important characteristic of the product because this product, the soil, the liquid, is going down of the pores, of the cracks, of the concrete, of the stone, and this is producing the chemical bonds, like Rafael explained before, with the material. And you have the nanoparticles on the surface, but it's not a coating. This is the problem for all the super hydrophobic products in the market. They are coatings, and they have very nice effect, but after 1 month, 1 year, you don't have the same effect. And the opportunity for us, the opportunity with this European Commission project, the European Commission funded this project, is that we can work with people from working in the real situation, and we can test the product in real situation. And another point, what very, very important for my group, is to work with Zika company, because all these soils, they were sent to the Zika company, and they are testing. They have very nice results as well, and they are testing in the conditions of industry conditions. This is completely different to the laboratory conditions. And I want also to remark that the main significance of our products and the difference with the products in the market is just the durability, because it's we have a impregnation treatment. The treatment is going down into the substrate, and the another one, that is the creation of the CSA gel. We have a lot of products in the market, but I am not familiar with any product that they are optimizing the product according to the creation of the CSA gel. I don't understand this, because this is very important for concrete, because you are producing the main component of concrete. And I want also to say thank you to people from Torroja, because we work together, we join efforts to study the production of CSA gel in the mortar and in the concrete. And if we have a success production. In this case, it also was very important the role of Tecnalia, because they prepare the modeling regarding what's the optimized components, optimized ratio of the components to produce the CSA gel. And I think this is the success of InnovaConcrete in this case, the working together of these different laboratories, simulation, experimental laboratory in NUCA, in University of Cádiz, INES, and other validators in the in-situ validation, and especially Zika company. And sorry, because it's a long answer, but I think you have another question about Rafael, because I don't remember. You have the second question on the range. Yeah, I know. So the results from InnovaConcrete, they are regarding to complete different situation of monuments in real situation, and with different concretes. We have these results now, and also, of course, the results from mock-up. But I think in the future, we need to work together to join efforts to apply in another situations, and especially in some materials, because the sustainability, because to produce to prevent the effect of the weather condition is very important. That I think this is also a second step in InnovaConcrete project. Thank you.
Sorry,
Yeah.
just I wanted to comment our experience with their product. We applied the product in 2 case studies, one in Warsaw and another one in Kaunas. And the first thing related with the durability, just mentioned that we experienced incredible results after 18 months. It's still, you will see afterwards, I will try presenting it. Extraordinary results after 18 months. And I want to highlight that that product that was applied and that was tested for 18 months is the product that wasn't optimized yet. So by the optimization, they could improve the penetration of the product. So I believe that the new product that was applied a bit after that, and that still under monitoring, and that didn't go so long, it will even behave much better. So in principle, I can tell you that it lasts quite a bit. And in relation with the compatibility with different materials, I think with different type of concrete, we undertook also certain core samples of the product, and they were analyzed at the laboratory, and no chemical incompatibilities were found. It's true that, well, we have maybe a sample of case studies that is not huge, because we have 7, but well, it's already a small sample that maybe we need to still, they need to still keep researching on it, but it's a promising start.
David, for your talk. And okay, so now is the time for another product developed in InnovaConcrete project. This is the time for Federico Olivieri. He works in collaboration with Gabriela Di Carlo and other research from CNR to produce smart corrosion inhibitors. The target of the InnovaConcrete product was to produce this container, this smart container for corrosion inhibitors, and the next step was upload these smart corrosion inhibitors in the impregnation treatments previously described, in the impregnation treatment from University of Crete, and also in the impregnation treatment from University of Cádiz. And Federico is going to present the results obtained in this part of the project. Okay, your time.
Hello everybody. So I'll present you these multifunctional products containing smart corrosion inhibitors. As you know, in the InnovaConcrete project, the goal was to develop a new solution for preserve of concrete-based structures, searching to avoid time-consuming and exploited dedicated personnel, to avoid dedicated personal and working place logistics. So one of the solutions consists of the use of smart coatings, which are able to release on-demand corrosion inhibitors that will be able to allow efficiency and durable one-step treatments. In particular, in my activity, in my Institute of CNR, we focused our attention on one kind of nanocarriers, mesoporous silica nanoparticle, and in particular on 2 kinds of corrosion inhibitors, namely benzotriazole and benzoic acid. After me, Gabriella will talking about the other kind of nanocarriers, the layer double hydroxides-based material LDH. The particles that we obtained were synthesized with an high yields and high throughput synthesis. We were able to perform a synthesis with 98% of yield, and we following 2 different approaches. In the first one, the corrosion inhibitor was loaded physically into the mesopores, so the mesoporosity was exploited to nanocarrier in the real sense of the word. And in a second approach, we functionalized the starting nanoparticle with amino groups in order to chemically graft the corrosion inhibitors, in this case the benzoyl chloride. These kind of nanoparticles were previously characterized in terms of morphological properties and of surface area. In particular, we obtained a good surface area properties. The BAT was calculated around 600 square meter per gram. and the dimension, the medial dimension of the particle, the nanoparticle, was around 90 and 100 diameters, nanometers. The first approach, we developed BTA, benzotriazole metal complex, in order to cap the corrosion inhibitor previously loaded into the mesopores, so the benzotriazole. This complex is insoluble in neutral conditions and became soluble when increasing and decreasing the pH. Since corrosion phenomena are triggered by pH variation, we can obtain a solution that releases the BTA included into the mesopores with increasing and decreasing pH. So we performed and studied the release kinetics, and we saw that, as you can see, in very high and low pH, we have a very fast release, and while pH is near from the neutrality, we have stopped the release. This kind of nanoparticles were tested with embedded in acrylic coatings and tested on bronze substrates. We can see that in a traditional coating with BTA, free BTA, substrate were really damaged, and instead we have better protection in using our nanoparticles. In a second moment, we develop a new metal BTA complex based on silver ions that is also insoluble in neutral pH and soluble in acid and alkaline environment. But here we have two further advantages. The first one, we have a white coloration of our nanoparticles, so the complex BTA-Ag does not alter the starting MSN coloration. And in a second advantage consisted of the capability of capture of ions, chlorine ions, from the Ag, the silver ions. Since chlorine ions are a very aggressive ions for corrosion pits, this is a great further advantage in our system. We tested our system also on iron rebars, and we exposed our sample to acid and alkaline condition, and we can see that our system made embedding our nanoparticle in polymer coating present the best performance to corrosion protection. In a second approach, we functionalized the starting MSN with amino groups in order to graft benzoyl chloride. The idea was based on the same concept, so a system that was stable at neutral pH and unstable, varying the pH. In this case, from benzoyl chloride, we triggered the release of benzoic acid, which is a corrosion inhibitor. Also in this case, we test the release kinetics, and these kind of nanoparticles were sent to the partner of this project, to the embedding in alkoxysilane and calcium oxalate consolidants for in-situ application. And now, this was the kind of nanoparticle. And now Gabriella will continue the presentation.
Thanks, Federico. Good morning. In the second part of the presentation, I will talk about another class of nanocarriers that we used in order to protect the embedded rebars from corrosion and to obtain a long-term protection, because the idea was to confine the inhibitors inside the nanocarriers, which are able to release the protective molecules only in the presence of external stimuli. So we compared two different classes of nanocarriers, in particular silica nanoparticles functionalized with an inhibitor which was grafted on their surface, and the layered double hydroxide, which are functionalized with an inhibitor intercalated into the layered structure. In this slide, we compared the two classes of nanocarriers functionalized with the same molecules. And we observed that a very high loading was obtained by using the second class of nanocarriers. We performed the release test in simulated concrete pore solutions in order to evaluate their behavior in an environment which is very similar to the one observed inside the concrete porosity. And the results showed that in the case of silica nanoparticles, the inhibitor is released depending on the pH of the solution, so we can obtain pH stimuli responsive systems. If we look at the release test performed by using a layered double hydroxide, in this case we compare the release at neutral pH, at basic pH, and also in the presence of chloride ions, and the results show that the release of inhibitor only occur in the presence of chloride species, which are among the main degrading agents for steel rebars. So we decided, in order to improve the protective properties of these materials, we focused our attention on layered double hydroxide, and we compared different protective molecules by focusing the attention on the best performing materials. For example, here you can see the behavior of paraminobenzoic acid and glutamine compared with a reference substrate without any corrosion inhibitors. And the results confirm that the glutamine is the best performing inhibitor, and in addition, since it's an amino acid, is a green molecule, so we can also take into account environmental aspect. This inhibitor was used for the functionalization of layered double hydroxide nanocarriers, and the synthesis was optimized in order to obtain a loading up to the 30 weight%. And the scanning electron microscopy images show that we can obtain an hexagonal shape, which is typical for these materials. And the results of the other characterizations that we performed show that the inhibitor was successfully loaded inside these nanocarriers. So we studied the stimuli responsive properties of also for this material, and the results again confirm that the inhibitor release occurs only in the presence of chloride ions. And in addition, we have characterized the materials before and after the release test, and the results confirm that the layered double hydroxide structure is modified and that the inhibitor molecule is replaced by chloride ions. So it means that these nanocarriers can also act as a nanotrap for the chloride species. So the best performing materials were combined with the consolidant developed by the University of Cadiz and University of Crete. So we decided to use a combination of mesoporous silica nanoparticles and LDH nanoparticles in order to combine nanocarriers with a complementary release mechanism. And we optimized the dispersion of these nanocarriers in the consolidant, and the multifunctional product was applied on reinforced mortars prepared by the CSIC group in Madrid. And the surface of these specimens was characterized. The results showed that the consolidant properties are comparable with those of the consolidant without nanocarriers. And then we performed electrochemical measurement in order to evaluate the ability to protect the rebars from corrosion. And the results showed that the multifunctional properties show an enhanced protective action with respect to the with the two components which are not combined between them. So this optimized formulation was sent to the partners which are responsible for the monuments and was applied on different case studies like the tower and the angel in Torricella Peligna, the Torroja building in Madrid, and the railway station in Poland. The efficacy of these materials were monitored during time, and the results show that, for example, the corrosion inhibitors are able to delay the corrosion processes. For example, here we can see that if we compare the treated and untreated area, the corrosion rate slightly decreases in the presence of these multifunctional products, but the results will be discussed in the next section. And so, in conclusion, we during this project we have the possibility to optimize nanocarriers with a low tailored release of the protective molecules, and the multifunctional products was able to consolidate the surface and to protect from the rebars from corrosion. So, thank you.
Thank you very much. Thank you, Gabriela, for your very nice and Federico nice presentation and very promising materials in this case, in the case of the corrosion inhibitor. I don't know if you have any questions or not, but we have short time, and in this case, this is the time for the next presentation. And you can okay. The next presentation is from Monica Tonelli from University of Florence, from CSGI group. And in the case of Monica, in the case of the University of Florence, they develop another complete different solution. This is the case for cracks, for larger cracks in the monuments, in the buildings. They prepare a mortar. The innovation of the mortars is they include halocide nanotubes in the mortars. Next, in the next talk, we are going to another different solution in the same way from Torroja in this case. But now is the time of from University of Florence, and this is your time, Monica. Thank you.
Yep, it's working. Okay, good morning, everyone. So just let me spend just a few words to introduce CSGI. CSGI is the Center for Colloid and Surface Science. And as you can see here, we have many centers among Italy, and we are from the headquarters, which is at the University of Florence, where we are a lot of people. I put here only a few of all the co-workers that we have. And the reason why the expertise of CSGI well matched the InnovaConcrete project is because among the various topics that CSGI is involved in, we can see the conservation of cultural heritage, so the restoration and cleaning of pieces of arts, and the long history on the study of cement chemistry, in particular involving the hydration and the study of the microstructure of these materials. So CSGI was involved in the InnovaConcrete project in 3 different subtasks of 3 working packages. You can see in the first 2 which are the one I will talk about you in this speech, which involves the incorporation of those halloysite nanotubes that I'm going to introduce you in a moment into these cementitious formulations. And Among that, the preparation of repair micromortars and also pasties to be applied on very cracked surfaces to provide reparation to damaged building. Concerning the final working package 4, which CSGI was involved as well, this involves the definition of protocols for the removal of patinas, biofilm, and previous treatment to provide a proper cleaning, allowing the successful application of the following products on the buildings. Now, when we think of cement reinforcement, we can see it at very different scales. So probably all of you have heard about reinforced concrete. So we have these rebars that can be very long, even up to meters. But the literature is becoming more and more focused on the use of reinforcement even at a lower scale. So it has been already reported in the literature, for example, the use of glassy fibers or other similar fibers, let's say at the millimeter scale. But now we are starting to look at the micrometric and nanometric scale in order to provide those kind of reinforcement or additive properties also when using nanotubes. And when thinking of nanotubes, halloysite nanotubes seems ideal to be used in cementitious matrix because those halloysites that you can see here are a natural product, so they can be easily extracted from quarries, meaning that they are highly available and low cost. And as an additional bonus, they are non-toxic. As a matter of fact, they have been used also in some biological application. Since they share the same chemical composition with cements, displaying silanol and aluminol groups, they are perfectly compatible with our material where we are going to mix them. They display this 1D shape, this tubular morphology, typically ideal for reinforcing purposes, and they have this cavity, as you can see here, this empty cavity, which is called lumen, that allow us to entrap molecules. So what I'm trying to say, I'm trying to convince you that halloysites are very versatile, and it has been already reported that they can be used to reinforce mortars. As you can see here, we have some images showing you that those nanotubes are perfectly compatible and can be well mixed into our matrix. And as anticipated before, it is possible to entrap active molecules. So what we did here, it was starting with the loading of a protection molecules that would be released after all in the matrix to provide additional protection in our cement materials. And we started using a corrosion inhibitors, well-known corrosion inhibitors, benzotriazole, already presented by CNR in the previous presentation. First, we improved the loading procedure of halloysite, of course, and we found out that by improving this procedure, we were able to load a lot of active molecules. By applying different cycles of air and vacuum into saturated solution containing the molecules to be entrapped into our halloysites, and after these cycles, it was possible to entrap, as I said, a lot of benzotriazole into halloysite, which were then centrifugated, washed, and dried. So obtaining a dry powder of halloysite loaded with our benzotriazole. So it was possible to easily mix these loaded halloysites containing those active molecules that we have chosen directly with the cement powders to be eventually hydrated to prepare our paste or mortars. And we showed that a lot of benzotriazole was entrapped into halloysites, reaching up to 90% of the maximum capability, so quite a good entrapment. Now, moving to the preparation of those materials, the idea was to prepare cementitious based materials in our case. So not only to repair cracks and damages, but eventually also to provide a physical protection to the monument suffering from aging, and also to repair problem of delamination that are quite common in damaged monuments. So, and this allows us not only to repair the damage that already occurred, but also to improve our cementitious materials by providing this so-called this protection, thinking to the fact that concrete, as we already said today and yesterday as well, strongly the durability of this material strongly depends on the permeability of the surface, since many potentially harmful molecules can enter through the surface. To do that, we prepared our innovative formulation by using various additives. So, of course, cements and loaded alloysite, but also silica that allowed us to improve the attachment at the interface of our materials to the aged material that we are going to repair, and also a lot of additives, commercial additives in this case, to achieve an easy application, a good workability, and the proper viscosity and setting time. Also thanks to a close collaboration with the actual final restorers, expert restorers that are going to use it, that gave us some indication on how they wanted these materials to be for the application. So we find out the optimal condition to obtain a nice attachment thanks to the use of silica. As you can see here, you have an easy rupture at the interfacial, at the interface. And we evidence that the use of alloysite molecules loaded with those protective anti-corrosion inhibitors allowed for a slow release, so a releasing time of our corrosion inhibitors upon raining, for example. So the corrosion inhibitors can be released into the cementitious matrix when it is exposed to the external agents, so when it's needed actually. Moving the next step, we started to vary again the composition of our materials, so testing various materials and changing their amounts, and we have done a thorough laboratory validation in order to finely tune the property of our materials to address very specific problem that commonly happens in those kind of buildings. So we developed 3 different formulations, so cement-based formulation, to address the repair of those damages. In all cases, we paid our attention, especially checking that we achieved an adequate formation of the dense cementitious material, the CSH, which is the binder phase of cement, of course. We checked that we had this good adhesion, so that our coating, our repair material wouldn't preferably be spared at the interface among the old aged surface. We verified to have a proper workability and setting time to avoid shrinkage, and we confirmed that the active molecule, so the first case was benzotriazole, could be effectively carried out, entrapped into the alloysites, of course, and then slowly released in the final material. So the formulations that we prepared were those called CSGI formulation A, B, and C. The formulation A, as you can see the first picture, is a very fluid cement paste to be applied as a coating. So in this case, we are trying to solve the lamination problems. So obtaining a very fluid paste, this would be easily spreadable with a spatula from the final user. Then we have formulation B, which is a very viscous, again a cement paste, to be easily injected, and this can be used in very small cracks with a width up to 5 millimeters. So in this case, for example, even using a syringe, we can directly inject our viscous paste into our small crack in order to entirely fill our crack and close these cracks that would allow harmful molecules to enter in our materials. And then we have formulation C, the final one, which is a very plastic mortar, and this is the one that is being prepared in this video, just to see how we are doing it. And this is a very plastic mortar, so this is suggested not only for brick cracks, so up to 10 millimeters, but also it can be used as a repair mortar for small detachment, because being a very plastic mortar, so we included sand, of course, in this case, it's being very plastic and viscous, it allows to shape, as you can see now, as you will see in a second in the video, to shape its geometry very easily, so to repair those damages that we were looking for. So all the three formulations were applied in many case studies of the InnovaConcrete project, as you will hear later in the following presentation, and we achieved quite successful achievements, so that was nice. And I want to thank all my co-workers, of course, and all CSGI, all the InnovaConcrete partners for everything, for all these 4 years, and of course you for your attention.
We are the line. Maybe you have a short question now. Yes, and I want to say that now is the time for the coffee break. I think it's better we are going to have now the coffee break for 15 minutes, and next we finish with we have two speakers after. But Werner, if you have any question, please go ahead.
Monica, great presentation. Question is, your nanotubules should have a length approximately 1 micron in length and in the inner diameter of 15 nanometers. Let's say that is usually the size of this kind of nanotubules. The question is now, what do you put into? What is the inner diameter?
It's tens of nanometers, so 56.
Tens, as more than 10. More than 10 nanometers or below 10?
No, more.
So it is
50, 60, you can
50.
See the outer diameter, the inner
Is 50, that's correct, sure. But the inner?
The lumen, to the is around 15, the lumen.
Now to the question, what can you put into these tubules? Because 50 nanometers is not large.
No.
So you can put TEOs in it, but what else? You cannot put bicarbonate in it. You cannot make. So what do you put into your?
In the literature about the loading of alloysites with protective molecules and various molecules is very large. You can find a lot of additives that have been entrapped or also adsorbed onto the surface of those alloysites.
On the surface.
It depends. People are both entrapping molecules into the cavities or adsorbing molecules.
Right.
It depends, because since you have a different chemistry, I didn't stress on that. As you can see, you have aluminol and silanol on
that. That is a core structure. That is the core structure of the tubules.
It's like a rolled kaolin sheet. So you have a different chemistry in the lumen or outside. So different pH and different aluminol or silanol groups, meaning that you are potentially, if you do it correct, allowed to decide whether your molecules are going to be adsorbed on the external surface or entrapped in the internal surface.
Then you can call it, your material, like Gabriela's material, intelligent nanotubules.
Why not?
No, it's like this. Very great.
Maybe the coffee break.
Sure.
Thank you, Monica. Thank you. Sorry, another question from our modeling team.
Sorry for this, but I just wanted to ask Monica, when you start to release, for how long do you release whatever it's loaded in these tubes? This is the first question. The second question is, if you have mortar with larger, let's say that you have larger aggregates, would you find these nanotubes also in the interface between the aggregates and the paste? What is the distribution of this?
Is it, yeah. We studied the release of benzotriazole from those nanotubes, first of course in the simulated body solution and then in the cementitious matrix. And to do that, since to achieve the release you have to be in solution, we did some simulated rain tests, meaning that first we directly put our cementitious materials containing the loaded halloysite nanotubes into the solution to see if when water was present, the active were released from the matrix. And we verified that this happened in terms of tens of hours, but with a lot of water, okay? Then what we did, it was simulated a more realistic situation, so with the rain. What we did was, sorry, I don't know where to put the mask. So what we did was, we have our sample, we coat it with, let's say, formulation A containing the loaded halloysites, and then we simulated a very strong rain in an European central zone, looking for data on that, and we drop our, slowly release our water, simulating this rain on our sample. And we do it to simulate a rain for continuous rain for 1 week, 1 day, or 3 weeks, or 3 days. We did that. And then after all, we break our sample. We take pieces from the different parts of our sample. So from the top coating, where the coating with containing loaded halloysite was present, in the middle, and in the bottom. And we put these 3 pieces in a little amount of water for a lot of time to be sure that all benzotriazole that has exit from the halloysites and moved into our matrix was released into the solution. So we can do now the UV spectra of this solution because we choose molecules that could be studied by means of spectroscopy technique. So we look at that and we see how much benzotriazole is released from the halloysite and whether it has moved and be transported through our matrix. And we saw that this is possible, and not the benzotriazole were not entirely released after 3 weeks of high raining, so continuous rain for 3 weeks didn't allow for a total release, meaning that you still have some benzotriazole disposable to be released in the future, and the part that was released upon raining actually moved into the cementitious matrix because we could see that the center and the bottom parts contained those molecules. You have another question, and I'm not sure if I correctly answered to everything you asked me, so please.
Yes, for this part, yes, but I was also referring because let's say you can induce damage in this interfacial transition zone between aggregates, for example, and cement paste. And did you measure, let's say, where do you find these nanotubes if you mix it with some coarser aggregates?
We didn't check if the nanotubes would preferentially aggregate, if this is what you're thinking of, around, let's say, the rocks that would find in the concrete or not. This is something that should be for sure interesting. What we know that is that when mixing these nanotubes into the cementitious matrix, so in the cement paste or also in the one containing sand, it is homogeneously dispersed. So let me have a look at here. You can recognize, especially in the figure on the bottom on the right, those halloysites. And when you have aggregated halloysites, they are quite easy to recognize because if they preferentially aggregates, you can find very huge aggregates of these nanotubes. So it looks like they are well dispersed into the matrix, but we didn't check it in presence of huge rocks like in the concrete materials. Also because we focus our attention on the IBCM formulation, which are bases and mortar, so we didn't move on concrete. Thank you.
Thank you, Monica. Thank you. Sorry for the line, because we have a lot of questions today, very interesting questions. We are going to start again at 12 o'clock, and we have the last two talks regarding to this session. This was the starting of the session at 12 o'clock. Thank you, and we have now the coffee break. Thank you.
2009, después de haber pasado por ellas, me quedan dudas. En cualquier caso, felicitaciones por el hermoso patrimonio que tenéis y la enorme responsabilidad de cuidar. Bueno, el hormigón armado ha tenido la virtud de replantear a través de la materialidad, a través del cálculo y a través de la puesta en obra, la eterna relación que hay, todos sabemos, estrechísima, entre arquitectura y construcción. Quizá venga a cuento recoger una frase muy famosa
Okay, gracias. Hello again. We are going to start with the next part of this InnovaConcrete conference, and due to the delaying before the coffee break, we have a lot of questions, very nice, a very interesting question regarding to the materials. Thank you. We are going to finish with the two last presentations about materials and techniques. First, we have the presentation from Professor Müller from University of Maine. He's going to present a very, very promising, very innovative material. That's the name of the title of the talk is Biomimetic Self-Healing. And I want to say thank you very much to Professor Müller and to all the people working in University of Maine, because it was a pleasure to work with you, and I am really happy with the results, with very innovative and promising results to obtain in InnovaConcrete. This is your time, Werner. Thank you. You want to remove the mask for the leg, for the leg of the people in the technical. They need to remove the mask.
Okay. Yeah. Very good morning. Many, many thanks, Maria. I'm very happy that I'm here. On Monday, I have to give lectures to the students. And the advantage of a workshop and a seminar with the students is that I can look in the eyes, for instance, of Fernando, and I can find out if I was clear. If I'm not clear, Fernando, I become unhappy. So, to make a distinction between cement, concrete, and a biological material, you can see here. That is a tree, and this tree has some kind of a damage. And people thought they are smart, they put a concrete in it, and you see already what happened with time. It falls apart, the cracks become larger, and then finally they fall off. This means something must be different between this solid material, concrete, and and these biological materials, the tree. But first, I want to go to this. Everybody might know it, or this, if they get some kind of age of 90, 100, they need to think about implants. The present-day implants which you get in your body, because I'm working in the University Medical Center, that's the reason why I have this. So they put in a titanium hip. And this is similar like a concrete material. This has nothing in common with any kind of biological material. This is inert, has no ability to interact with the natural tissue. And even worse, and that is something what one of the previous corrosion presentations came, that even settlements of the bacteria can be here, and they make problems with time, and you get a re-inflammation again. In other words, you will never find interaction between a foreign material like concrete or titanium with a human or animal system. And here is the thing what we learned with the hydrophobic interaction. The biofouling process is nothing. This is basically what wonderful here with Rafa and with Maria said. We have a biofouling process going on the surface of the monument of concrete. But what we have at the beginning is that we have, for the biofouling, we need to have nanoparticles which are settling out extremely fast on even a nano hydrophobic surface, very fast. And if this happens, then it's over. So the bacteria can come, they can settle, they can make a biofilm, then they can start to make corrosions and dissolution of the concrete material. Then larger animals or plants can come and can settle on the surfaces of these previously superhydrophobic surfaces. Okay.
Sorry about that.
Yeah. And now we had this wonderful meeting in Greece, and there we saw that even very old monuments can survive, and you don't hardly see any cracks. So there must be a miracle in this kind of binder and concrete material. But what is a miracle? That was a task, and if we disclose the secret of this kind of, let's say, biological or whatever is called processes, then we can also fabricate a self-healing, a regenerating self-healing binder. And so we were thinking what to do, where we can find an animal. We must find an organism where we can use a blueprint, because nature is much better than humans when they are going to prepare for instance, concrete. So we were, some years back, we were thinking which kind of ancestors are the ancestors of the humans, of the animals. And we ping-ponged and found out that people were thinking that it was very easy just by diving in a cave in the wherever. I was diving in several places. We can resolve the question which kind of origin we have for our animal kingdom. And we did it. These were sponges. And these kind of sponges have some kind of a very wonderful skeleton. But because we are speaking with a cement on solid, crystalline, semi-crystalline, or even very hard amorphous materials. And this is a skeleton of a sponge. I was diving with a submarine in the depths of 400 meters, and we were collecting these kind of wonderful organisms. That is a glass sponge, looks like this. And that was a discovery that approximately 20 years ago, when we found that these kind of hard skeletons have a fiber inside, a proteinaceous fiber, let's say organic fiber. And we analyzed this fiber, and we found the first enzyme, which is going to synthesize polymorphic inorganic material. So Müller was a person who disclosed first the synthesis of organic materials from inorganic precursors, and we solved the question how inorganic precursors can become inorganic polymer, silica, by an enzyme. It's enzymatically driven. Everything what a biochemist is thinking, working in a biomedical center, is we have to look for enzymes. When we have the enzymes, then we can manipulate with the enzymes. So we found this kind of enzyme, silicatein, the first one in this row. And we could apply it. We published this also in Science. And then we came to this, that silicatein is a silica-forming enzyme. We can also use, by the way, theos. Theos is a substrate, more or less a natural substrate for silicatein, which can form this kind of very, very window class material which is present in the sponges. But unfortunately, silicatein was very difficult to prepare recombinantly, so we were thinking differently, and we are asking what are the enzymes in our skeletal system? You know that 20% of our skeleton is made of hydroxyapatite of calcium phosphate, and this is a crystal, and we were searching for the enzymes which are involved in the crystal formation in our body. So we came up, the first thing is always, and that is another dogma, if we want to understand anything in biology which is crystalline, we have to go to the amorphous state. So we always have to find what is the amorphous phase of, for instance, for calcium carbonate, that is amorphous calcium carbonate, and this is produced by the carbonic anhydrase. In our case, in our body, carbonic anhydrase 9. And then this, in the amorphous phase, only in the amorphous phase, we see anything which is converted in another phase, let's say in the amorphous calcium phosphate phase. So we need phosphate. So we were thinking, where is the phosphate coming from? And then we discovered that it is present in huge amount in the blood platelets. And then after being transformed to the amorphous calcium phosphate, we get a spontaneous crystallization, like in the cement. Spontaneous crystallization to calcium phosphate, to hydroxyapatite. So, now what about these rocks? I showed it also 2 days ago. These rocks, I was saying this, and I repeat it again today, we found it, and this was really gorgeous. In the Ronda area close to here, 100 kilometers close to here, that is a city which was built on a calcareous rock. And this calcareous rock is a huge bioreactor. You hardly see any cracks. No cracks. Everything is resealed. Only if it comes to that area where we get water, the water flow out, then we get holes. But usually here this is very solid. The houses are made of calcium carbonate, and the rocks are also made of calcium carbonate. What is a miracle that these kind of rocks are so stable and don't have any cracks? They surely get cracks. You have also earthquakes, but then they are resealed. How? And this is due to the fact that the bioreactors, the calcium carbonate rocks, carbonate rocks are full of bacteria, and the surface of the bacteria is decorated with 2 enzymes. We are always looking for enzymes. 2 enzymes, that is a carbonic anhydrase and the alkaline phosphatase. Coming first to the carbonic anhydrase. The usual way until, let's say, 6-7 years ago was, when you look in textbook, that we have CO2. To say it again, the karst region here in Andalusia is one of the largest CO2 scavenger in Spain. So this is very good for the green environment. So we get bicarbonate, and then bicarbonate is formed with the carbonic anhydrase, and then it is processed to the different crystalline stages to waterite, aragonite, and then finally calcite. But we have initially the enzymes, the amorphous, which is amorphous calcium phosphate. This is what we showed already before in the previous slide here. Now the question was, and this was really a difficult question, how we can stabilize the amorphous calcium carbonate phase. If you go to the literature, you will see that amorphous calcium carbonate is a very labile material which is very rapidly means within minutes, transformed to calcite, which is crystalline. And if it is in the crystalline stage, it will never heal, will never work as a self-healing material. So the challenge was to produce amorphous calcium carbonate in large amounts. Well, this is what we achieved. We used polyphosphate. This is just for Eddie. We can also model a little bit, but on the in the angstrom level, but not in the wonderful way like you. And it is very simple. It's a very, very interesting polymer. It is made of phosphate, and it is linked via high energy bonds. At room temperature, these bonds are stable, but if you remove one phosphate, you get a lot of metabolic energy out of it. And when you go to your body and you have somewhere a break of your bone, then you have accumulation of the enzyme which is splitting up the polymer, and also accumulation of polyphosphate. So polyphosphate is, let's say, the clue for any kind of regeneration process, and also in the cement, as I will show you later. Polyphosphate can be produced by a company which you have never heard before, that is Budenheim, close to Mainz. But when I tell you what they are producing baking powder, which is sold all over the world. And every lady in the United States or in Spain and in Germany knows baking powder, but this baking powder is coming from Mainz. And they are producing also a large amount of polyphosphate. It's not very expensive. We publish this thing in chemical reviews, by the way. It has twice as much impact factors than Nature. So, next. So, we had to focus on the alkaline phosphatase. Why do we need now the alkaline phosphatase? Because the amorphous, we found that the amorphous calcium carbonate and also the amorphous calcium phosphate, the amorphous phase is stabilized by polyphosphate. If we go to nature, if we go to our body, then you can see that we have huge amount of amorphous, when we have bone formation of amorphous calcium phosphate, and about 5 to 10% polyphosphate in it. And polyphosphate is a substrate for the alkaline phosphatase. If we let the alkaline phosphatase working, then after, let's say, half an hour, we have a transformation from the amorphous state to the crystalline state. That is basically the thing how our bone is formed. Now the question is, can we apply this also for cement? Polyphosphate is stable, it's alkaline and whatever, so it's non-toxic. You can apply it for wound healing and whatever. And here you see how the microorganisms are storing polyphosphate inside of the organisms in nanoparticles, approximately 100 nanometers in diameter. It is not soluble. And we found out that it is calcium polyphosphate in the nanoparticle range. And so we had a challenge if we can produce this kind of amorphous calcium polyphosphate material, which we obtained. That is a calcium, the nanoparticles from calcium polyphosphate, and you see that it's highly amorphous. And then if you remove step by step the polyphosphate out of this, we get the crystalline state. So we have the patent for this all over the world. And now I want to show you some pictures how we could apply this kind of material for sealing of cracks in the cement. So that is amorphous calcium phosphate, and it is stabilizing amorphous calcium carbonate and also amorphous calcium phosphate. Let's stick first to the amorphous calcium carbonate. The other thing is, this picture I showed for Eddie. So if we put this kind of nanoparticles into a solution, then we get some kind of a transition from the particle phase to the coacervate phase, that is some kind of a gel-like material. And later on, this material is becoming a phosphate when the alkaline phosphatate is around. So this is what we also developed, what we found further on, is what is introduced protruding into the cracks and is going to reseal the cracks. This is after later stages, and this process is called coacervation. So we are using for sealing our cracks cement with nano microparticles which contains polyphosphate. And I want to show you the final product. These are the nanoparticles, and in different stages we can see with FTIR the transformation from the sodium polyphosphate to the amorphous particle polyphosphate to the coacervate and so on. So we can follow this up, and then we saw if we add it to the cement, we can see already that the cement becomes tightly packed. Somehow this kind of polyphosphate is gluing the cement particles together via the coacervate formed from amorphous calcium carbonate together with polyphosphate. And we made this kind of biomechanical things, and this is what I like very much. We were cracking it, and then this part is jumping out. So, and we made this kind of force displacement studies, and the material which we produced with the calcium polyphosphate is not that hard, it's more dynamic, basically what we want to have for any kind of crack filling material. Then, in order to make it more realistic, we went to an old building, we isolated bacteria out of this, the stones, calcium carbonate stones, and we produced, we synthesized polyphosphate, calcium polyphosphate out of it, and could then mimic also everything what is shown here in this slide. Also in situ. At the beginning, we have the calcium polyphosphate, and in the presence of the bacteria, that is the issue. The bacteria are basically the driving force. If we add or if we store calcium phosphate in in a bag or wherever, we can leave it, if it is stabilized with polyphosphate, we can leave it for half a year, nothing, or for a year, nothing happens. But if it comes together with a bacteria, we get a transformation from the nanoparticles to the boatzerate stage, and then finally to the crystalline stage, which is calcite. So a few more pictures, and we can make it also with calcite. So here we have at the beginning with amorphous calcium carbonate, then the nanoparticles are coming, and the polyphosphate, which is a stabilizer for the amorphous calcium phosphate, is chopping off polyphosphate, and then we get a transformation. That is all, and the alkaline phosphatase is not introduced by us, it is coming from the bacteria. So the final product, we formulated a material which could be sprayed, or also brushed, but spraying was easier, brushed onto a cement crack, and we heard yesterday that it was working also somehow beneficial to the Warsaw monuments. So basically we can come up with the last picture. I think we have a concept at least for even we can produce now a large amount of our cement together with amorphous calcium phosphate, amorphous calcium carbonate particles in it in large amount, and it costs approximately per kilo 2 cents more. So it is not so expensive. So we have here a crack, we fill in our material, and finally we can reseal. So I stop at this point, and I thank you, and I hope I was not boring you too much. Thank you.
Thank you very much for your wonderful presentation, Werner. I want to say thank you very much to Professor Wang, to Professor Muller for the involvement in the InnovaConcrete project and for very amazing work. I think the success of the InnovaConcrete project is to join efforts, people so different, such as people working in laboratories in outstanding level, like Professor Muller, people writing journal papers in journals like Nature, working in polyphosphate, working in very high level research, with architects, with engineers, with people from the case studies. This, I think, is very difficult, very hard to join these complete different topics, complete different works, but I think this is the important success of this project, because we can discuss together. The another day we have the internal meeting, and we discuss together with modeling, with experimental persons, with people from case study, and we have very nice conclusions. I feel in this case that this is only the beginning of the work together. I think that this is the first time working in concrete, working in cement for your laboratory, and for me it's an honor that the first time is in InnovaConcrete is in this project. But I am sure that we are going to prepare another collaborations, another synergies in the future, because this is a very promising strategy. I will need to continue to explore this strategy, because I think it's the future for a lot of problems of the K concrete. Thank you, really, thank you very much. Thank you very much. And now this is time for any questions for Professor Muller about the materials, about the talk. Do you have any questions? Okay, Jan.
Thank you for a really wonderful talk. Actually, I have more questions, but first I would like to ask, because you have the carbonates that you produce, what is the pH within this, and especially related to reinforced concrete? let's say, would this protect then the corrosion? I know it protects, let's say, water to enter, but related to pH, would this protect then the reinforced concrete as well?
Yeah, Eddie, this was the crucial point when we prepared the calcium polyphosphate nanoparticles. At pH 10, they are stable. And this, at pH 10, stable. Yeah, but if you put them down to pH 7 or pH 3, then we have this transformation to the coacervate, which is a biologically acting working material in our body, but also in the cement. It's a material which is transformed from the pH, let's say, 10 or 8 to at pH 5 or 5.5. Then you get this transformation to this glue-like material, coacervate.
But let's say you would have then the corrosion of if it's in contact with steel or with reinforcement.
Yeah. This was a question which I asked also. Federico and also Gabriella. We can reach, let's say, when they make corrosions, they have a surface and they use particles which have a diameter of 50 nanometers or even lower. And that is exactly the size which we need in order to avoid any settlement for the bacteria, because the bacteria are larger than 500 nanometers. They can never penetrate into this smaller caves of the corroded steel, but the nanoparticles of them can do this. So they can nicely preserve the steel.
Can I have just one more? No, because bacteria are not so happy with the environment of pH 12, 13 as it is in Portland cement. Do you introduce then additionally bacteria within this product, or they are really naturally present, this type of bacteria in the concrete?
You mean the polyphosphate?
Yeah, so for the enzymes, the bacteria that...
Yeah, first of all, yeah, that's a very good question, and thank you. We can isolate from, let's say, 1 gram of bacteria, which we isolated from the concrete. You can easily isolate approximately 100 microgram, a huge amount of polyphosphate. So the bacteria, what usually the people don't realize, is full of polyphosphate. And so the bacteria is a carrier for polyphosphate, and on the surface of the bacteria we have the 2 enzymes which are processing polyphosphate. Thank you.
Thank you, Janet. And now is that we have 2 last presentation in this section. We are delayed in the session. That the reason is that we have a lot of questions, and it was very, very interesting session. And thank you to all people for your interest in the InnovaConcrete product. Now is the time for Inés. Inés is from Torroja Institute. She's going to present an innovative material developed in InnovaConcrete. This is a mix between the mortars, micromortars, with the product prepared in University of Cádiz, the hydrophobic product. This is again a new collaboration between 2 partners from InnovaConcrete, and the idea of this solution is to apply in the case of cracks, in the case of bigger cracks than the InnovaConcrete impregnation treatment that we cannot use. And thank you, Inés, and this is your time.
Thank you, Maria. I'm going to try to be fast. So, hi again, everybody. So, as Maria said, I'm going to talk about the repair micromortars with hydrophobic. Oh, sorry. You can hear me now, no? Much more better. Sorry. So I'm going to talk about the development of repair micromortars with hydrophobic performance. Well, I have already showed you this picture. It is well known that the concrete structure can suffer different types of deterioration processes. As we have said this morning, regardless the type of the decay process, the consequences for the concrete are going to be always the same, and is this increase in its porosity, its permeability, and the consequent cracking. So nowadays there are different strategies to try to protect the concrete. These strategies usually contemplate change during its fabrication process. However, in the particular case of the old concrete structures, especially those built in the 20th century, no particular care was taken, probably because at this stage the mechanisms of decay were still unknown. So, as we have seen, one common approach to try to protect the cultural heritage concrete is the use of impregnation treatments. Among these impregnation treatments, we can point out the use of consolidants and the super hydrophobic products, which respective objective is that to recover the cohesion of the material, that is to say the loss of mass that we have with the decay process, and also to avoid the water ingress. As we have seen during this morning, the water is one of the most aggressive agents for concrete. We have already seen that the impregnation treatments that we have developed during this project are very, very good to heal or to shield small micro cracks and cracks lower than 1 millimeter. And what is more, these products are going to be 100% compatible with our substrate. However, as Maria has said, we can have the case of cracks much more bigger than this 1 millimeter or important loss of the material, where these solutions are not as good as we expected. So it's necessary the application of another kind of solution. The solution will be the repair micromortars. In the market, there are a lot of types of repair micromortars for concrete, but as far as we know, none of them has been especially designed for the protection and the repair of the cultural heritage concrete. So, with this in mind, one question arises, and is how must be repair micromortars, especially designed to repair our cultural heritage concrete. So, must cover three important aspects. First of all, must be compatible with the original substrate. Secondly, must show similar features like color, but also similar properties like the porosity or the thermal conductivity. And last but not least, must have mechanical compatibility with the substrate. This means that the mechanical strength of the new repair micromortar must be equal or even lower than the original substrate, because in case of the breakdown, it's preferably to use the new repair micromortar than the original substrate. So with all of this in mind, in the Eduardo Torroja Institute we have designed a new repair micromortar in which we want to cover the different aspects. We needed to have a high fluidity and a medium viscosity to be applied via injection or via spatula in the cracks of the mortars and concrete substrates. We needed to have a good stability volume, a good adherence to the original substrate, mechanical compatibility, and also a hydrophobic performance was also desired. So let me turn now to show you the raw materials that we have used to prepare our repair micromortar. So in our case, we have selected a white cement. The reason to select this white cement is because this is going to facilitate the final color adjustment that can be easily done in the monument with the use of pigments. We have used sand with a small particle size diameter. We remember that we needed to apply this via injection. We also have used several chemical admixtures provided by one of our partners, Sika. The use of admixtures are going to be used to improve or to modify certain properties in the mortars, like the rheology, so the fluidity, the viscosity, but also other properties such as the adherence or the stability of can you hear me? Oh, sorry. Of the stability of volume. And finally, we have introduced our star product, the EUCA TP product developed by the University of Cádiz. So this product, as Rafa has explained very well this morning, is a combination of silica oligomers plus a surfactant, which is going to have a consolidant effect, but also incorporates certain proportion of polydimethylsiloxane, which is to provide to our mortar the hydrophobic performance. So here I have prepared a couple of videos. First of all, what we want to do is to test the fluidity of our mortar, the fluidity and the viscosity. So for this, what we have done is to premix all the solid materials, that it was the cement, the sand, and the chemical admixtures with the water. And we have incorporated during the mixing the product provided by the Yucca. And here, what you can see in this other video is a very easy test, the mini-slam test, that is usually used to check the fluidity and the viscosity of the 72 spaces. As you can see, it consists in to put in this cylinder, which is bottomless, the fluid mortar, and after 13 times, so 60 seconds or something like that, you lift the tubes and you are going to see how is the spread of our repair micromortar, and we can test it if we have bleeding, the viscosity, and so on. As you can see, our mortar is quite fluid. So once we have obtained the mortar with our desired properties, we have tested all the kind of properties. So for this, we have prepared several types of specimens. So we have tested the mechanical strengths, we have tested the hydraulic properties, so the capillary water, the low pressure water absorption, and also the contact angle. And we also have tested the stability of volume. But we also have done another approach, that it was to double check two important properties of our mortar with respect to the substrate, which are the adherence and the sealing capacity. For this, what we have done is to prepare specimens with simulated cracks with different diameter, and we have filled with our fluid mortar these cracks, and later we have tested these properties, the adherence and the capacity of sealing. So I'm going to show you some results. So in summary, with respect to the mechanical strengths, we have obtained mortars that are compatible perfectly from the point of view of the mechanical strengths with our original substrate. In all the cases, we achieve more than 50 megapascals. So we also had checked the volume stability. So we didn't see an important wrinkage of our material, which is very important. With respect to the hydraulic properties, through these different tests, below water absorption test and the capillarity water, we have observed that our mortar has a very low water absorption. And with respect to the hydrophobicity, through the test of the contact angle, we have checked that we obtain angles higher than this 90 degrees, which is a clear indication that our mortar that we are producing has these hydrophobic properties. So finally, as I have said, we have checked also the adherence and the capacity of sealing of our mortar to the original substrate. So in the pictures on the left, you can see that the repair micromortar that it appears like in white is perfectly integrated in the OPC sound matrix. So we didn't see any kind of debonding failure. So the adherence was practically perfect. And with respect to the capacity of sealing, we used this test, the custom pipe test, and we observed also that there was not any kind of water absorption, which is a clear indication that the mortar has sealed completely our crack. So in conclusion, so the impregnation treatments are very effective for the protection of the cultural heritage concrete. However, as Maria has said, in particular cases, we need other kind of solution. The solution could be these repair micromortars. So the incorporation of this UKTP product into the fresh mortars improve a lot the hydraulic properties. So in all the cases, we overpass with 90 degrees, which is a clear indication of the hydrophobic performance. And at the end, we have achieved a mortar with a high fluidity, mechanical compatible with the substrate, and very good hydraulic properties. And that's all that I wanted to show you. Thank you so much for your attention.
Thank you very much, Ines, for your presentation, and thank you, Ita, to all people from Torroja, because you did a very amazing work in InnovaConcrete project, and this is a promising result, the combination of Ronuca product from the University of Cádiz and micromortar. Thank you. I don't know if you have any question. We have very, very short time. I'm sorry about that, because we are really delayed. But if you have any question, this is your time about the micromortars. Okay, so in this case, we are going to present the last talk in this session. This is the device. We produce a device in this InnovaConcrete project. It's the plasma atmospheric plasma, and as I described before, this is the combination of the one product from the University of Cádiz joining to plasma atmospheric prepared, produced designed by the on-back company. A good collaboration. We have a patent in preparation, and this is. I'm sorry, Gianfranco, you have the. Okay. Sorry, it doesn't work. But yeah, you have here. Okay, you can do this. It's not necessary to. Okay. No, you need to copy in this case. Copy to the. You open? No. Open. Abrir. Sorry, some technique. Can you help us, because we have a problem with the presentation, please? ¿Se puede venir algún técnico a ayudarnos con la presentación? No, now it's okay. No, don't. No, but it doesn't work in the. No, you cannot open again. No. ¿Alguna persona de técnico, por favor, puede acercarse para ayudarnos? Porque no. Sí, allá viene. In this time, I'm going to remember the visit tomorrow to the different monuments in Cádiz. The visit is starting at 10:30. The meeting point is El Olivillo. If you remember the building with the banner when the buses stop it, and we are going to start with the visit to the Olivillo, that we have in this visit two significant architects. They lead the renovation of this building. And next we are going to visit the Testaccio, the Roman Testaccio, and in the subway of the building. And next we have a visit to another monuments in Cádiz. I don't know the time for the complete, total duration is 2 hours, exactly 2 hours for the complete visit of the different monuments. The visit starting in El Olivillo building, el edificio El Olivillo, at 10:30. Thank you. And now this is the time from Gianfranco. Thank you, Gianfranco.
Sorry for the technical issues. In this presentation, atmospheric plasma treatment for the super hydrophobic surface treatment.
I will talk about the plasma. I will spend some word about the atmospheric plasma device, and then I will talk about the work done during InnovaConcrete for the treatment for superhydrophobic surface. So the plasma is often indicated as the fourth state of matter. Lagme introduced this word in the 1923 to indicate partially ionized gas that contains the same number of positive and negative charge. All of us know the plasma because the 97% of the universe matter is in form of plasma, and some examples are the aurora borealis or some flares. And we can reproduce the plasma in laboratory by raising the energy, usually by electrical field or magnetic field. Because an object interacts with the surrounding through its surface, we can preserve or modify it by control the physical and chemical properties of the surface of the object. And even if there are different approaches to do it, plasma-based technology are more suitable because allow to modify the surfaces acting only on the few nanometer of the surface without modifying the bulk material. Indeed, plasma processing is not a process, but a field of opportunities for the surface modification. And here I report some of the many plasma applications used for the surface treatment, like the deposition metallic or insulated material by physical vapor deposition, deposition of diamond by microwave chemical vapor deposition, the clean through ion etching, or the treatment of cultural heritage, the cleaning of ancient photo, or the creation of a protective film on ceramic. But all these examples need the use of vacuum chamber. Vacuum chamber can be defined as a chamber inside which the gas molecules are removed through the expensive pumping system. But for some application, like biomedical application or the treatment of large objects like monument, we can use vacuum chamber, and we must use another plasma technology, the atmospheric pressure plasma source, that can be defined as a device inside which the plasma is formed after a gas discharge and projected outside in the environment. The main part of this kind of device are the gas inlet, the region where the plasma is generated, the region where the plasma interacts with the precursor, and the interaction region of precursor, plasma, and atmosphere. The main advantage of this kind of technology are that are environmental friendly, are cheaper than the vacuum-based plasma technology, and made possible the in-situ change of the surfaces outdoor. Here, two examples of the already manufactured plasma torch, one for the sterilization membrane and another one for the removal of aluminum from polycarbonate, to show you that for the specific application we need different energy of the plasma. And so we need to act on the electrical or fluid dynamic parameter. And in particular, we have to consider that biomedical application or the direct treatment of cultural heritage need to work with the plasma at low temperature to avoid damage of the substrate. So talking about the work done during InnovaConcrete, we developed two atmospheric pressure portable plasma devices to apply the hydrophobic compound, the UCATP, developed by UCA, for the super hydrophobic treatment of the concrete-based monument. In particular, our work focused on the manufacturing of a device based on the plasma generation through a low thermal technology to avoid the substrate alteration as well as the chemical alteration, and a device able to ensure high roughness, uniform roughness surface, in order to induce the Casey-Baxter state, a condition in which water will not penetrate the roughness, unlike the Benzel state as described by Raphael before.
So starting from the design, we fabricated two hardware, two plasma torch, one liner to cover 100 millimeter of surface and one B-shaped to treat twisted surfaces. Both the hardware are based on dielectric barrier discharge configuration, that is a way to obtain a low thermal plasma. And both the torch are characterized by a plasma generation chamber, a post chamber where the precursor interacts with the plasma. Other two developed part of the device are the power supply, in particular an high frequency, high voltage power supply that ensure the DBD plasma generation, and the system for the regulation of the gas and precursor flow. Because the parameter definition is a crucial aspect of the plasma-based technology, the power supply is settable, and the control regulation system allow to adjust the fluid dynamic parameter. And during the development phase, we restrict as much as possible parameter like frequency, flow, that will be used, that can be set with the system control, in which the power supply and the flow regulation system are combined. Thanks to the control system, the operator can set and configure the atmospheric plasma torch, can control in this way the coating porosity and the surface finishes, and can select parameter in order to work in mild condition. These are the two prototypes that we fabricated, and the plasma torch with the video of the plasma torch after the activation of the plasma. The developed devices are transportable in order to exploit outdoor the high performance of the coating that the plasma technology can ensure. And after the development of the two devices, we characterized the prototype on a silicon surface and on OPC mortar, looking at the higher spectra of the treated silicon buffer. One buffer treated only by spraying the UKTP on the surface, and the other treated at different power condition of the plasma. We can see that in looking at the spectrum, there are no variation in the shape and the peak of the bands. That means that the chemistry of the compound, of the chemical compound, is preserved, and it is possible to observe a decrease in the band of the SCOH that indicate that the plasma treatment can accelerate the polymerization of the UKTP and so the formation of the salt gel. If we look at the higher spectra of the OPC mortar treated with the plasma devices, we can compare the mortar untreated, the spectra of the specimen mortar treated by brushing the UKTP, and the mortar treated with the plasma devices. Also in this case, the plasma does not modify the mortar composition after use, and this spectra confirms that the UKTP reaction product applied with the plasma devices have the similar composition of the substrates. Looking at the SEM and the wettability test, we can see that the untreated mortar surface is irregular surfaces that show an hydrophilic characteristic with a static angle of 30 degrees. The mortar treated by brushing the UKTP is a flat surface that show an high contact angle but no water repellence, while the mortar treated by plasma, in the mortar treated by plasma, we can observe the formation of the nanostructures and it shows super hydrophobic surface with a contact angle over 150 degrees and water repellent with an hysteresis angle below 10 degrees. So, as explained by the Casey-Baxter working model, high glucosity combined with the surface energy promotes the super hydrophobic characteristic of the surfaces. All the mortar treated with the plasma devices do not show aesthetical alteration like the one where the UKTP is applied by brushing. So with the test on silicon OPC mortar, we show that the plasma in conjunction with the UKTP can create linked structures that promote the super hydrophobic characteristic of the surfaces, and so we moved to the in-situ test. We made the in-situ test in Torricella Peligna, on the right the video of the application. After the application, by visual inspection, it is showed that no color alteration, no tactile alteration are present after the plasma application, and that the plasma application is rapid and can be done by using few millimeters of product. The monitoring carried out by the CNR confirmed that there are no color alteration and validates the capability of the plasma treatment to make surfaces super hydrophobic. So by concluding, we manufactured 2 plasma devices able to deposit UKTP, a technology that can work avoiding the surface alteration and that can be used for the preservation of the concrete-based monument. Finally, we demonstrate also that the ultraviolet ray created with the plasma can accelerate the UKTP polymerization, and that the use of the plasma rather than the brushing method allowed to a faster application to reduce the quantity of the product applied. Thank you.
Thank you. Just a moment. Very nice presentation from John Bach, Gianfranco. I want to remark that put very nice synergy between the UCA and John Bach, and I would like to remark 2 significant conclusions. One of them is they prepare the system without preventing thermal treatment, and this is important for cultural heritage. And another one is in the specific case of our product, we demonstrate that the plasma treatment can promote the polymerization of the product. It could be very interesting. In some cases, we need a quick polymerization of the material. And this is a different conclusion that is not in the original objectives of the project, but it's very nice. And we are preparing the patent, and we hope that it could be in the market in the future. Thank you, and I don't know, we don't have any time, but if you have, we have very, very short time for only for one question, but it's not questions. So, thank you, and now is the time of the third part of this session. This is what I want to say. Thank you very much to people from Work Package 2, because they did some very amazing work. We have over 40 papers and another maybe 20 in preparation, and in very high level journals, and it demonstrates the importance, the innovative of these materials. For another one, we have 1 product in the market, and 2 another product close next to the market. And now is the time for the validation in situ work package. This is work package 3. Please, people from work package 3, you can join in the table, please. And Gabriela from CNR, she's going to be the chair. She's the leader of the work package 3, and she's going to be now the chair of this session. She's going to introduce 2 different groups, 2 different partners. They are the people that they work in the monuments, they did the validation of the monuments. In this moment, I would like to have present to the one person. He's not here today due to the problems to the COVID pandemic. He's the Piero Tiano from CNR. He was an important, significant person in this project. I think he is in a virtual way, but he's not today here. But he is the leader of the mobile laboratory, and he was very important in this work package. And now is the time for Gabriela. Thank you, Gabriela. It's your time.
Okay, thank you, Maria, for the introduction. And in this session, we will discuss about the in-situ validation performed on different case studies which are located in different countries, and so we can take into account the behavior of the materials in this different context. We are going to start the section with a first contribution from CNR. Will be presented by Joanna Kuzman, and she will discuss about the monitoring strategy which was defined and used for to study the behavior of the products in situ on the monuments. So, one moment that we.
Hello to everyone. So in my talk, I will speak about the monitoring strategy for in-situ assessment of the product's performance. First of all, I would like to thanks to all the partners that collaborated with us for fulfill this monitoring program. At the beginning, it was planned in a way, but due to the COVID situation, we should to recalibrate our monitoring plan because of the restriction to travel. And the case studies where the monitoring work performed for validation, for evaluation of the conservation state or for the evaluation of the products are the Centennial Hall, Elogio dell'Orizzonte, Eduardo Torroja Institute, Flaminio Stadium, Zdromesher Train Station, Ninth Port, and the War Memorial Tower, and the War Memorial Angel, which was the case study for the restoration. So the monitoring workflow includes, let's say, to monitor the conservation risk assessment and to identify the criticality of the monument, and for this it should be selected the appropriate parameters and instruments for this task. And the monitoring is also very, very useful in product evaluation, in which we selected appropriate treatment areas, and then the products developed in this project were applied, and the appropriate parameters and instruments were selected for its evaluation, their evaluation. The criteria for the evaluation of the new product was to select suitable experimental test areas in each monumental site, to design the protocol for cleaning and the protocol for the application of products, to establish the diagnostic protocols, which includes the instrumentation and the methodologies, to define the correct procedure for the evaluation of the products developed in this project, and the monitoring at different times. And it was agreed to also, because of the COVID situation, to measure at least 5 common basic parameters: the color, the hardness, the compactness, the water absorption, and the photographic documentation. However, I would like to mention some
differences between the validation and monitoring and validation on-site versus laboratory. In laboratory, as my colleagues showed in the previous presentation, you can prepare specific dimension of the samples. You can measure with the standard methodologies, so it's very accurate. While in on-site, the situation, it's a bit more complicated, let's say, as there is a higher variability of the surface with respect to the ones of the mock-ups. However, these differences are due to the characteristics of the surface, to the suitability for doing specific measurements on site, which often is the roughness is very important, the test area of the instruments as a dimension versus the aggregate grain size, or the hidden rivers that you cannot see inside the monuments. The different aging, so in laboratory you have a controlled aging, in the on-site it's a different one, a natural one, and the influence of the external exposure, the climate, if it was rained or not rained, so the measurements are a bit changing. However, for this reason, it was fundamental to have a reference area not treated, very close and with the very similar characteristics to the treated one during all the monitoring campaigns. As I said before, due to the COVID situation, we shared the monitoring activities with the different partners, but this created somehow also some drawbacks. I thank again to all the partners for their help. These different factors that influenced the monitoring activities were related with the application being made by different operators of the treatment, even with the same protocol. The instrumentation that have been used, even if there was for the selected parameters and for using the same principle, they could be different, and the performance of the measurements by different operators. Here, I resumed the parameters and the instruments that have been used to assess the protective consolidants and corrosion inhibitors products. So for the color changing, it was used the spectrophotometer. The hardness was measured with the Schmidt hammer. The compactness with the ultrasonic pulse velocity, and so on, as you can see in this table. So I will go further. Here are some examples of the instruments that I presented before, the colorimeters. Here are, for example, two, one used for the CNR, from the CNR, and one used from Centennial Hall. The Karsten tube, the sponge test, the ultra pulse velocity, the Schmidt hammer, peeling test, the instrument for measurement the electrical resistivity. Here is the SUSI and thermocamera. For what regards the mortar repairs, it was there were used 3 continuous monitoring by means the 3D scanner and the wire crack meters, which was performed by Rina. And the ultra-close range photogrammetry was used only in the case of Torricella Pelligna on one type of mortar. And the photographic documentation was used in all the cases. This minimal, let's say, methodologies for monitoring the crack stability helped to understand if there was some morphological changes in time or some detachment problems or new fissures in the mortar. So with as regards the solution for solving somehow the critical points that I mentioned before. So one of the conditions was to have two similar areas, one treated and one not, in the same condition, atmospheric condition, and of the quality of concrete. So the selection was the selection of the areas that have been made before the product application considered that the surfaces to have similar characteristics, to have a similar environmental condition, the exposition, to use the same protocols, for example, for cleaning the surface, to use the similar devices and the similar skills of operators. So the data collected for the selected parameters must always be checked at each time during the monitoring campaigns on the both areas, evaluating the behavior in time of each product with respect to the not treated area. So in such way, the project can collect comparable numerical data about the products applied in each monument for their validation. And in order to compare the results that we obtained on all the monumental sites that were acquired by different operators and operators, we considered a percentage value that with who we can distinguish a real variation from the possible errors that may occur in on-site measurements. So, to separate the variation, let's say, of the surface roughness with the influence of the product, let's say, surface roughness, surface heterogeneity, not only the roughness. So in this way, we could identify the presence or the absence of an evident variation of the parameter. And to do this, we fix it, taking into account also the standard deviation of the measurements that we obtain, a threshold of 10% as a minimum one. So here is a summarizing table on which you can see all the case studies, and on the right-hand side, there are the applied products on each monument. And now I will continue.
Okay, and now there is the contribution regarding the results of the in-situ validation on the war memorials in Torricella Peligna in Italy. This contribution was prepared by Maria Isabella Pierigè from the Ministry of Culture in Italy, and by Oana Kuzman from CNR, and will be presented by Oana. So thanks.
Okay. So I will start with the case study of Torricella Peligna. And here are, actually, I will start with the Torricella Peligna War Memorial Tower. And then we will show you a video or two videos that prepared the Isabella Pierigè about the angel. So I will speak about in this intervention about War Memorial Tower, and later about War Memorial Angel. Here are the two monuments that have been selected in this project for the application of the products due to their social importance and the presence of the cement. The War Memorial Tower was cleaned by using two different procedures. One with the CSGI method product of the University of Florence, and one with the sandblasting cleaning, for comparing in between to see which one is the best one. And a part of one cleaned area, which is called S4, all the rest on which the products have been applied were cleaned with the CSGI method. Here are some details about the location and application characteristics of the products. All the products have been applied by brushing. And here are some other, here is the application of the tube material, for example. Here is before and after the application of UKT plus LED-ACA corrosion inhibitor. And here are the products that have been, all the products that I mentioned before were applied inside the tower, while these ones, the UKTPS, the superhydrophobic product, and the UKTP applied with the plasma have been applied outside of the tower. Here are the mortars that, some examples, some photos of the mortars produced by CSCGI mortars and the XIC, the Toroja Institute mortar. And here is the summarizing table with all the products. So the protective UKTPS, UKTP plus plasma, the consolidants UKT and TUC, consolidants plus corrosion inhibitors, these three ones, and the mortar repairs is missing only the mines one, but the Torricella Pelligna War Memorial Tower was actually the site on which have been applied almost all the products except the mines mortar. And these two mortars, CSCGI 2 and 3, were monitored continuously by RINA. Here I show you again the instruments and the parameters that have been monitored in the case of the War Memorial Tower. Here the same in the case of the mortar repairs. Here is some areas on which, as an example, on which the RINA performed its continuous monitoring. And here down some other measurements, the ultrasound pulse velocity, absorption methods, and biological presence assessment with the ATP test. And here is the photogrammetric methodology. The results show for what the color concerns, the color didn't change the color of the treated surface so much. And however, in the case of the products that was the value, the delta A values was above 5 threshold, which is considered that cannot be seen by naked eye on very huge and uniform surfaces, because in the case of the paintings, for example, the threshold is 3. However, in the restoration intervention of the cultural heritage, a slight decrease of the luminosity sometimes make the surface more vivid and is not always considered a drawback. So the color variation could be assessed case by case when a product should be applied. So the results as regards the other parameters, we applied the formula that and the concept that I presented you in the previous presentation. And we observed that the weighted response for the consolidants and corrosion inhibitors and protectives are in pink. So the products behave quite well. On all, also the hardness was improved, compactness for some consolidants, the superficial cohesion was improved for all of them, for all consolidants. The corrosion inhibitors showed very good results, and also the protectives show the water absorption reduction very good. And also the biological presence was observed especially outside, as it was quite obvious, also due to the presence of the roughness. So the biological presence doesn't mean that the product is biodegradable. It's only bioreceptive, but also due to the roughness of the surface. So the other parameters like SUSI, IR thermography, electrochemical measurement, chemical stability, and byproducts formation, and morphological aspects remained quite unchanged without. As regards the mortar repairs, the same in pink color are the expected weighted results, and from photo survey, most of them, they remain unchanged, so no detachment, no. The 3D model show that some little change, but the surface general remain unchanged, and the same also for what regards the microscopical aspect. So with this, I finished the Torricella case study, and we can put the videos for what regards the angel.
Maybe they should, they have the video, okay, perfect.
Please, we can play the first video.
Por favor, en la parte técnica, ¿podéis cargar el vídeo de la restauración del ángel de Torricella? What's the name of the title of the file? Not here.
Otherwise, after lunch, it is not. Yes, this is.
Okay, thank you.
Torricella Peligna is a small town in the province of Chieti in the Abruzzo region, Italy, located at about 1,000 meters above the sea level. During the Second World War, this town was included in the Gustav Line area, a defensive line that divided Italy in two parts by using the natural obstacles aimed to delay the advance of Alliance force. After the great slaughter of innocents, the citizens of Torricella Peligna built two monuments, the Angel and the Tower. in order to commemorate and don't forget the fallen of both the world wars. The monument, named The Angel, is impressive and majestic, and it was dedicated to the fallen of the First World War. This war memorial is located at the center of a remembrance park, on the top of a hill close to the historic town. The monument at the central and highest position acts as the organizing element of the park, with majestic and imposing dimensions. Standing on the steps in travertine with a quadrangular base with 4 literary bundles at the corners and surmounted by an obelisk, it recalls the names of the heroes of Torricella during the wars. The angel sculpture in concrete is placed against the obelisk at the frontal side, looking towards the town. The figure, with female features in classical style, has hair that is worn tied back from the face and the wreath of laurel leaves. A strong sense of power is associated to the kindness of the winged figure, represented while is writing in a golden book the names of the fallen, and at the same time is squashing with her left foot a big eagle, a symbol of the Habsburg Empire, which in the meantime is struggling to get free. The monument is a work of Lucci from Pennadomo, built in 1922. Still today, the monument recalls the sacrifice of local people during the world wars. After a few years, the monument was damaged by a hurricane and then was also bombarded during the Second World War. A reconstruction intervention was carried out in the early 50s, involving the local administration committees to remember always the horrors of wars and the human sacrifice. After completing the activities planned for the Tower War Memorial in order to give further strength and validity to the project materials, following the sampling and characterization activities carried out also on the Angel War Memorial, called Zaffi Lumena by the Torricella inhabitants, we decided to intervene not by carrying out a simple activity of application and validation on the limited areas of the monument, but to organize a real restoration site, carrying out all the operations that, according to the standards, will be foreseen in a real conservation intervention. In addition to the return of the restored monument to its citizens, the aim of the work was to test in a real working environment the eventual problems of the materials related to their workability, resistance, and ease of application in a way compatible with the normal methodologies used for intervention on similar artifacts. From the research of the historical documentation, which was provided in part with the help of the inhabitants and the municipal administration, it was possible to make more detailed assumptions about the modalities used for the past interventions. The statue was initially green, but it was probably painted with white between the 50s and 60s of the past century, following the restoration works after the bombing that it had suffered during the Second World War. The last and most invasive intervention, instead, has seen the application on the entire surface of a grey paint, with characteristics absolutely not compatible with the underlying material that, in recent years, has contributed to a very accelerated advancement of its degradation. The first intervention, preceded by a 3D relief, has been the removal of the irrelevant and degraded layers of paint using traditional methods. This operation allowed to highlight all the criticalities of the monument and also allowed to choose which materials would have been appropriate to be used, both for the consolidation and for the construction closure of the missing parts and cracks.
Restoration work has been supported through additional investigations carried out by non-destructive techniques and devoted to assessing the product's behavior developed in the InnovaConcrete project. The analyses that have been performed are the following: colorimetric analysis, water absorption assessment, bioluminescence, microscopic observations on site, X-ray analysis, durability of mortar through structure from motion technique. Colorimetric analysis showed no significant color variation. The water absorbance results are in accordance with the colorimetric assessments, indicating that from autumn to spring the surface became more dry. The bioluminescence measurements revealed a great reduction of the biological presence after cleaning. The 3D models used for the evaluation of the durability of the CSGI3 mortar used close a long crack along the arm of the sculpture demonstrate that after 6 months the mortar was well adhered to the surface and the crack is well sealed. In the following images, the 3D relief of the statue before and during the restoration with the mapping of all the mortars used and the end of the work are shown. Thank you very much for this great work that was performed, and I want also to say that this work is significant because this war memorial very important for their symbolic value as a representative for the memory of all the European citizens, so this is very important. And now we will have a break for lunch, and then we will be back at what time? Half an hour. And maybe also for the question, I don't know if you have any question or if we want to discuss after lunch.
I want to say thank you very much to people, especially to Isabella, people from MIVAC, people from CNR, because and Vigorra, because it's a very nice movie, very nice film, and I think it's an amazing result that you restore the complete restoration of the angel. And I think you have another important significant importance in this monument, because it's very important for the citizens, to the European citizens. Remember the war, remember this very bad history, because it's important to know the history, because we cannot repeat we don't want to repeat the history. This is the important reason. And Isabella, you did an amazing work in this project, and really happy with your work, really happy with your enthusiasm in the project, and thank you very much to be part of InnovaConcrete.
Thank you all. Thank you, Maria. Thank you for the support by the CNR, Oana, Sabrina, all the partners. And I think that the project is very important for the conservation monument and for the concrete conservation. I'm a restorer. The conservation monument for me is very, very important question. And about the social awareness, I would like to show you a second video. Okay. Because the small town in Torricella have participated to the restoration. Okay.
Thank you.
Okay, so now we have now, in order to continue the section, we have the contribution of David Lopez that will talk about 2 case studies, one in Kaunas and one in Poland. Okay, thank you.
Thank you, Gabriela. So, well, first of all, congratulations, Isabella. Really nice video, but you increased the standards of the presentations. That's unfair. Well, I would like to welcome the project officer, and I hope not to make it too dense. So I'm going to speak a bit about the in-situ validation in 2 case studies. Sorry, I don't know what happened here. This is a bit the schedule that I'm going to be following. I'm going to talk a bit about the brief introduction, which were the preliminary steps that we took before applying the products, and afterwards, which was the product in-situ validation, well, different steps. And finally, I will finish with some conclusions. Well, just to contextualize a bit this part of the project, this morning we had a great presentation from Janis that was explaining a bit the theoretical part, no? The physical models that he has done in order to see that according to certain parameters, the products could actually fulfill the properties that they were talking about, that not only at the beginning, but it was undertaken at the end in order to well, tailor and improve those products. No? After that, there was certain tests that were undertaken in laboratory that well, they were incredibly presented by Inés from Instituto Roja, and afterwards we go to the real cases. Once we have validated the laboratory, we go and test in real cases to see other conditions that couldn't be tested in the laboratory, just previously to be able to conduct mass production and pass it to the industry. Well, the 2 case studies that I'm going to talk about are one in Poland, in Warsaw, and the other one in Kaunas. These are the 2. And well, in the case of Warsaw, it's a train station structure that well, it's a shell structure that was built as part of the reconstruction of the city, and it's part of a set of shell structures that formed the city central line. And well, this they show the interest of these structures is the shapes, no? The possibility that the concrete allowed in developing different shapes. In the case of the Kaunas monument, well, here we have different meanings. No, we have on one hand the magnificence of this huge sculpture, the meaning that is representing the defeat of humankind in Nazi's time, and afterwards the potential of humankind of being able to come out from that. No, and besides that, we have to say that it's in a spectacular location that coincides to be an extermination camp. I don't know what happened. Sorry for the problem. Which are the phases that we passed before doing the application of the products? Well, first of all, we did a characterization stage that we conducted several studies in order to know which were the properties of the concrete, which were the problems that the different monuments had, and try to understand which were the best products to be applied in each case. Once we knew that, we passed to identify which were the best areas to test the different products. In one way to see logistical issues, but also to make sure that they weren't very visible, just in case well, things didn't go out as nice as possible. No? And afterwards, before applying the product, we had to conduct certain preliminary activities, which were, for example, an important one that is testing the products in a non-cultural heritage site. Okay, we tested, thanks to SICA and thanks to the Instituto Roja, we could test the products before applying them in these 2 case studies. We could test them in their facilities, and this way we could well, see how they behave, how we could prepare them, and so on and so forth. Besides that, we conducted continuous monitoring thanks to RINA and some cleaning activities before applying the products thanks to CSGI. Okay, as an example of characterization activities, we did an historical study, we did geometrical and structural definition that we use for damage mapping. You're going to get sick and tired of this model today, so I will pass it. And we used it for doing different things like climate analysis, representing damages, and being able to locate the best places where to apply the products, no? Just in order to test different areas, no? With different exposition and with different problems. So the conclusions of this first stage was that in the case of Warsaw case study, the best suited products to be applied were all the sealing products, the corrosion inhibitor, because we found that there was corrosion problems, and we also tested there the consolidants and the superhydrophobic product. In the case of Kaunas, here we considered that it was a better place for testing the superhydrophobic products and the consolidants, but we also tested in certain places different sealants of the project. Okay, well, sorry. Before going to the conclusions, I'm going to see if it works. I'm going to explain. Works? Great. Well, I'm going to show a bit which were the activities of the product in situ validation. No? The first thing that I want to highlight is that well, we tested, in the case of Warsaw, we tested altogether 8 products. One of them with 2 versions, and we conducted the first application of 2 of them in October 2019. So we had 18 months of monitoring allowed, and the rest of the products were applied due to COVID circumstances in August 2020. Just to mention that all the products were applied on the top of this shell structure, because this way it couldn't be seen by anybody, and we could work a bit more freely. Okay? You're going to see now which were the different products that we tested. As I said before, 8 different products that we tested in different locations. Each product in several locations, in order to be able to see if we can detect any difference between also the environmental exposure. So, starting by the sealants, these are the ones that we tested. And here I explain a bit where they were tested. No? This is the Mi2 Zika that was explained before by Inés, developed by Instituto Torroja in collaboration with Zika. I'm sorry that I didn't put the UCA University. That was for small cracks. This one also by the same members is another sealant that is designed to address cracks and over 5 millimeters, excuse me. In this case, this was another mortar that was developed by the people from Florence, that was explained before, and it's equivalent to Mi2, that is addressing small cracks between 2 and 5 millimeters wide. And this one also developed by CSGI, and equivalent to the M4 for cracks over 5 millimeters. Also tested in 2 different locations with continuous monitoring, as you saw. And finally, here we have the Mainz product, which Professor Müller spoke before. And this product is addressing smaller cracks, under 1 millimeter. Okay? And this one could only be tested in 1 location. Afterwards, here I'm presenting all those that are impregnation treatments. No? First of all, the UCAT and the UCAT-PS, developed by the University of Cadiz. This is the first version of the product that was applied in 2019, and well, it's a super hydrophobic product that it was applied in 2 different locations, and another 2 different locations for the new version that was a version that was optimized, and that optimization consisted in the possibility of going deeper into the material. And that one was applied in August 2020. the consolidant we also applied here, developed also by the UCA team, sorry. And well, this product, what it seeks is to consolidate the top surface of the concrete, to improve that the compressive strength and the quality of the concrete top layer. Finally, the corrosion inhibitor developed by our colleagues of CNR, that it was also applied together with the consolidant developed by the University of Cadiz, and it was applied in these two locations. And now I will talk a bit about how the application was undertaken, which were the main problems that we encountered, because we think we don't need only to evaluate the performance of how the product behaved after the application, but how you transport it, how do you prepare it, and how easy it is to apply it. No? So I'm going to go a bit through. I'm sorry if it's a bit repetitive, but I think it's important. In the case of the Mi2 Sika, well, we tested in this ambient and surface conditions. It has a very good packaging, good preparation. It's easy to prepare, and it lasts long to be able to work with once you prepare it. It can be applied either with a syringe, a bit big because it has a bit of sand, or with straw, and the consumption of it is normal. You just need to fill in the cracks. So at the end, there's not much difference with other products in the market in terms of consumption. In terms of the performance of the behavior, well, just mentioned that we, for example, we measured the crack depth evolution with ultrasound equipments, and they showed a clear decrease, almost completely sealed. And in the case of the water absorption, you see a bad result here for the T0+4, but it's because of the technique. That test was undertaken in December, and it was super cold, and we couldn't manage to properly close the casting tube, but the T0+9 was giving very good results. In the case of the M4, it's more or less the same conditions, environmental conditions, because it was applied at the same time. A very good packaging, good preparation, it's easy to prepare. The workability also is good. This one is for bigger cracks. We applied only with straw, and well, the consumption is normal, no? for this type of products. In terms of the performance, well, you will see here that it performed also very well when measuring ultrasound, and the same thing for the water absorption. If you see the graph for T0+9, it shows very, very good results because it was really working. The problem of T0+4 is not because of the product, but because of the measurement that we took, that it couldn't stack properly the casting tube. So we could validate these products. In the case of now we're going to go to the Florence products. Here we have the CSGI2 for small cracks. That is also easy to prepare. This one can be injected easily because it doesn't have such amount of sand, and well, it has a normal consumption. Here we're showing that we wrap them once we apply them in order to avoid retraction problems in the first hours. But in all cases, this sealant didn't show problems related with retraction. In the case of crack depth evolution, very good results, and the water absorption, the same. We had the problem in December, but after 9 months, it was behaving beautifully. So, and we have also continuous monitoring techniques, measurements, sorry, that also support these results. And now, just mention the corrosion inhibitor that we applied under these conditions. It was easy to apply, easy to prepare, and it's applied with either with brush or with spray, so it's easy. And the consumption, it's more or less 300 milliliters per square meter. Sorry, that is, I don't know why it's not appearing here properly. Which is good. We applied it in 2 layers, as recommended, and we think that it's a good way of doing it. In the case of in terms of the result, we got good results and promising results after 4 months, and the only thing is that after 9 months, the results are not so good. So we consider that, well, it still needs maybe some more work, or maybe it's a problem of our measurements or of the product, we don't know, we are not sure. So we recommend that we continue working on this type of, on this particular product. And once I finish with this one, sorry, I'm going to show, I'm sorry, that I have another one of the other monument, okay? In the case of Kaunas, we tested, I think it was 7 products overall. We tested also sealants and impregnation products. I show this image just to, well, so you get the scale of the monument, and to call your attention also to visit it because it is really magnificent. And the spot is, the fortification in which it's built is really impressive. So, as I was saying, in this case, we applied 7 products. Not most of them are the same as we applied in Warsaw, but there are some new ones. One developed by the people of Florence that addresses the lamination problems. Just mentioned that we try to look for different locations. As you saw before, we made a climate study with sun impact, where are the locations that are more subject to rain or exposed to rain, in order to try to locate different places in order to be able to compare how the results were coming out between the different places where we applied the product. We developed a 3D model because we considered that it was interesting for understanding the structure, the monument, and locating damages, and also the location of the products to be tested. So, in terms of sealants, which ones did we apply? Well, we applied these 5. We already presented some of them. But, well, in the case of the Mi2 Sika, just mentioned that we applied it in 3 different locations. That you can see, this is the one that was addressing the cracks between 2 and 5 millimeters. And, well, that was developed by the Instituto Torroja and collaboration with Sika products, and also the UCA University with the UCA TP that was explained before by Ines. Besides that, as I say, this is the CSGI-1, which is addressing the lamination problems. This is a quite difficult problem for concrete, and well, it's a mortar, a bit with a different viscosity than the other ones for the cracks, and that I will now comment on the results. We applied the CSGI-3 on one location because we only found one crack that was that could have this applied, and in the case of the mines product, we applied here in 4 different locations. As you can see, well, we were suggested at the beginning to apply it with a brush, but we did it both with a brush and with a syringe, as I will explain now. I'm going to talk now, as before, about we also, sorry, here I'm talking about the impregnation treatment, sorry, which are the superhydrophobic and the consolidant, developed by the UCA team. And well, just mention here that we chose 5 different locations, as I was saying before, in order to be able to have different exposure conditions, okay, and analyze the performance in those conditions. Well, I think we didn't come up yet with all the conclusions that we want to also discuss with all the other partners, and maybe we are talking about seeing the way of writing a paper that well, covers all these results and these investigations that I think they are interesting for other people to know. So, in the case of the product application and performance monitoring, as I'm going to follow the same scheme as before. You have first the application and how it worked, and afterwards how did it perform. So, in relation with the application, well, I think I start with the sealants, and well, just mention that we applied the Mi2C, as you know, and this one was had the packaging here also. We applied it under different ambient and surface conditions, and as well in this place, in this case study, we also experienced easy preparation, good portability. It was easy to apply, and well, I have to congratulate the people from Instituto Torroja, because I think they came up with a product that is useful. And here we also found one of the tests that we undertook, and one of the locations, it came out really well. And here you can see with the ultrasonic pulse velocity, this was a crack depth evolution that shows decrease, a clear decrease. And in the case of the water absorption, we had the same problem. In December, we couldn't measure properly, but after 9 months, it came out very, very good results, almost completely water repellent. I'm talking now, here is the application of the CSGI-1 for the lamination problems. And well, in this case, the packaging was also very good, preparation very easy. It was also nice to work with because it lasted long. And we applied with a scroll, and here I think it's worth mentioning that we didn't see any retraction problems either. That in this case maybe it was a bit more challenging. We also had good results of improvement of concrete quality and the compressive strength. So I think it worked. In this case, it worked nicely. And finally, I left the best for the end. I'm sorry that I'm making it a bit long. I'm going to talk about the super hydrophobic product. Okay, super hydrophobic product was applied, for those that were interested before, it was applied in 2 layers. The consumption was of 300 square meters, 300 milliliters, sorry, per square meter. I say that the packaging is fair because we had some problem with the bottle, but at the end it's a matter of fixing that, and it's very easy to fix. It's very easy to prepare, the workability is very good, and it's easy to apply with brush or even with a spray if you have a very big surface. No? So I think it's something very useful. And in terms of results, I'm going to show now some results of the water absorption, which is the main parameter that we measured here. Also the color, but in terms of water absorption, you can see that it's incredible how it works. And in this case, better than any result, any test that we undertook on the field, I want to show some images and a video of what nature can show you. No? At the end, here we had snow and rain, and you can see that you can easily identify the spot where the product was applied, because it's completely dry. The surface gets wet, and the place where this was applied is completely dry. And now this next picture, for example, that I'm showing here, the one on the right-hand side is after 13 months. Okay, and it's the first version of the Yucca TPS, which is without any improvement. And I'm here showing the last time that we went, we didn't have rain, so we need to have an impact in climate and produce the rain by ourselves. And you can see after 18 months how it works. I hope that you put your seat belts because it's absolutely amazing, as you can see. Okay, so I almost shut up. Just 1 second. So at the end, the conclusions, which are the conclusions? That according to the Barcel studies, we can validate the 2 sealants prepared by Instituto Roja. We also can validate the 2 sealants prepared by the Florence institution, and we think that, well, we obtained some promising results with Yucca T, with the corrosion inhibitor together with Yucca T, and that need to be further studied. And in the case of Kaunas, here you have the results, and you have Justin. And so thank you, and excuse me for the long talk.
So thank you very much, David, for your presentation and for the work, all the work performed on 2 different case studies. So thanks a lot. And now the next presentation. Sorry. Please, if there is any question. Okay.
Okay, it works. First, thanks for this magnificent presentation and work. It was not at all too long. I could listen to this for much longer. The question, because you did also the analysis first of the damage of the weathering of material before you applied, and you said that you applied these products basically on the surfaces facing the sun. So was this because it was more weathered than on the other side, or how did you choose the places related to the direction, let's say, of wind, of sun, or I don't know whether you consider these parameters? Actually, the same question would also be for to Richela, but now I give you the question to you.
Yeah, we didn't chose only those that were exposed to the sun. What we did with the climate study or the sun study, and also with the thermographic cameras, is on one hand identify where you have more sun and shade exposure or areas, and afterwards which are the ones that are more subject to have moisture problems because they are more exposed to rain, or more exposed to rain at the same time they are less exposed to the sun. So what we tried is to test in all different possible exposures: sun, shade, places where you get more humidity or more rain impact, and so on and so forth. That in order to be able to compare if there is any difference of the product performance according or depending on the environmental exposure. I don't know if that responds to your question. And thank you for your...
Yeah, certainly it does. But related to damage, let's say, did you observe any differences in where it was related to orientation?
Yes, well, the concrete doesn't behave very well with water, and then obviously there are certain parts that you have more, how do you say, when the water goes down, for example, in the lower parts, that are also on the interior side, you have some more problems because it doesn't get dry, and the moisture is higher. So we tested in different locations, trying to include these ones and the others that experience also problems. It's also true that, for example, for the cracks, you cannot choose where they are. It's more difficult. So there we try to select cracks with different orientations. But for example, in the Warsaw station, the orientation doesn't have such an impact.
Okay, thanks. And there are any questions? Okay, please.
Yes, the impregnation treatments, well, we were told, and we tested before going in, well, actually the impregnation layers, the impregnation product we tested in SICA's facilities before going, and they were saying between 2 and 3 layers of application, and we decided to give 2 because there were certain potential problems related with giving 3 layers related with the color.
So we gave 2 layers, and overall consumption was of 300 milliliters per square meter. Okay.
Okay, if there are not other questions, we can thanks again, David. Okay, thanks, David. And the next contribution is about the in-situ validation performed at Lojo dell'Orizzonte by Guadiana in Gijón, and is going to be presented by Lorenzo Fernandez from Estudio Guadiana.
Thank you very much, Gabriela. Chillida worked with concrete for many years. He started to work in concrete in the 70s, in 1974, more or less. And the vision of working with concrete was the ability the concrete give him to make a bigger dimension, to achieve, because he was used to work with iron or in a small dimension, but not in a small scale. Their artworks were always thought to be bigger. So when he had the opportunity to make the art, workers' art bigger, he with concrete he started to do these sculptures. I was so lucky. He asked my father to start doing, and the first sculpture, my father helped him with the sculptures in the family factory, prefabricate concrete factory, and then after, when the sites were growing, at last he started doing that with a local contractor or with a contractor. So we had a lot of information of these sculptures, but they really didn't want to do a concrete sculpture as a normal way of thinking about concrete. They really were thinking about experiments. So we have here are different places with different really materials, different granulometry, different cement, sometimes aluminum cement, sometimes normal cement, some places with a lot of salt, some places in the middle of a town, very different reactions. And after 30, 40 years of these sculptures have been done, they started to have problems, and we were asked to do something about it. And we are really lucky that Fernando Espinosa and the ICOMOS at the end they came to the Cadiz document, because for an architect who does restoration, we have a lot of pressure. Imagine there are here some sculptures which are private and others are from a town hall, and but when the sculpture starts to crack, the owner wants it to be restored right away, and it's really hard to explain them that you need to do a search, analysis, characterize the concrete, understand what is happening, if there is a problem in the cement, if there is a problem in the weather, in the place where they are, and what you have to do. And for this reason, we started to do a protocol so in any case, because there are different sculptures with different cements, different materials inside, they pour sometimes things that you couldn't pour in a bridge, because they wanted it to look older, or they wanted to look with oxides. A lot of they worked a lot the patina and the surface of this sculpture. So we wanted to have
a way of dealing with this. And this was a protocol in which you study the sculpture, you analyze, and then we were so lucky to get that this project appears in our way, and we had the opportunity for that to analyze the elogio in the way every other sculpture should have to be. The elogio had a lot of, from the town hall, a lot of pressure to be restored. It's a symbol, it's more than a monument, it's a symbol of the town, and thousands of people goes every week. It's in a very special place for the town. It's where they used to look far away to the wells of this town, and so it has a relationship with the sea, a very specific, very special. And so when we started, we were so lucky to have this project, and we understand that we could align ourselves in the way that we wanted to restore the sculpture, but we were going to understand how this is like a case study of a real restoration. So we have here two parts of our work. We work basically in work package 3, and that is sample and characterization, and that will go till August 2020. So before, because we have so many pressure of the community on what we were going to do there, we have to do a presentation, and we prepare drawings to explain to the people what the project was about, because everybody was really have little fear on how to touch this sculpture, in how it should be touched. We did characterization with Torroja. They helped a lot. They did all the laboratory studies and helped us to understand what we were looking for, and because in the beginning we didn't really know what was the problem. Once the characterization was done, we came to the diagnosis, and that's very important for us, because that defines what we have to do there. And for us, is one of the basic goals we have achieved with the problem. It's not to apply, it's not like in the other cases, we don't want to apply all the products, but we want to apply the products that are going to help us restore the sculpture. So we have a second phase in which we explain also to the public what we were going to do is first application and also monitoring. We have a lot of problems with the pandemic situation. We couldn't go there. Also the weather was very bad, and we have many problems with that because we couldn't apply or monitor when it was too wet, and the town hall representative was telling me that they have 2 weeks of rain the last 2 weeks. So it's a very special weather and very difficult to monitor. In any case, well, we did this monitor at the end every month too, and we did also 2 applications because we had to monitor again the first one. One of the main problems of the sculpture is the graffiti. There are, you can see in the lower part there, we have a problem with the graffiti, and we got the help of Florence, GACI, to clean the sculpture. We sent them, and they help us also to understand what was happening in the lower part of the sculpture. Okay, so this slide is the conclusion of the diagnosis. in which after the analysis we conclude that the problem of the sculpture was the chloride attack, it was not the carbonization. So in order to deal with this problem, what we have to do is to use the Yucca super hydrophobic product in order to stop the water to go in the sculpture. And also we have some detachments in which we have to deal and to have to reintegrate, to restore it. And so we use for that two of the mortars of the project, which are the product from Florence, the GI3 and the Torroja mortar, which is called M12. One of the first things we did is a map of the sculpture, and this is very important for us so we can monitor in the future and we can keep track of everything that is done from now on. And also let us project all the application and also the monitoring and understand what's happening. If you see, there is like a line, a difference in the lower part of the sculpture, and we didn't understand why was that. And the Florence University helped us to understand that that was done by the cleaning of the graffiti. So we didn't know really if they applied some product that changed the composition or something like that, but finally we found that because they use a water torch to clean, they have eroded the surface of the sculpture. And what we are seeing this is the actual concrete without the patina of the sculpture. Because we had this problem, we addressed it with these two mortars and the water repellent. Okay, so to do that, we choose, first of all, two areas, one with solar exposure and one with looking north without solar exposure. Also, we put some with 2 layers and one with 1 layer. And also because we have this specific problem that is the chloride attack, we did desalted a zone in order to apply, because one of the things we were told to do is to desalt the sculpture. So we are thinking in the restoration to desalt the sculpture and then to apply the Yucca or water repellent. Okay, so this will be the CSGI3 we applied, as you see in the detachment, when you can see a corrode bar. And they are, as David explained, it's very workable and very easy to apply, and with all the time that has gone by, it doesn't show any cracks, so really attached well to the concrete, and is really all the measures we took so that there is no crack or detachment between the solid concrete, original concrete, and this mortar we applied. So we think is really good. What we saw with in this area, which are some detachments, and so there are corrosion inside, and that's why there is a detachment. We saw that there is an improvement of the resistivity, but also it's very little, this improvement, and so and all the areas around these detachments show that there is a very low resistivity. So that means probably that Also, it's not that the touch is corroded in some way inside. So it's necessary to apply the water repellent as soon as possible. Also, the ultra velocity showed a real good improvement. Regarding with the M12 Zika, we use this to seal cracks, and also we use a spring to put it in, and after 18 months it's still in place and it works really well. And we are really happy about it. This color is easy to reintegrate after, and we are talking with our storage on how to reintegrate this mortar. So we have a lot of questions when we start doing this with the storage, putting it, and we have a lot of help from the rest of the team, the Zika team, the UCA University, which by phone told us how to do things, and it was very helpful from everybody. Finally, we did the application of super hydrophobic. Because there are other products in the market, we wanted to test them with a contrast product in order to see if we could get an achievement or there was a difference. Here you see 1 layer and 2 layer in the bottom. That's the UCA product. At the beginning, we were a little worried because it seemed that there was like a signing effect during the first day. The second day, we saw it was really clear where we applied the product. But after a time, it clearly you couldn't see it, so it really matched the color of the base of the sculpture. Instead, the contrast products have problems at the end, and they market a lot more than the Zika products. So, so we are very happy with this product in the sense that they look they look very well in how they match the color of the original base. Well, I just want to okay. I just want, okay. Thank you very much.
Okay. Thank you, Lorenzo, for your presentation, and we have time for a very short question. Okay, so we can, okay, the next contribution is about the Eduardo Torroca Institute in Madrid, and is going to be presented by Ines Lodeiro from CSIC.
Thank you, Gabriela. I'm going to try to look for my presentation.
Thank you.
So. Well, so hello again. As Gabriela has said, I'm going to talk about the validation in our case of study, which was the Eduardo Torroca Institute. Well, in our case, the element that we selected to validate the InnovaConcrete products and the different solution was the car park pergolas. But before the validation, we performed a work about the characterization and the diagnosis of our cultural heritage concrete. For this, what we did was to extract core samples of our concrete And we analyzed the sample in the lab in order to have more information about the type of cement, the type of aggregates that we have in our concrete, the microstructure, the possible presence of alteration products. So with all this info, we're going to have a general idea about the real estate of our concrete. Apart of this, we also use the georadar to try to locate the reinforcements bars in the concrete. We also perform some carbonation tests in order to see also how this element was affected by the carbonation, which, as I have said this morning, is one of the most important causes of decay. So all this info are going to help us a lot about to decide how we are going to perform the validation. So the second step, it was to create a map of damage. So it's quite important to know the pathologies that we are going to have in our elements in order to select which are going to be the best product to apply. So here, as an example, I showed you the different pathologies that we have identified in our elements. So in green, we have previous reparation, previous repairs. In pink, we have the presence of cracks. We also have identified some biological colonization in yellow. We also identified some points of corrosion, some delaminations, and so on. So once we have identified these cracks and this type of problems that we are going to have in our element, the second step, it was the cleaning of our monument. As you can see in this picture, our monument was covered by paint, a white paint, which was an anti-carbonation paint that we needed to remove before the application of the different type of InnovaConcrete solution. So for that, we performed two different type of cleaning. The first one that you can see on the left on the top is the hydro cleaning, the hydrojetting, which consists in to apply water with certain pressure in order to delaminate the paint. And the second one that we chose, it was the chemical cleaning with some product that one of our partners provided to us. And especially we did this cleaning in the tips of the monuments where we detected a higher amounts of cracks. Well, so once we have all the damage identified and we have our element completely clean, the next step it was the application of our products. So in our cases, we have applied 5 different InnovaConcrete solutions. So we have selected the consolidant provided by the University of Cádiz, which is going to help us to recover the cohesion of our concrete. We have used some corrosion inhibitors that are going to be used in combination with the different solution, the consolidant, but also the repair micromortar. We have selected the super hydrophobic product, also from the University of Cadiz, to avoid the water ingress of the elements. So during today, we have seen that the water is one of the most aggressive agents for concrete. And we also have selected the hydrophobic repair micromortar that we have developed. And we have applied this one in cracks and where we have seen some delamination. So we are ready for validation. So here in this slide, I wanted to show you a general idea about the different techniques, methodologies that we have used to validate the InnovaConcrete products. So to analyze the change or the possible change in the aesthetic parameters, we have used a colorimeter that allows us to measure the color and the brightness of the substrate just before and after the application of the treatments. We have also analyzed change in the hydraulic properties before and after the application of the treatments after certain times. For this, we have used the low pressure water absorption, the cast and pipe, the contact angle, the sponge edge. We also have tested the adherence of the different impregnation treatments to our substrates using the peeling test. We have evaluated change in the compactness of our material using the ultrasound spurious velocity analyzed, but also the Smith's hammer. And finally, we also have analyzed the corrosion rate and the resistivity in order to see if this kind of anti-corrosive molecules are are doing their job. So let me turn now to show you some results with respect to the consolidants and the superhydrophobic products. So as you can see in this table, the application of the UKTPS product, the superhydrophobic product, was a success. So as you can see here, we reduce the decrease of the water absorption of around 90% after 8 months of applications. So none of these impregnation treatment, neither the consolidant nor the superhydrophobic products, produce important change in the color. So in both cases we have a delta lower than 5, which means that are completely acceptable. So with respect to the change in the sulfate hardness, we didn't detect any change. So the concrete was perfectly okay. And with respect to the adhesion with the peeling test, we didn't obtain any kind of dust or any kind of product in our tape, which is a good indication that our impregnation treatment is perfectly adhered to our substrate. Well, with respect to the CC repair macromortars, we also tested these in different techniques. Through the ultrasound pulse velocity analysis, we saw that there was an increase in the velocity, the modulus of Young increase, which is a clear indication of the effectiveness of this kind of repair macromortar. With this mortar, using the SPON test, we also test the hydrophobicity, and we observed that after 8 months of application, we achieved to decrease the amount of water up to 80%, and it's going to retain its efficiency after 9 months. And here, through the infrared image, we can see how the repair mortars effectively get less wet than the original materials. So finally, with respect to the corrosion inhibitors, which have been applied in combination with the other kind of treatments, we have seen that there was a slightly decrease in the corrosion rate. And here I would like to point out that also we measure where we have applied the superhydrophobic product, and in this case also we observed the same trend. There was a decrease in the corrosion rate. So to conclude, after a preliminary characterization and diagnosis, we see that we have selected a novel approach developed in the project to validate our monument, our treatments. And in our case, the chemical and aesthetic compatibility, the efficiency, and the durability has been successfully proven by in-situ non-destructive testing in historic concrete. And it's still working very well after 9 months of treatment. And that's all that I wanted to show you. Thanks a lot.
Thank you very much, Ines, for your presentation, and we have time for some questions. Okay, if there are no questions, we can go to the next presentation, which is from about the in-situ validation on Centennial Hall. I think that Christoph should be connected remotely. I don't know if...
Yes, I am. I hope that that you can hear me. I think, Gabriela, that will be better today that I maybe launch the presentation from my computer and
no,
I will have control on it.
In this moment.
It's okay.
Christoph, can you hear me?
Yes, I hear you. Okay. Did you see the presentation or no?
Maybe we have some problems with the audio.
Only with the audio and okay. Okay, 1 minute.
Okay, do you hear me or no?
No, it doesn't work.
Okay. 1 minute. Nie słychać mnie, Mateusz?
Słychać cię tu chyba normalnie, jak
Okay.
can you hear me?
Okay, Gabriele, do you hear me or no?
We are trying to solve this problem.
Okay, Mateusz, spróbuj ty się połączyć, zobaczyć, czy cię słychać, okay?
Okay.
So I don't know if there is any news regarding the. Otherwise, we can switch to the next presentation, and then we will try to solve this problem with the connection with Christoph, and we can present later the Centennial one. Yes, the one on Fleming Stadium. Okay. So now I can present the contribution regarding the Fleming Stadium. Just one moment. Okay, so we can go on with the presentation regarding the Flaminio Stadium in Rome. Okay, just a few words to say that this stadium was designed by Pierluigi Nervi, which can be considered a pioneer in the use of concrete in different ways. He was one of the world's leading exponents of structural architecture, and he was one of the most relevant exponent in the study and use of reinforced concrete. Here you can see some of the works realized by Pierluigi Nervi. Regarding the Flaminio Stadium, our interest on this monument can be justified because this is one of the iconic works of art designed by Nervi. And in the Flaminio Stadium, the concrete was used in a variety of ways, some of them unconventional. We can find large structural frameworks realized by in-situ casting, prefabricated elements, and also the ferro-cement canopies realized on site. The Flaminio Stadium activities were carried out by CNR in collaboration with the Italian Ministry of Culture and with Roma Capitale. This was an additional case study with respect to those planned in the proposal at the beginning of our activities. And so the first step was to collect some samples from different areas of the Flaminio Stadium in order to have representative materials which take into account the different building techniques, geographical locations, and state of conservation. Here you can see some pictures which were taken during the assembling activities. The samples were collected from the canopies, but also from the pillars, which are located in the internal and external area of the Flaminio Stadium.
The characterization of these samples show that we have a great heterogeneity in terms of amount of aggregate, binder aggregate ratio, and porosity. And the matrix was mainly composed by hairline and cement. We also performed different in-situ measurements, and the results show that the damages are mainly due to water infiltration and to the formation of biodeteriogens. In addition, we observe low values of salinity index that confirm the good quality of the pillar and a low risk of decay. It was also observed the presence of rising dampness and detachment. We performed also some in-situ measurements to evaluate the corrosion activities in the pillars, and we observed that in the pillars realized by in-situ casting, the corrosion rate was almost negligible. On the contrary, in some internal area, we observed a corrosion activity from moderate to high values. And on the right, we can see, for example, the radiography of a sample which was collected from the ferrocement canopies, and we observed that the steel grid is still intact, thus confirming the good state of conservation of the structural elements. However, we have to say that we can observe a degradation state which is mainly due to the water infiltrations and to biological colonizations. So, in order to preserve this important part of our cultural heritage, it's important to plan appropriate restoration intervention. And to this aim, it's important to say also that in addition to the InnovaConcrete project, other activities was carried out on the Flaminio Stadium aimed at the conservation of this monument. And so this is important in order to promote the awareness of this monument. In September 2018, the Flaminio Stadium has been listed as a protected cultural heritage site, and this is important in order to prevent inappropriate interventions. Within the InnovaConcrete project, we've organized a workshop in Rome dedicated to the works of art of Pier Luigi Nervi, and in particular to the Flaminio Stadium. And we had about 200 participants from different countries, and in this way we contribute to promote the awareness of this monument. We have to say that several activities were carried out within our project from ICOMOS and from Docomomo. So, I don't know if you have any questions, otherwise... okay. I don't know if there are questions, otherwise we can try to be connected again with Christoph.
Okay, I hope that... So, Gabriela, could you please confirm that you hear me?
Yes, now it works.
Okay, so if now it's okay, so I will also now share the screen and start my presentation. I hope that everyone will hear and see it. Okay? So I would like to present the results about the in-situ validation of InnovaConcrete products on Centennial Hall that we performed with Mateusz Motko and in close collaboration with CNL in the last, I think, 2 years. This is our building, so the building which erected in 1912. In general, this object is few years ago after the general conservation from the outside. That's why the original surface we have only in the interior, and we test all of the products inside. We select several zones where we
where we have the places for application, and we divided our activities into, I think, 4 main parts. So the first one was sampling and characterizations in 2018. In that time, we collect the whole information about the concrete that we have previously and what we also add to the during this test about the aggregates, about the cement, about the. I hope that, do you hear me or no? Is everything is okay? Yes, I hope that everything is okay, so I will continue.
Yes, it's okay, Christoph, we can hear.
So we have the division into 6 zones. Then from 2019 to 2021, we start and finish the crack monitoring in collaboration with RINA. And from the beginning of 2020, we start the product application, and then we start the performance evaluation in collaboration with CNR. We select 6 products to be tested on Centennial Hall. It were consolidants and cement paste and micromortars for crack injection. You can see now the timeline when we start different process from cleaning to then through crack monitoring and product application and then performance evaluation. Because of pandemic times, this performance evaluation was not regular, and as you can see, we divided these activities because of work in 2 groups, so in 2 teams, CNR and team from Centennial Hall, in different period of time. So this collaboration was crucial because we use different techniques. Is an example how we do it in the first and second area, where we test UKT consolidants, where we have no treated area and treated area. We can see on the right side and how to compare it. You can see also the difference in the color after application, and also the cleaning process using water, and then the product application using spray and brush. There were 2 areas, because in the first one we use only 1 layer of UKT product, and in the second we use 2 layers of UKT. The second part was performance evaluation before and after application, and also on untreated and treated areas. We use different devices and different techniques, but I think it's very similar to the other objects, which are the case study in this project. So also PV test, sponge test, peeling test, or colorimetric measurements. As you can see, it was also some of the test was performed in 2 ways, so by 2 teams, and we then compare the results. In the third and fifth area, we apply the TUC consolidants. They were applied also after cleaning process using water and then using spray and brush application. And also similar to TUC products, it was divided into 2 areas. In the first one, only single layer, and in the second one, double layer of the product. And you also can see different measurements techniques to how we evaluate the performance before and after application. In case of crack injection, we also prepare the cracks with air pressure and then with some with the component based on the alcohol to decrease the adhesion. And before we apply the product, we start the monitoring process in one of the places, and then we apply 2 products in the same in the same area because we want to compare the results. So in the first one it was cement paste CSGI 2, and in the second place it was product M4CK. So as you compare, is in the form of H shape. We have two products, and in the area where you can monitor the cracks. So it's the view of the cracks after injection. Of course, this white color, as we know, is only a basic color that could be changed and modified if you would like to match it into the original surface in the objects in the future. And also in the sixth area, we have also cracks that is more than 5 millimeters. So in this case, we also make some kind of preparation and then application of different mortars and cement paste in the same cracks to compare it and to see what is the difference between. And using the strategy which was presented by CNR, we also can compare the results. We have different measurements techniques, but I highlight only maybe 6 that I would like to comment during this presentation. So the color, the compactness, and the water absorption, because in this case we have very similar results made by 2 teams, so by Centennial and CNR. In each of them, we compare the values that we have just from tests, and then try to formulate the similar conclusions. In case of the color, we can see that this coefficient delta E is more than 5 in case of ucatillary, so it means that the difference between color before and after application, so between the untreated and treated area was bigger than in comparison to the areas where we have TUC consolidants, and this coefficient was less than 5. I will also show you the numbers, but in general, if we apply the UKT, after applying of UKT, we saw that the color of the concrete, original concrete, was a bit darker, and in case of TUC consolidates, a bit lighter. But the difference was not significant. So in my opinion, this is a kind of subjective opinion, it's recommended to use it, and the change of the color is not significant. And the second interesting also result was that the compactness, so superficial compactness after application in case of UKT product was, so the results was also changed in positive way. So we can see that there was the influence of the application of products into the structure of concrete. But I think that the most important and most interesting results was in case of water absorption. So in each of the consolidant product, we saw the decrease of water absorption after the application in different period of times. That's why we could formulate the conclusion that after the application, the concrete was well protected against environmental conditions, against water, even if it applied only in the interior of the Centennial hole. But I think that the conclusions is common also for the exterior surface. Some results in details. The first one, the color. So we compare the number L, mainly because it's a kind of the range of monochromatic color, and you can see that the test from left side and from the right side, performed by CNR and Centennial Hall, was very similar. So the trend is the same. It's also a conclusion that if we monitor the evaluation process, we could do it by different teams and also sometimes by different measurements techniques or devices. Here you can see the results about the superficial compactness. So we can see that the velocity also changed, and after application of UKT lower, it increased in comparison to the first value more than 10%. And finally, the results for water absorption, as you can see, if we use sponge test, contact sponge method,
we can see that after application in different period of time, in each case we decrease the value of water absorption. So I think that we will have the similar effect that in one of the previous presentation David showed us in case of Kaunas. So also we have the significant decrease of influence of water into the concrete. So here you can see in this table the results performed by CNR, and in this case results prepared by Centennial Hall. So the similar trends, maybe a bit different values, a bit different techniques and operators, but the similar trends, and I think that it's crucial. So to sum up, I think that maybe these four main conclusions are important to underline. So the first one, I think that is a kind, maybe a bit objective opinion, but after application of both consolidants, we see the change of the color, but it's not significant. So I think that it's recommended to use it, including some conservation recommendations. Interesting conclusion regards the superficial compactness, which was observed after application of one layer of UKT treatments. And the third conclusion, I think that the most important, that the application of both InnovaConcrete consolidants, so UKT and TUC, caused significant decrease of water absorption. So in this case, this effect can be due to the filling of the pores by the treatments and has a positive influence on protection of concrete against water and corrosion against agents penetration. And finally, the fourth conclusion, which was defined also by Irina, that after permanent monitoring process of crack of cracked which was less than 5 mm, after M12CK mortar application, we observed that this product could stabilize this crack behavior. Thank you very much for the attention.
Thank you very much, Christoph.
The connection was okay and you hear everything. Thank you very much.
We have time just for a very, very short question. Otherwise we can... okay, yes, please.
Thank you very much. Thank you very much. So I have a question about the, let's say, size. So what was the meter square of this sample? Do you think the size of this space was representative enough? And you didn't mention its exposure to sunlight or weather. It seemed like it was a bit under the roof. Could you explain a bit more about the size of the sample and its exposure to weather conditions?
Yes, the size was, I'm not sure exactly the value, but the size was about 50 per 50 centimeter. So it was a kind of rectangular shape in each of these areas, 4 areas, I mean. And if it's representative for the whole building, that was the question. Maybe not exactly, because in Centennial Hall we have concrete, which was, we have many types of concrete. So another one was for the interior walls, another one for the main structure like ribs and rings, another one for exterior. So I think that in general the results of performance evaluation of application of these products are the same, but mainly in case of the porosity of the concrete, it should be, of course, the test could be, of course, would be repeated in different type of concrete. But in case of the influence of exterior conditions like environmental conditions, so I talked at the beginning of this presentation that this object is after renovation, so it was no opportunity to make this test on the exterior surfaces.
Okay, thanks. And together with Oana, we prepared just
two slides to summarize the final conclusion of the in-situ validation activities.
So as regard the protectives, so the UKTPS was applied on 4 monuments, the superhydrophobic product UKTPS on 2 monuments, and the UKTPS applied by plasma only on 1 monument. And however, all these products, the first 2 ones, confirm their superhydrophobic characteristics for all the monuments, and the UKTP applied on Torricella Pellinia only of 5 treatments, this kind of 5 application of plasma. The color variation may occur, but is depending on the type of concrete, and it's not always a drawback. While regards the consolidants, the 2 ones that have been tested, one on 5 monuments and the other one on 2 monuments, both showed improvements in the hardness and compactness. The color variation was generally not significant, and the water absorption was reduced in both cases of the consolidants. And sometimes in some case studies, the superficial cohesion was increased. While regards the corrosion inhibitors, the first one was applied on 3 monuments, the second one with 2 on 1, and the last one also on 1, the Torricella Pellinia. A slight slowdown in the corrosive phenomena progress was observed, and no color change in the case of the first product. They may improve the hardness, the compactness, and the superficial cohesion, and the water absorption capacity was reduced. And as regards the mortar repairs, the one with asterisks was continuously monitored. They seems to stabilize the crack and to reduce the crack depths, and the improvement of the crack depth was noticed. The Mainz mortar is suitable to fill micro cracks. No significant in shrinkage, adhesion problems, and fissuring were noticed with the photographic documentation. And now the remarks and open questions will be presented.
Yes, just to summarize, within this project we have the possibility to define protocols, for example, foam cleaning, to apply the products developed by CSGI on the different case studies. It was possible to define monitoring protocols, and so to study the behavior of the products that have been evaluated to help, for example, in the selection of the most appropriate conservation treatment depending on the monument. So thank you to all the partners that contributed to this activity. Thanks a lot.
Thank you very much. And we are continuing with the last round table, so please, I ask the speakers to come here. Well, first of all, I want to apologize for the delay. We have been accumulating delay along the day, and some of the speakers have to go very quickly to get their train, their transportation. So,
Yo tengo 5 diapositivas, si me dejáis.
Si arranca si quieres.
Me tengo que ir quitando.
¿Tienes ya preparada?
¿Cuál es la tuya?
Excuse me. So, well, when we designed the program of the meeting, we want to talk about something about the future, you know? What to do after the project, what to do with the results, what we are doing, other things that we are doing during the project that have not to be with InnovaConcrete, no? And just to know other things that the partners are doing, no? And also give the opportunity to talk, to be included in the program, and some of the important people of the project that were not participating. So this is very special for us
for the two American partners that we have, the Argentinian partner and the partner from the USA. They have been a very important partners in the InnovaConcrete consortium, but the budget they have is no budget for the partner of the state, because the European Commission do not allow, and just a symbolic budget to the partner in Argentina. But also we have also the contribution of partners that are not officially not partner in the consortium, like the City Hall of Gijón. We have a strong support of the City Hall of Gijón, and he is not a partner of the project. He's not receiving funding, but we cannot do a lot of things we have done in the project without their support. So we were also very interested in them to come here to represent all the people that have give support to the partners, no? And also other people that have been participating in the project in an indirect way, because the face we know from Ines in the consortium is David, but also Jose Antonio has give a lot of support to us. So, well, I'm not going to waste more time in this introduction, just to say that the round table is composed by Miguel Barrero from the City Hall of Gijón, Luis Chillida, very well known for the consortium, Luciano Hernandez from CIPEC, from Argentina, that is also well known in the consortium, Paul Godet from WGA from the United States, José Antonio Martín Caro from Ines Ingenieros, y Ramiro García from SICA. It was coming from SICA, Michel Donadio, that is also a person from SICA that helped us a lot in this project and this moving and pushing inside the SICA to continue the collaboration with the partners of InnovaConcrete after the project. But at the end he couldn't come, so Ramiro is going to intervene in the round table. So what we have talked during the lunch is to do a first intervention of 5 minutes, a short intervention of 5 minutes of each one, and then continue when the people has to leave. But José Antonio Martín Caro has to go just in 10 minutes. He have the time he needs, because he's not going to be long, because if not, he's going to lose the train. So, José Antonio, the floor is yours. I'm going to be there doing signals if somebody talking more than José Antonio, you have all the time.
Well, no, only 5 minutes. I have 5 slides, but only one idea. Okay, thank you very much. It's good to be in Cádiz, especially with good friends. Well, I will try to answer one of the questions that arise, which is the future of conservation of historic concrete in the near future, no? But which is the future? And I think it's really challenging, no? I will try to explain myself. We've been used to work not in research projects, but also in professional projects, in streets projects, with elements that belongs to heritage, you know? Most of them, especially during the 20th century, they were related, well, to, I don't know, museum, religious, old buildings, all elements, castles, walls, and all of them were built mainly in masonry, mud, maybe wood. Then the steel appears in the 19th century, so we still have a tradition working on that. The main objectives of those projects were improvement the tourism in the area, for example, to reaffirm the cultural and historical identity, but also, and this is very important, to improve the infrastructure operational need, no? And this is one thing that I'm going to talk about in the near future. But now things have changed. I mean, especially in the 21st century, industrial heritage, they have another group which is civil work heritage. And there are plenty of work to be done in that sense. And most of the elements, imagine bridges, dams, are made of concrete, okay? So for example, these are examples of projects that we've been involved. This is the Fort George rehabilitation. This is in Grenada, in the Caribbean island. Again, let's say it's a classical heritage project with the World Bank. Masonry, more in most of the time, so we still have a knowledge of this, how to improve and to repair these traditional materials. This is another one in the north of Iraq. In this case, it was with the UNESCO. Again, masonry, well, not masonry, in this case was mud and adobe, which is a special behavior. In this case, the main objective was to create a cultural identity of this part of the earth. This is another one in Haiti. Again, masonry. But what about this? I mean, we have a lot of bridges. Bridges, they have their own values, their own heritage values, and this is really important. And this is not only technological values, no? I mean, it's not that they were, for example, pioneers of some construction method or analysis method. They have their own singularity, technological singularity, but bridges are places where a lot of things can happen, no? They are linked to the citizens. It's the way back to your house. It's places where you have a photograph. It's places, many bridges appear, for example, in a lot of films. And there are places that people go there to do, well, in this case, for example, this is the Viaducto de la Calle Belén. People go there to commit suicide. I mean, it's a very special place in Madrid, and it's linked to the cultural part of the city. And we have plenty of them. And you can now, we have not only local administration, public, local, national, and even international administration are worried about it, also private administrations. So we are going to have a lot of work dealing with this special heritage, which is the infrastructure heritage related with concrete. And I think that's why it's very challenging. We have a lot of work to do, and that's why this type of research projects have a lot of sense. And that's all. Thank
you. Thank you, José Antonio, for being also so brief. Well, it's time for Luis. Luis Chillida. You can talk in Spanish if you prefer.
Bueno, pues aprovecharé para hablar en castellano, que creo que me expreso mejor que en inglés, pero entiendo el inglés y lo hablo, pero... Bueno, a mí realmente mi intervención va a ser breve, pero sobre todo yo creo que en el momento que me llamó Lorenzo para poder participar en este proyecto europeo, pues nosotros somos una familia, somos una empresa, y de alguna manera desde nuestra fundación pensamos que sería muy interesante lo que iba a pasar. Generó unas expectativas y realmente en la primera reunión que tuvimos en Bruselas hace ya 4 años o por ahí, se generaron unas expectativas en mí que creí que eran muy altas, y lo que he comprobado es después de estos 4 años que se han superado con mucho. Yo realmente, primero, una de mis reflexiones es que me ha hecho creer mucho más en Europa. Yo siempre he defendido Europa y la unión de la Comunidad Europea, y creo que este tipo de proyectos nos ayuda a ver que al final somos muchos colaborando en algo, y es algo que es de todos y que la comunidad al final lo que promueve es este tipo de actividades, y realmente me ha parecido que ha sido algo que me ha sorprendido y que me agrada mucho. Y luego yo creo que hay una serie de cuestiones que para mí, claro, son muy importantes en un sentido mucho más moral que otro. Nosotros, como descendientes de mi padre, como sus hijos, lo que defendemos es un derecho moral de nuestro padre, a que las cosas se cuiden, se hagan bien. Pero mi padre fue un artista que estuvo muy interesado en la obra pública, ¿Por qué estaba interesado en la obra pública? Mi padre desde los años 50 tuvo muchas presiones de su galería en París para que hiciese múltiples de las esculturas. Su galerista le decía: Eduardo, eres un artista muy lento. Como no hagamos múltiples de las obras, va a ser muy difícil que la gente pueda conocer tu trabajo. No vas a poder estar en muchos museos o en muchas colecciones. Y bueno, mi madre, que al final mi padre le tenía el agua a mi madre, que era la que se ocupaba de casi todo, menos de hacer las esculturas. Y mi madre al final le convenció a mi padre para hacer una prueba el año 57 y le dijo: Eduardo, no puedes decir que no a algo si no lo pruebas primero y ves lo que sucede. Y entonces, en ese año 57, mi padre eligió 6 esculturas suyas, de las cuales creyó que se podía hacer un molde, y se hicieron 4 copias en bronce de cada una de ellas. En el momento que esto pasó en París, en un atelier de París, cuando estaban hechas, les llamaron y fueron mis padres a verlas. Y cuando mi padre abrió la puerta de ese atelier y vio la obra original y las 4 copias al lado, lo primero que le dijo a mi madre fue: Pili, esto parece una zapatería. O sea, no le entraba en la cabeza. Dice: ¿eso qué tiene esa obra de verdadera? Pero para mi padre una obra verdadera es la que le había trabajado, la que le había sudado, la que le había hecho. Lo otro era simplemente una copia. Muchas veces decía: probablemente mucha gente las verá y pensará que son obras mías igual que las demás. Dice: pero sin embargo yo cuando las veo que no son lo mismo. No es la obra que yo he hecho, simplemente es una copia. Entonces su honestidad le hizo decir que jamás en la vida volvía a hacer eso. Y fue a hablar con la galería y dijo: nunca más en mi vida voy a hacer esto. Y el galerista le decía: Eduardo, esto va a ser muy malo para tu carrera, la gente no va a poder conocer tu trabajo. Y mi padre le dijo: pero es que lo que no te das cuenta es que tú me estás proponiendo que yo multiplique las esculturas para que el público en general conozca mi trabajo. Y le dijo: y lo que yo pienso es, ¿por qué no multiplicamos a los propietarios en vez de a las esculturas? ¿Qué hablaba mi padre el año 57? Hablaba de la obra pública. El hormigón, ¿por qué llega? El hormigón, como ha dicho Lorenzo, los proyectos que hay llegan cuando en la obra pública, pero para mi padre una obra pública era trabajar en función de un lugar. Una escultura es algo que se relaciona con todo su entorno. Por lo tanto, la escultura tenía que tener una escala adecuada. No puede ser ni más grande ni más pequeña. Ese pensar esa escala condicionaba los materiales. ¿Por qué llegó el hormigón? El hormigón llegó porque con el hierro que trabajaba había escalas, había lugares en donde está el elogio del horizonte, en el cerro de Santa Catalina. Por muy grande que intentes forjar una escultura en hierro, nunca va a ser la impresión que genera el hormigón y el volumen que se puede hacer. Entonces, por eso el hormigón llega en ese momento en el que mi padre, a través de la amistad que tenía con José Antonio Fernández Ordóñez, que aparte de un grandísimo ingeniero, era un grandísimo amante del arte, y bueno, pues tenía mucha amistad, fue cuando empezó a pensar en esa posibilidad de un material en el cual podía llegar para obras públicas a unas escalas que él las tenía en su cabeza, pero que no era capaz de llegar. Claro, ese trabajo, ¿qué suponía? Claro, mi padre, el trabajar el hormigón no era una obra civil, como ha dicho Lorenzo. Él quería ver qué tipo de hormigón hacían, quería experimentar. A mi padre, como decía él, las cosas tienen que suceder en el momento, en el presente. No le gustaba saber lo que iba a hacer. Hacía pruebas, variaba, cambiaba. Claro, los hormigones que hacía, cada uno es diferente. Si habéis visto las diapositivas, veréis que ninguno es el mismo. Todos son hormigón, sí, pero cada uno es un hormigón diferente. Así que, bueno, eso sobre todo yo es agradeceros a todos, sobre todo a la universidad, que ha sido la gran artífice de este proyecto, a la Comunidad Europea por su apoyo, bueno, al Instituto Torroja, al Como, y a todos los que han hecho posible que esto se haga y que, bueno, formando este equipo yo creo que vamos a conseguir, no solo para las obras de mi padre, sino que el hormigón pues se pueda poner en su lugar y se pueda conservar. Así que muchas gracias.
Muchas gracias, Luis. Algunos no tenían activado la traducción, se lo han perdido, pero ya se lo contamos después. Bueno, Miguel Barrero, del Ayuntamiento de Gijón, si lo quieres hacer desde ahí o desde aquí, como tú prefieras. sin ningún problema.
Hola, me quedo aquí porque voy a ser muy breve, soy el que menos sabe de hormigón en la sala, con lo cual tampoco tiene sentido que me dilate mucho, ¿no? Yo vengo simplemente porque quiero agradecer la inclusión del elogio del horizonte en el proyecto Innova. Es algo muy importante para la ciudad de la que vengo porque el elogio es más que una escultura. El elogio es la escultura de Gijón, ¿no? Desde su inauguración en el año 90 hasta hoy, 31 años después, ha pasado un proceso que también resume un poco la percepción del hormigón como materia prima del arte público, ¿no? En tanto que su inauguración estuvo acompañada de una polémica importante en la ciudad, fue una escultura muy contestada desde varios sectores y hoy, 31 años después, es una escultura a la que nadie quiere renunciar. Hay un ejemplo muy bonito y muy reciente. Cuando el año pasado acabó el confinamiento y por fin nos permitieron salir a la calle, la mayoría de los gijoneses fue a buscar el elogio, ¿no? Han convertido esa escultura en una especie de símbolo, en una especie de anhelo, que fue lo que fue en su momento cuando Gijón atravesaba una etapa difícil de su historia, y el elogio vino a marcar un punto de inflexión a partir del cual la ciudad caminó hacia un lugar mejor de alguna manera, y casi por azar confluyeron la vocación del artista, de Eduardo Chillida, con la vocación de la ciudad, y ambas se encontraron en ese punto afortunado que fue el Cerro de Santa Catalina, ¿no? Como bien sabe Luis, el elogio es un símbolo que desde relativamente pronto empezó a dar problemas, ¿no? Por su ubicación está sometido a la acción del agua, de la lluvia, del mar, del viento, y también de manera secundaria pero insistente, vamos a llamarlas intervenciones artísticas espontáneas, que influyen en su factura, ¿no? Nos resultaba muy complicado dar con un diagnóstico certero y con una metodología adecuada para solventar esos problemas, y este proyecto ha permitido que por primera vez tengamos tanto ese diagnóstico completo como una herramienta que va a servir para paliar todas las dificultades que acarreaba su preservación y su mantenimiento. Es verdad que Eduardo Chillida era partidario de que la naturaleza fuera desgastando, vamos a decirlo así, sus obras, pero creemos que ese desgaste tiene que retrasarse o por lo menos modularse de manera que tarde en producirse. Por eso quiero agradecer a Lorenzo especialmente su trabajo. En enero empezaremos a trabajar en la limpieza integral del elogio y en la aplicación del método salido de este proyecto para su preservación. Y nada más, simplemente agradeceros el trabajo y el aplauso en realidad es para vosotros, que sois los que habéis estado trabajando en esto durante estos años, ¿no?
Muchas gracias, Miguel, por tu brevedad. Se nota que eres periodista y sintético y al grano. Además, has dicho cosas muy, muy interesantes. Bueno, el turno es ahora para Luciano Hernández, nuestro argentino favorito.
Gracias, Fernando. Bueno, buenas tardes a todos. Mi nombre es Luciano Hernández, soy de la provincia de Santa Fe, en la República Argentina, y me invitaron a hablar sobre las pautas y condicionamiento de la restauración del hormigón. Lo había seccionado en dos partes, en la parte teórica y en la parte práctica, pero por razones de tiempo, lamentablemente vamos a dar una, y si están más o menos no aburridos, vamos a dar la segunda. Supongo que es esta. Sí. ¿Está? Aquí la paso.
Sí, la pones aquí y la pasas con...
No vamos para poner.
Con eso le das a este y ya está. Acá, espérate,
Bueno, traté de ejemplificar los retos que significa y los beneficios que trae la aplicación de un hidrofugante y un consolidante en piedra. Acá hay que hacer un punto de inflexión para reconocer un factor que sucedió en Argentina, que fue un acontecimiento histórico importante. En el año 1880 hasta 1910 hubo una inmigración europea abundante en la cual se caracterizaban los españoles y los italianos. Esta gente traía consigo el bagaje de conocimiento de otras tierras y eran especialistas en mampuestos y maestros albañiles. El problema que hubo en la Argentina fue que conseguir piedra para construir los edificios o restaurar o reemplazar la fachada era demasiado costosa y tuvieron que formular o inventar situaciones que imitaran la piedra. De ahí surgió el revoque símil piedra, que es muy conocido en este país. Bueno, estos son algunos ejemplos del antes y el después de intervenciones con símil piedra. Este es el anterior, el cual tenía una patología muy determinada en una obra de Santa Fe, la Casa de la Cultura, así como quedó terminado y cómo se procedió a la hidrofugación. La hidrofugación es sumamente importante porque afronta las causas patológicas de superficie, las cuales denotan la lectura del edificio. En definitiva, la lectura del edificio es lo que está grabado en la memoria colectiva de la población y es lo que lo representa y lo que le da valor a cada obra en particular. Este es un aspecto interior de la misma casa, esto es solo anecdótico, para demostrar el antes y el después, y el desafío fue ayornar el edificio con equipos de aire acondicionado, instalaciones nuevas y cableados de tecnología moderna. Este edificio es de 1910 y se está dando un reuso importante en este momento en la provincia de Santa Fe. Este es otro aspecto de los interiores, una escalera que se terminó de restaurar completamente y además tenía problemas estructurales. Bueno, este es un mascarón, es una obra que pertenece a la Embajada de Estados Unidos, donde la carbonatación del símil piedra y la entrada de humedad por porosidad completaron el problema de desprendimiento que tenía parcial este mascarón tan lindo. Esta es una representación de la cara de Baco, está en la Embajada de Estados Unidos en Buenos Aires, y se hizo un trabajo minucioso de retiro de los hierros que provocaban la situación patológica que ustedes pueden ver. Se lo completó, se lo veló, se le hizo un decapado de ácido para contrarrestar el efecto nuevo respecto al entorno, y fue sumamente importante la hidrofugación para evitar a futuro los mismos deterioros que esta patología presentaba. Este es otro caso similar, este es un mascarón de una china que se le dice, que la china generalmente es la mujer del gaucho y está representada en esta imagen. También la misma patología, tenía problemas de fisuración, carbonatación, y se producía un efecto cíclico y acumulativo que iba oxidando la armadura y desprendiendo a su vez cada vez que cambiaba de volumen. Se hizo el mismo trabajo, se retiraron los hierros, se completaron las partes faltantes y se procedió a un velado con la hidrofugación correspondiente. Esta es una de las pocas obras en piedra que hay en la República Argentina. Este es un arbotante neogótico de la Basílica Nuestra Señora de Luján, que está ubicado en la localidad homónima, Luján, de la provincia de Buenos Aires. Por motivos de esfuerzos mecánicos y situaciones no deseadas, se provocaron las caídas de los roleos de la cresta superior del arbotante. Lo que se hizo fue un trabajo de reconstrucción y anclaje, la reparación completa, la consolidación y la aplicación del superhidrofugante. Este es otro aspecto de la misma basílica, donde la porosidad de la piedra lograba imponer situaciones patológicas irreversibles y se terminó restaurando con mortero, aplicando el hidrofugante posterior. Este es otro ejemplo de un escudo. Esta es la foto anterior. En la concha superior, donde está este ornato, hubo que restaurarlo, retirarlo y sacarlo. Volverlo a colocar, restaurar la superficie y también termina con el hidrofugante para evitar la absorción de agua. El agua provoca generalmente todas las patologías. Bueno, esta es una vista posterior del ábside de la misma basílica que está construida en piedra, donde se hizo un trabajo importante de limpieza piedra por piedra y tomado de juntas, una consolidación. ¿Terminó? 30 segundos. Y se aplicó el hidrofugante. Este es el famoso edificio Cábana del año 1936 en la Argentina, también revestido en similpiedra, donde se hizo un proceso de lavado y de hidrofugación. Bueno, esta es la Universidad Nacional del Litoral, con el conjunto escultórico que ustedes pueden ver acá. Está complementado con una serie de ornatos que estaban totalmente destruidos. Para hacerla corta, muestro la terminación como queda. Y esto sí realmente requería la colocación de un similpiedra eficiente donde no permitiera que volviera a suceder lo que pasó en su momento, que era esto, que la acumulación de musgo, líquenes y plantas y contaminación urbana que el edificio tenía por estar en una zona sumamente transitada. Listo. Esto es la comparación del antes y el después. Ya me voy. Y quedaría la parte teórica, si es que hay tiempo, después la damos. Les agradezco mucho, muy amable por su atención.
Muchas gracias, Luciano, por contarnos tantísimas cosas que tienes tú, tu experiencia, que ha sido muy importante para tener en cuenta la parte práctica en lo que nosotros desarrollamos, ¿no? Bueno, es el turno de Paul Godet. It's the turn for Paul Godet, so the floor is yours. You can do it from there or from here.
Thank you. I did want to, before I start, thank Maria and Fernando, number one, but also Gunny Harbo and Fernando, number two. And I apologize to the two Fernandos for continuously emailing to the wrong one over time. But I did want to congratulate the concept and the approach to this project. Over the years, it's very similar to the way we approach things at the company I come from, which I've been at for about 40 years now. But we take the scientific approach, which I think is the correct way to do it. The constant questioning, the looking at things from a skeptical point of view, always trying to improve, and then modification. And so just when you get it right, you reassess it, and then you repeat that analytical process. I think one of the best things you've done during the course of this, and I think it should continue, is that grouping of scientists, conservators, architects, engineers, material scientists, and that it goes on and on and on. I think you have to get the different perspectives. Certainly, I'm an engineer, and the way I approach it, and some of the other engineers, is totally different from a conservator's point of view, or an architect's point of view, or a material scientist's point of view. As we all know, that a project, the most important part of a project is the part you know best. And you tend to give a lower level of concern to the other ones. And once again, what I've learned over time, and I think is what's been shown here, is the art of collaboration, searching out the negative question and trying to improve it, tailoring things to the project. And I believe that is what's taking place in conservation of concrete. Over the years, concrete has been delegated to, well, how did they do it with stone? How did they do it with masonry? And some of the repair techniques have been topical or superficial, but I think we're probing more deeply now. And I think we're looking at things from a more practical viewpoint, and how do we improve it? Once again, constantly self-criticizing the approach, changing it for each project. at least, and that's what I've seen here. And I think we need to continue to do that and improve and not stay within our own areas of expertise, but also expand that to talk to the scientists, to talk to the petrographers, to talk to the material scientists and how different things are affected, because we all carry different perspectives, we have different experiences, and I think at the end of the day, we will be better off for doing that. One thing I really was glad to hear today, and I think at least helps me, is I have to understand how it's repaired, how it's restored. Can it be done? Certainly you can ask for anything, but can it be done? And I think that's really important to bring in. What you've done is you bring in the manufacturers, you had them participate and tell, well, we can produce this, we can make this, but is it practical? And I think then doing the testing and once again being skeptical about it, I think is very important. And in my view is, I think going into the future is certainly some of the results that have come up here will be criticized. That's good. You don't want them dismissed. You want them criticized, you improve, you modify, and then you move on from there. And I think that's what will happen next is, as some of these products are used, I think the quickest way forward is to use them on less important structures and monuments. Get them out there now and get them in areas where you can, where they'll have a really difficult environment to work in. I come from an area where the environment's very difficult. And things fail very quickly, which is good to understand how things will work in the future. But that really gives you a quick perspective on how things can fail in the future and how they can improve more importantly. So once again, test, mock up, design, and then install and then monitor. Just which are the major goals laid out in the Cadiz document, which I think does a nice overview of the process moving forward. But I once again want to congratulate this group, and I really admire that push towards collaboration and searching out skepticism and taking in that advice moving forward. But that's my view of the future for the InnovaConcrete project. But thank you and good job, everybody. Thanks.
Thank you, Paul, for your nice work. Now it's the turn of SICA. Ramiro Garcia is going to give the following talk. I have to say that, well, all the partners of InnovaConcrete are important, but we have a favorite partner, that is SICA. I think that well, the SICA put the project in a different level, and the implication of SICA gives credibility to all the things that we are doing, and this is very important for us and very important for the project. But I love you all.
Extremely appreciated for these kind words, being honest. I'm on behalf of Michel Donadio. He's at corporate level responsible for these technical departments, and more specifically in this area of protected concrete, okay? Firstly, it's gonna be short, I promise, and not too emotional, but quite. So my point here is to make a short review, what about has been our key learnings, okay? As human being, as also as company, okay? And I would like to start with this proverb, this saying that if we go alone, we go fast, but together we go far. And this summarized very well the feeling that I got after these 4 years with a pandemic in between, where we were acquiring very, very complementary and very diverse knowledge and background within this project. And that was, since my humble perspective and analysis, the most incredible contribution of this project is because of what has been the best approach. From my humble perspective, is exactly this connection between very, very diverse knowledge and backgrounds. The humanistic, the more close to the preservation, historical background, understanding of the deep connotations of every single monument and the technical background where we were treating them as materials without any kind of basis from that perspective, but with a magnificent understanding all the chemical bases, phenomena, pathologies. So this merging process took us a while. That was extremely powerful to achieve exactly this. And to summarize, we were not only 11 countries, but many different nationalities, background and knowledge, extremely powerful, all of them together. And this is a summary. So you say here cultural heritage, stakeholders, certified bodies, manufacturers, tool models, so extremely diverse. That was, from my humble perspective, the most the valuable strength of this project. The challenges that we see, we can summarize quite easily. There is only one challenge, which is the sustainability. That is a challenge, and at the same time is the unique opportunity to demonstrate ourselves that we can really approach in other ways. And yesterday there were very interesting speeches and deliveries talking about this. Here Mr. Cox, here Mr. Haspel, sorry for the pronunciation, my German is awful. Anyway, what we start to notice is we need to have a deep understanding what sustainability means to approach in all the different ways that we can contribute on that. All colleagues from RINA were summarizing this under this life cycle analysis perspective, which is contributing in this holistic approach to understand every single impact connotation that we can really bring on the table. We, as project colleagues and co-workers, we demonstrate that sustainability as a main driver of contribution within this sustainability concept. We can contribute significantly in the evolution, preservation, conservation, and improvement of structures, concrete structures, but extension, natural extension for all the kind of sensitive materials, silicon based, but also limestone based, so we have many tools to work with. Upon this, we, in my case, at least in my case, as a technical person, we have a new dimension, what concrete means. What, from a social perspective, as Gemma or Manuel were explaining within these 2 days, how one structure can influence people, can feel people proud of. So we need to bear this in mind in every single aspect. And this is what is challenging us to demonstrate that we can contribute significantly to this sustainability. But I'm fully committed, I'm fully convinced that whatever it should take, we are gonna do it, okay? Maybe it take a while, we don't know, but it will be there, okay? And that's all from my side. I hope that it's gonna be short enough, but anyway, this is the end, okay?
Thank you to all. So if anybody wants to talk and say anything else, have 30 seconds to say. If not, we are going to continue with the program because we have also to give a prize. And
I would like to say thank you very much to all the people here in the table. You take part in you are a very important part in the InnovaConcrete project. I think it's you have in all the workshops, in all the meetings. In the case of the SICA, this was the main important pillar in the project. And in another case, thank you very much to Paul. Thank you very much, Luciano, because you are not really, you don't have funding in the project, but that's very, very important. Your advisor, your ideas, and I hope that this is the beginning of the next collaboration in the future. And in the case of Gijón, the city of Gijón and Chillida Foundation, it was really important for us because Gijón was amazing. When we organized the workshop in Gijón, It was really amazing. The people, media, newspaper, journalists, they were very close to the InnovaConcrete project, and this is really important for us. And it was very, very happy for InnovaConcrete project that Chillida, Luis, and the foundation take part in this project, because I think the awareness of concrete, since awareness regarding to concrete and regarding to historic concrete was carried out. Thank you to Chillida, and thank you to people from Gijón, because it was a pillar for this awareness part of the project. Thank you very much. Thank you. And thank you. And we are now the closing ceremony, and we have here to the winners of the prize. And I would like to ask for the help for the Ramiro, because he's in the chair of the exploitation committee, and please Gani Harbour, because I don't know if Gani Harbour is here. Yes, okay, please, to close in the ceremony, and also to Alatau, she is the vice chair of ICOMOS. Please go to the table, and during this close ceremony, we are going to give the prize to the winners of the photography contest. We organize a contest for each workshop, for each city that we organize a workshop in InnovaConcrete, because this is a way to integrate the people of the city in the importance, in the significance of the historic concrete. In this case, the contest was organized regarding to the historic concrete monuments in Cádiz region. And we have two winners. And first of all, before the closing ceremony, we are going to send the prize. I would like that to send the prize to the winners. Please, do you have the prize here? Okay, say thank you. And we are going to upload here, I hope, the photographs, the winners. And the winner for the best picture is Isabel Zambrano, I'm sorry. Isabel, por favor, ¿estás tú presente en la sala? Muy bien. Okay. And this is the picture regarding to the winner. Okay, and yes, I think if you put. Yes. He's going to speak English, okay? So.
Okay, hello. When I heard about this contest, I tried to make a photo, and I tried to project the easy treating life in comparison to the technology. I think I really made what I wanted. But now, as I was here and I heard all these professionals, and I feel very proud about
all these technicians can't keep this for future generation. So really I feel very, very generous with these technicians can do this for the rest of the people and for our future young generation. Thank you very much.
So thank you, Isabel. And now the second prize, the second prize is for the picture with more likes in Instagram. And the winner is Agustín García de Sola Márquez. Congratulations, Agustín. I think Agustín is here. En español, si tú quieres.
Nada, solo quería daros las gracias por la oportunidad, a vosotros, a los que me han votado por haberme votado, y quería hacer mención también a José Luis Suárez Cantero, que es el autor del diseño de este complejo parroquial. Y nada más.
What is the complex? What is in Cádiz?
En Cádiz.
En Cádiz, es en la ciudad de Cádiz.
Sí, sí.
El nombre de la...
se llama Parroquia de San Servando y San Germán.
The name of the church is San Servando San Germán. Fernando, the wedding of Fernando was in the...
Servando.
The wedding...
Servando.
No, la boda. The wedding of Fernando was in this chapel, yes. The wedding. And he says thank you very much. And
Y nada más.
Y nada más. Okay, thank you very much. Gracias.
I would like to congratulate you all again for a very, very interesting project, and there's a lot that has been said about concrete and 20th century heritage and masters, but I would also like to emphasize what we have achieved is, you have achieved actually, is this intergenerational dialogue and the cooperation with the universities. It's, of course, first of all, University of Cadiz, but among the partners there are several other universities, and this master-apprentice dialogue and giving the chance to young researchers is really, really very important. And I sincerely hope also from behalf of ICOMOS that many of these young researchers that we have been listening today will join ICOMOS family in the near future. But I actually was intending to target this to my colleagues in the ISC 20 ICOMOS Scientific Committee, but I'm happy to share it with wider audience and to talk about another initiative of ICOMOS that we had just recently and which is involved directly with universities. And it was a workshop in August dedicated to heritage alert initiatives. And as you know, UNESCO, there's a lot of heritage that is constantly in danger, and UNESCO has a mechanism called World Heritage in Danger, and ICOMOS has a mechanism that is called Heritage Alert. And it is not as much used as it could be, because it's a very, very good tool to do it. And wondering why it is not as well used as it could be, we organized a student workshop. And these are some of the initiatives that ICOMOS has on heritage, different heritage alert activities. And we also asked a master student from Cottbus Brandenburg Technical University to analyze the effectiveness of heritage at risk initiatives of ICOMOS. And as you know, we work all on voluntary basis, but a huge number of ICOMOS members are university professors or teachers. And so the idea to test ICOMOS activities through universities was also partly inspired by the fact that we could showcase at our workplaces in the universities what we do in ICOMOS, and at the same time also to profit our daily work. And this summer school had several goals. One of them was, of course, training new generation, like every initiative with universities. But it also, we wanted to get the practical outcome, and the practical outcome was the knowledge on how well ICOMOS activities are known, feedback on the efficiency of ICOMOS activities, and to get really practical help in updating ICOMOS website and assistance in identifying gaps and new target groups. And for this project here, it has been mostly the students of architecture and engineering, and in this workshop that I'm talking about, we more had the students of heritage studies and architecture involved. And in quite an easy manner, we managed to get 14 universities around the world. We had all parts of the world represented. This is the list of the universities. Here are the tutors from different universities and also ICOMOS members. And what we did was we gave the students, first of all, they had a good round of presentations from ICOMOS members, and we had a really very good feedback on what the students really liked was the enthusiasm of ICOMOS members in explaining what they do as their voluntary work. And as a return, the students had to fulfill then 2 exercises which were tutored in a week's time. And one of them was to take an existing heritage alert that ICOMOS has made, and some of them are quite fresh and the others were a bit older ones, and they had to indicate the problem, why it was made, and then we asked the students to go through public media databases and social media databases, not to run for their really deep expert knowledge, but really to the public knowledge on what we are doing and what is known about the problem, what has called the heritage alert, why we are alerting the world that something is wrong with one or another site. And the outcome was I would say, rather educational also for ICOMOS, because in some places we were referred to, and the other places there was not a complete silence, but still the general public did not know too much of what the question was about and why the experts complained. We also asked the students to identify in retrospect what could have been done differently, and there was a lot of very good suggestions from the students. And we are still working on now with national committees and international scientific committees, and I'm also asking my colleagues in the ISC 20th Century Heritage to discuss these issues, that how can we profit from this feedback. And the other exercise we had was that the students were asked to compile a heritage alert, and we used real case studies, the sites that are in danger in one or another way. And here are the examples what we used. I have marked in red the ones that are in Europe, so even though we had students all around the world, the majority of the heritage alerts so far have been made in Europe. That's why it's prevailing also in this list. And here is another list. We had altogether 54 students participated, and we lost in a week's course 4 students, and everything was going on online, which was quite a challenge at the same time. And really what I was also referring to, that the feedback was really positive, that first of all this enthusiasm that the students noticed and gave quite a lot of credit to. They were happy that they could train real case studies, so it was not invented case studies, but they were really practical exercises. And what I think one of the key messages that the experts tried to give the students was also the responsibility of every step you take, because this is something that is of key importance in heritage issues, that the values are very often subjective, they change in time, and there are different points of view, so that you have to be very critical in what you say and do, and especially what you write down, so that you will respect everybody's rights also to heritage. And another, I think, very important lesson learned was the need and the way how to cooperate and how to create mutual trust in a situation of crisis. And this is something that really ICOMOS as an organization is cherishing very much, that we are facing very many problematic situations, and then we have to work as one team, and it doesn't matter in which side of the world you are, or is it day or is it night, so that we have to work in a team. And I think like this project here, with a lot of young researchers and students and universities involved, I think it's a good way also for ICOMOS to continue its work and to constantly interchange the ideas with younger generations and other partners. So I'm really grateful, and I'm looking forward to the rest of the meeting here with also my closest colleagues in ICOMOS, that we can carry on the consultations on the outcomes of this Heritage Alert seminar. But with this short intervention from another theme. I thank you again for the possibility to participate at this very, very interesting seminar. Thank you.
Thank you, Rui. And just to finish the meeting, Thank you. Thank you. Just to finish the meeting, I would like just a short conclusions from the leader of the exploitation committee and from the leader of awareness committee. Yes.
Very short.
Yes, very short. Yes.
Well, the summary is very simple. It's a starting point. Actually, we are setting the basis for site meetings for different key exploitation results to continue to really reevaluate the potential to redirect them. Just the case of Janus, for example, with the modeling, just the case with the UK products, where we want to start with, is continuously working together with some technology centers, which is the case of the Roja Institute and so on. Technalia, for sure, we're involved in many cases. So, and the rest of colleagues. Now we have interaction and we have a proper interface each other. So that is a very good start point. More than the end is a starting point. So, and that's my summary. So let's go.
As far as the awareness committee goes, I think that we all saw that component of the project was really a key thing to get the word out. All this hard work doesn't mean much if it all stays in the room, and that there's been a huge effort to try to take what we've been learning and share it with others and to push it out both through the workshops and through other means, through the social media things. I'm pretty good about sending things out that I get, and I hope others are doing the same. I think that the two main work products that we brought to the fore, the 100th of the 20th that Docomomo did, and the document that we unveiled yesterday, I think will have a lasting impact. At least I hope they do, and that people will be able to use those things in many different contexts and be able to look back on the InnovaConcrete project as the instigator of that and really be grateful that we were able to produce those tangible products that people can then take with them in an intellectual way. And I think that my big takeaway personally from this thing is having met such wonderful people from all over the place, getting to know you and your different viewpoints. This is a point that was made several times today. The idea of collaboration, I think, is key to why this project works so well. And it's also why I think all of us that have participated have feel more enriched by the experience. And I hope that for ICOMOS anyway, that this is a good lesson learned for them, that there are these opportunities out there that we should be trying to take advantage of. Because we have a lot to offer, and I think that it'll also be beneficial to our members to be more engaged in real life situations like these research projects. That people don't get that opportunity very often. So I think it's been fantastic. Thank you so much, Maria, for your leadership. It was a really, really, really difficult thing. I don't know how you did it with all the changes you had going on in your life as well. So it was fantastic. I'm sad that it's over. It was really a fantastic experience, and thank you so much for including ICOMOS. And to my friend Fernando Espinosa de los Monteros, without you, my friend, it wouldn't have happened for us. So thank you for doing that and bringing ICOMOS together with UCA to make it happen. It really was great, fantastic experience. Thank you all. Thank you all.
So this is the end of the final meeting of InnovaConcrete. I am really sad too, but the experience was amazing. I want to say that in my site, we worked 20 years ago in materials for cultural heritage, for buildings, for concrete, for stone, for buildings, but now it was the opportunity to work, to join efforts with modeling, to join efforts with people from ICOMOS, from people from SICA, from companies, and I feel that now we have the best results of our products because we have over 100 papers with our results in 20 years, but now we have the real results in real situations, and this is very, very fascinating for our group. On the other hand, I think that when we start the project, we thought, oh, we have very difficult targets in this project, but it's very difficult to bring the products to the market. It's very difficult to create, to join efforts with people from modeling because it's different language. I mean, not different language for different countries, it's different language modeling and experimental research. And we thought this is really difficult. And in the case of the company, we thought maybe for SICA, this is not the priority. They have another priorities. But I think we achieve all the targets of the project. We have the products very close to the market, and one product in the market. We have the complete restoration of one of the monuments. We have a very fascinating document of Cadiz, and we have a lot of very promising results. This is a dream for me and for my group, and I want to say thank you very much to all the partners. Thank you very much to European Commission because you create. You think this is the correct way, the proposal from InnovaConcrete, and I also want to say thank you to people from my group, to Almoraima, Manuel, Giada, Rafa, and all people, Carlos, all people, Carmen, all people working today and the previous day in the organization of this difficult event. And I feel that this is not the final of our collaboration. Of course, to Fernando, I'm sorry, because I forget Fernando. This is a pillar in the organization of InnovaConcrete. But I feel this is not the final point. This is the starting point for another target, another objective, and I am sure that the collaboration go ahead. And I hope that we continue working together in the future. Thank you very much. Thank you. And I think we are going to take a picture with all people here now in the room. I think here is the place with all people. Thank you.
Any question?